Welcome, everyone. My name is Arvind Narayanan. I'm a computer science professor here at Princeton University. I should say this is a surreal moment for me. I remember telling my co-organizers that we should consider this workshop a success if 30 people attended because it's such a niche topic. And you can see what actually happened on the slide. We have a tremendous amount of interest. We have a lot of participants here on Zoom and a lot of other people watching on YouTube from all over the world. My guess about what's going on is that we've all been thinking about reproducibility issues in machine learning without realizing that everyone else using machine learning in science is also encountering these issues. And that's what makes this workshop such a tremendous opportunity to get together and learn from each other. In particular, we're very grateful to our expert speakers today. They've all published interesting and important papers related to reproducibility and validity in machine learning-based science. We're going to take just the first 10 or 15 minutes for opening remarks by me and by Sayesh Kapoor before we jump into the first session. Let me take a couple of minutes to go over what the workshop is about. Let me start with what we mean by reproducibility. Now, different people and different communities are going to use this word in different ways, and that's perfectly fine. We're not the terminology police. In fact, you'll hear a talk in the first session with a different definition of the term. That's all okay. This is just so we have a shared understanding of why we're here today, regardless of the terminology that we use. So in my view, I see reproducibility kind of as an onion with three layers. The innermost layer is what I call computational reproducibility. That is, if you take the code and data that's provided with a paper and give it to an independent researcher, can that researcher produce the results and figures in the paper? Of course, if the code and data are not even provided, then computational reproducibility is going to fail, but there are a number of other ways in which it can fail, and we're going to hear about that a little bit. A more stringent requirement is to ask the independent researcher to redo the data analysis by writing their own code. If there are no errors in the original code, then at least in principle, the researcher should be able to reproduce the data analysis. It turns out that machine learning code is very tricky. So this is the layer where a lot of failures occur. A layer beyond that is replicability. And that really applies to experimental sciences like psychology. And that goes beyond analyzing the same data. Replicability says if a different researcher were to repeat the experiment on different experimental subjects, perhaps a whole different population, would they get the same result? That's mostly beyond our scope, although there's a lot to learn from that. You may have heard about the replication crisis in many statistical sciences like psychology and medicine. Again, that's what that is talking about. Our scope is mostly limited to the data analysis part of reproducibility. And then the word crisis, is it really a crisis? Maybe it is, maybe it's not, I don't know. The term doesn't matter so much. The point is this. Here's the point. You've probably seen this table on our website. The key thing is that dozens of fields are independently rediscovering these issues. In some of the systematic reviews you see here, a large fraction, a majority of the papers fail to reproduce. So it's clear that some systematic intervention is needed. And that's a big part of why we're here today. I also want to clarify that there's a spectrum of machine learning research. If you're familiar with conferences like NeurIPS or ICML or iClear, most researchers there are trying to improve machine learning methods. As you can see in the screenshot, that community is having its own reproducibility reckoning, and they've been having workshops on this topic for the last few years. On the other hand, I think the majority of you here today are interested in using machine learning in social science or healthcare or chemistry or geosciences or what have you. So the reproducibility issues that arise there are somewhat distinct, although again, there's a lot of overlap. We do have several speakers today who've looked at reproducibility in ML methods research, and we're going to hear from them. Another quick thing, while these issues affect science and research, they actually also affect engineering. There are many kinds of ML failure modes in engineering. And if you're interested in that, here's a very nice paper from about a decade ago. It deserves to be better known. The title is a pun. It's called The High Interest Credit Card of Technical Debt. So if you're interested in ML failures in engineering, I encourage you to check out that paper. But again, our focus here is on ML-based science. So the last thing I want to share with you is a hypothesis on what are the root causes of the ML reproducibility crisis. Here's what we think is going on. Like all research fields, there's pressure to publish in this area, pressure on all of us. That's nothing new. But modeling, predictive modeling and machine learning have many sharp edges. And so when you put that together with the pressure to publish, what it means is that we've ended up in a place where we don't have sufficiently rigorous scientific practices to handle machine learning, which is a powerful but brittle tool. Another root cause is that in most cases, researchers can access the test labels while they're doing their research. Yeah, I imagine that this is the case for most of you. And so even if there's no ill intention, it turns out that the impact of any errors we might make is not random. It almost always causes us to overestimate rather than underestimate the performance or accuracy of our predictive models. So the combined result of all of this is that the published body of work on ML-based science suffers not just from a lot of irreproducibility, but also wild over-optimism about the accuracy that is possible using machine learning. And we think that people are willing to believe these sometimes amazing claims because a lot of the commercial AI hype from companies is spilling over into the scientific world. And it's also possible that over-optimistic results are in fact cited more, and we're going to hear a fascinating paper about this. And if all that is true, that kind of completes and sustains the feedback loop. That's where we are today. And by the way, this also gives us some hints about various places in this map where we can intervene as a community to put the brakes on this rampant irreproducibility. We'll hear more about that in the panels. So I'm going to turn it over to Sayash Kapoor in a minute. Sayash is the main force behind this workshop. You can read his bio in the chat. But before that, I'm grateful to our co-organizers, Priyanka and Kenny and Hian. Priyanka is doing her PhD at Northwestern. Kenny is about to start his PhD at Cornell. Hian is a senior at Princeton. They're all doing stellar work on understanding various limitations of machine learning, including reproducibility. And also a huge thanks to our staff, Ellen and Jonathan and Pete Nowak from the Center for Statistics and Machine Learning, as well as to the Data-Driven Social Science Initiative. All right, welcome again, everyone, and over to you, Sayash.
Thank you so much, Arvind. Thanks for that introduction. And hello, everyone. I'm Sayash. I'm a PhD student at Princeton. And for the last couple of years, one of my main research areas has been leakage in ML-based science. I'm also the one responsible for all of the pesky reminders about attending the workshop. So this workshop is motivated by one of our recent preprints, where we found that leakage is widespread and causes reproducibility failures in nearly every scientific field that has adopted ML. I'll start with a brief overview of our results. But just a quick note before we begin. While our workshop is motivated by our results on leakage, it is in no way limited to just leakage. There are several other causes for concern that you'll hear about today. All right, on to the paper. So our focus here is on data leakage as a source of reproducibility failures. But what is data leakage? So we define data leakage as a spurious relationship between the independent and target variables in an ML model, which could arise literally during any stage of the modeling process, during the data collection, the sampling, pre-processing, or evaluation. Most importantly, this relationship is not present in the distribution of scientific interest, and so it usually leads to over-optimistic performance claims. Now, this definition can be quite a mouthful, so let's look at a few examples. Perhaps the simplest example of leakage is when there is no train test split at all. So this results in over-optimistic estimates of performance because the model is trained on the same data that it is evaluated on. Now, this is a textbook example of overfitting ML models. However, not all cases where the train test split is violated are as innocuous. For instance, you can imagine a case where feature selection is performed before the training and test sets are split. And as a result, we are including information about which features work well on the test set of the model. So this is an example of how errors can be subtle to diagnose, even if the train test split is violated. A second example of leakage is when the model uses illegitimate features for the task at hand. My favorite instance of this is when a model that was intended to predict hypertension in a clinical setting had the use of antihypertensive drugs as one of its most important features. In other words, the model predicts that you can have hypertension if you're currently using medicines for curing hypertension. Now, as you can imagine, such a model does not have any clinical utility at all, since it is using a feature that we don't have access to in a clinical setting. Once again, this error might seem very easy to diagnose, but with datasets having hundreds of features, it can be hard to find the ones that cause leakage. A third and final example of leakage is sampling bias. So here's an example. A recent paper, the author of which would be in the first panel, by the way. The paper found that several models that were used for diagnosing COVID-19 were actually distinguishing between adults and children, because all images of people with COVID came from adults, and all images of people without COVID came from children. Now, once again, distinguishing children from adults is far from what the model claimed to do. The model actually claimed to diagnose COVID-19. So hopefully these three examples have given you a little bit of intuition about the different kinds of leakage. Now let's zoom out and see how prevalent it is. The main finding of our paper is that data leakage is widespread across ML-based science, and this table shows our results. The rows in this table are reviews of ML-based science across disciplines, and the columns on the right-hand side depict our taxonomy of 8 kinds of leakage that we identified. The key thing is that 329 papers have been affected across 17 different fields, and that leakage is a cause of reproducibility failures in each of these cases. Perhaps most worryingly, as Arvind mentioned, it seems as if each field is independently rediscovering these errors. So why is data leakage so rampant in ML-based science? Here's our hypothesis. ML-based science is particularly prone to data leakage, and much more so than other domains where ML is used, such as engineering. As a result, the ML community, which is focused primarily on solving engineering problems, has not really taken data leakage very seriously, leading to errors in other domains, such as scientific research. Here's a personal anecdote. So before I started my PhD, I used to work as a software engineer at Facebook. And it was clear that most people building ML models knew that data leakage could be an issue. But no one really cared about it too much, because you could always test your models in production and roll out a quick fix if you found there was leakage in your models. In other words, Facebook allowed you to move fast and break things. And although that mantra did not always work out well for them, it was quite enough for addressing leakage. In contrast, ML-based science has no production setting at all. In most cases, the final output of an ML project is the paper itself. And so if you're careless about not addressing leakage, other researchers could build upon our paper without acknowledging the lack of correctness of the models. And so you can see how this is a very, very different world from engineering, where you can roll out quick fixes to products which are already being deployed. So how can we fix leakage in scientific research? Here's our proposal. Along with our paper, we introduce model info sheets, which is a series of about 20 questions to guide researchers through the different types of leakage we found in our study. They're based on a taxonomy of 8 types of leakage and can help find leakage before a paper is published. The model info sheets ask researchers to provide very precise arguments to justify the absence of leakage, and they can help detect each type of leakage that we identified. You can find a template for the model info sheets on our website. So zooming back out a little bit, why this workshop? The results of our preprint were what motivated this workshop, because we found reproducibility issues in nearly every scientific field that has adopted ML. In each case, these errors were being independently rediscovered. In other words, it's a systemic problem without a systemic solution. Again, while our paper was focused on leakage, reproducibility issues can go way beyond leakage, as we'll see in the talks today. And our hope is that this workshop will foster the interdisciplinary conversations that are a key first step towards solutions. So as Arvind mentioned earlier, when we were making plans for this workshop, we did not anticipate such a big turnout. So first of all, thank you so much for showing up. To make the workshop a little bit more interactive, we're hosting a tutorial and an interactive session tomorrow at 3 p.m. Eastern Time on the same Zoom link as today. In addition, we've also created a Slack channel to create a network of researchers who are interested in reproducibility issues. You should have an invite link in your email for the Slack as well as for the Zoom. But if not, you can fill out a form on the link on the slide. All right, let's get into our plan for today. So we'll have 3 sessions of around an hour and a half to 2 hours each, and a 20-minute break after each session. Each session consists of 3 or 4 talks followed by a panel discussion. And during the talks, please feel free to put your questions in the Zoom chat, and our moderators will ask those questions during the panel. And here are the timings for each panel. With that, let's dive into session 1, Diagnose, moderated by Priyanka Nanayakara. Over to you, Priyanka.
Hi, everyone. Thanks, Ayash. Yes, I'm excited to introduce this panel called Diagnose on an outline of common failure modes prevalent in scientific research that uses ML methods. First, I'll introduce our speakers. First, we have Dr. Michael Roberts, who's a senior research associate at the University of Cambridge. Second, we'll hear from Dr. Jill van de Wiele, a postdoc at Ghent University. And finally, we'll hear from Dr. Odd Erik Gundersen, an associate professor at the Norwegian University of Science and Technology. Okay, before we begin the sessions, I will pass it to Arvind to make a quick note about timing.
Yes, thank you, Priyanka. I just wanted to mention that we've asked the speakers to keep their talks to 18 minutes, if at all possible, 20 minutes max. And so at the 19-minute mark, I might give the speakers a reminder. And for doing that, I've borrowed my toddler's toy bell. And so if you hear that sound, that's not Zoom bombing, that's just me reminding the speakers. And Priyanka, I believe the order was Jill and then Mike. I apologize for the confusion. I believe that's what we told the speakers. Is it okay if we go in that order, if the speakers are okay with it?
I don't mind.
Thank you.
Me neither.
Okay, sounds great. So in that case, then, Jill, do you want to maybe begin?
Yes, sure, my pleasure. Let me quickly share my screen. Is it visible?
Yes, looks good.
All right. So yeah, hello everyone. And first of all, thank you for being so numerously present here today. This is probably the largest audience I've ever given a talk to, but I'm looking very forward to it. So as already mentioned, I'm Gilles van de Wiele, and I'm here to discuss a paper we published some time ago, which was titled Overly Optimistic Prediction Results on Imbalanced Data, a case study of flaws and benefits when applying oversampling. And this publication was published in the context of the preterm project, in which we were trying to build predictive models in order to estimate the risk for preterm birth for patients in the hospital. And this was a collaboration between many people listed here on the slide. But before we dive into it, maybe a quick introduction about myself. So who am I? Well, I'm a postdoc at the Internet and Data Lab of Ghent University and IMEC. And my research topics center around interpretable machine learning, knowledge incorporation, and I also like to work with time series and bio-inspired algorithms. Moreover, I'm also a competition master on the Kaggle platform, and that will be relevant more towards the end of my talk. Now, my talk will consist of 3 major parts. First, I will sketch the necessary context and quickly explain what preterm birth is. At least I will try to do my best, as I am a computer science engineer and not a medical expert. Then I will dive deeper into the flaws and benefits when applying oversampling. And then in the end, I will quickly give 5 tips and tricks perhaps to avoid these mistakes in the future. So what exactly is preterm birth? Now, according to the World Health Organization, it is defined as delivering or giving birth before the 37th week of pregnancy. Moreover, we can make further distinction between the types of preterm birth depending on the severity or the stage of pregnancy when birth is given. Now, preterm birth has quite a high prevalence in on the entire world scale. The prevalence is around 11.5%, and the implications of preterm birth are very significant in a negative way. And because of that, preterm birth is actually the leading cause of death among children under 5 years of age, according to the WHO. Now, according to the WHO as well, 3/4 of these deaths could actually be prevented with currently existing and cost-effective interventions. To give one example of such an intervention, that is the administration of corticosteroids. That helps the development of the lungs of the child, but it is a bit of a trade-off, as it typically has negative repercussions on the brain development of that child. Moreover, the effectiveness of these corticosteroids are most optimal when they are administered 2 to 7 days before the actual birth. And this is where these risk for preterm birth models come into play. If we are able to somewhat accurately estimate how much longer the pregnancy will take, then clinicians can guide their treatment based on that. And yeah, you can tackle this problem either by directly predicting the amount of time towards birth, which is somewhat of a regression problem solved through survival analysis typically. But in this presentation, we will look at binary classifications, whether or not this woman will deliver preterm or not. Now, within this project, we had one certain research question, and that was whether a certain modality of data would be informative for these time-to-birth models. And the modality I am speaking about is uterine electrical activities. So that can be measured by a setup as depicted on the right top of this slide. So by basically attaching patches to the belly of the patient, and it produces a signal similar to the one depicted here on the bottom. And so we wanted to investigate whether this would be informative for our time-to-birth models. Now, at the time, and still, the Ghent University Hospital does not perform electrohysterogram recordings. So we had to look out for a publicly available data set. And we quickly found one on PhysioNet, which is a large compilation of biomedical data sets. And the data set we stumbled upon was called the Term-Preterm Electrohysterogram Database, or the acronym TPEHGDB, but that is still quite the mouthful. So I will just refer to this data set as the data set for the remainder of this presentation. Now, this data set contained information about 300 different pregnancies, and the provided information was, on the one hand, a raw EHG signal, and on the other hand, some clinical variables, such as whether this woman had diabetes or not, their smoking behavior, their age, their weight, and so on. Moreover, these recordings of these EHG signals were performed at different stages within the pregnancy. A larger part of the data set had their recording sessions performed roughly around the 24th week of pregnancy, so a very early stage, while the smaller half of the patients had their recording performed more later, towards the end of the pregnancy, around the 31st week. Moreover, as we can see from this visualization and the table, the data set is very imbalanced. We have only a very small fraction of patients in our data set that actually delivered preterm, but more on imbalance later. So the first thing we did is what we always typically do is set up a quick baseline. And as a matter of fact, along with the raw EHG signal, this data set was also accompanied with some pre-computed features. And so as a first baseline, we just concatenated the clinical features and the pre-computed features together, and we saw or tested how well a simple classifier such as a random forest would perform on this data in a cross-validation manner. And if we look at the metrics depicted here on the bottom, we see that we achieved an area under the curve of roughly 60%, which is a bit better than random guessing, as they say. But if we zoom deeper into these other two metrics, the specificity and the sensitivity, well, the story is a bit more worrying. Maybe as a quick reminder, as these metrics are typically only used in the medical domain, at least in my experience, what these are. So the specificity is how much of the negative samples in the data set your model detected. So in other words, it's the true negatives divided by the total amount of negatives in the data set. And then on the other hand, the sensitivity is maybe better known as the recall score, and that is how much of the positive samples were detected. And so the true positives divided by the total amount of positives in the data set. And so As we can see, we have quite a high specificity, but a sensitivity of 0. So this model would actually never be predicting that a woman would deliver preterm. Maybe an important remark here is that these metrics are calculated by setting the threshold at the default value of 50%. One could possibly tune this threshold to obtain somewhat of a more balanced trade-off between these two metrics, but it is definitely on the low end and too low to ever be useful in a clinical practice. So that was a bit of an introduction about preterm birth and a quick overview of our first baseline. And so now let's dive deeper into the flaws and benefits of oversampling. So yeah, as I said, our model was far from adequate to ever be deployed. So I did what any good PhD student would do at that time. I decided to go on Google Scholar and consult some literature. And actually, while reading all of these papers, I noticed that a large amount of them were reporting near perfect results on this very specific data set that I was using as well. As a matter of fact, we identified 11 papers that shared a common aspect in their machine learning pipeline. So let's zoom in a little bit on what this common aspect was. Well, it was oversampling, and this is when you augment your data set with artificial samples. On the left here, we have a simple toy data set in 2D, which is very imbalanced. We have much more blue samples than we would have red samples. And as a result of this, the machine learning model favors the majority class. And we can also see this in by looking at the decision boundaries of a k-nearest neighbor model, for instance, trained on this data. So we see that there are not many regions in this space where the model would actually be predicting red. And one way to be circumventing this problem is to add artificial samples to your data set. And when we do this, we see that this has quite an impact on well, the balancing of your predictions of the model. So we see a lot more regions where the model would be predicting the red class. Maybe as a small detail, these artificial samples are generated based on the limited amount of samples that we have in the original data set. So yeah, let's try to do what they all do and re-implement their approach taken from literature. So we'll apply augmentation on our data set and then assess in cross-validation how well this random forest model would perform on this newly created data set. And yeah, we can see quite the increase in our metrics. As a matter of fact, it's a mind-blowing increase that we see in our metrics. We all of a sudden get an area under the curve of nearly 100%, so near perfect. And also our specificity and sensitivity rates are extremely, extremely high. So yeah, a model like this would have serious positive implications, one would think, because we can now start detecting preterm birth at already a very early stage of the pregnancy. But wait, isn't this like a bit too good to be true? Well, as a matter of fact, it is way too good to be true. There was a fundamental mistake that was made here in this pipeline. The mistake we made was augmenting our entire data set before partitioning it into mutually exclusive training and testing data sets. And by doing that, we actually introduced two types of leakage, which are somewhat related, but slightly subtly different to our data set. On the left-hand side of this slide, we have a very simple toy data set, and we will be generating some artificial samples by just drawing a line or hyperplane between a pair of 2 points in the minority class, so red in this case, and then generate some points along that line we just drew. And by then splitting it into train and test after doing this step, we will introduce these two types of leakage. On the one hand, we will be adding artificial samples that are highly correlated with the train samples to our test set. For instance, this artificial sample looks very similar to this training sample. Moreover, we will be evaluating our model not only on real-world samples, but rather on a combination of real-world samples and artificial samples. And on the other hand, we also have artificial samples added to our training set, which are very correlated to the testing set. For instance, these 2 points. So before diving into these more realistic results, the result of this is that we're assessing the memorization capabilities of our model instead of the generalization capabilities of our model. And typically for research, we are interested in the latter and not the former. So let's correct our pipeline and introduce some more realistic results. So what one needs to do is apply the augmentation solely on the training data and leave the test data as is. And so if we do that, we see a minor increase in our area under the curve and a more balanced trade-off between this specificity and sensitivity scores. Of course, this is still not adequate enough for clinical practice. And so, as I said, we suspected 11 papers of making this mistake, as they all had near perfect results and they all applied oversampling on our data set. And in order to confirm this suspicion, we decided to re-implement all of the 11 pipelines. We had to re-implement it ourselves because none of these papers provided the code along with the manuscript. And so after re-implementation of these pipelines, we noticed that for almost all of these studies, the performance went from near perfect to almost random coin tosses. So this raises questions about any of the conclusions made in those papers. Now, you don't need to take my word for it. We practice what we preach, and we published our code along with the paper we published, of which you can find the details here in the bottom of the slide. Moreover, the code base includes an additional experiment in which we generate some random noise and label it at random as well. And of course, one cannot expect to achieve area under the curves much larger than 0.5 as the data is random. It's generated in that way. But we show that by applying oversampling in this incorrect way, that you can actually achieve near perfect results on random noise. Now, those 11 papers were not the only one that reported near perfect results. So we also investigated all other papers, and we found 8 papers which applied the opposite of oversampling. They did undersampling, so subsampling the majority class and then doing cross-validation on that newly created data set. And that is, of course, that introduces biases as well. We also identified 2 papers in which they cutted the original signals into smaller subsignals and then did not apply grouped cross-validation. And as a consequence of that, it could occur, and most likely occurred in most of the cases, that 2 subsignals stemming from the same original signal actually are divided into both training and tests. And of course, these are very correlated. Now, to conclude my talk, I will just quickly give 5 tips and tricks to avoid these mistakes. This will definitely not be an exhaustive list, and I'm sure that other speakers, and especially speakers in the next session, will be able to provide a much better exhaustive list of tips and tricks. Now, the first one is if you're using software, popular software toolkits, such as scikit-learn in Python, for example, well, most often they have built-in mechanisms to avoid this explicit data leakage. So in scikit-learn, this is called a pipeline, and you can define all the steps in there, and scikit-learn will make sure that no leakage occurs when doing feature selection, normalization, oversampling, modeling, and so on. Secondly, you should always be skeptical of results that seem too good to be true. When doing data analytics, sorry, there's a quote here, my headset just turned off, I was a bit confused. So always be skeptical of results that seem too good to be true. Here's a very fitting quote from Hadley Wickham, chief scientist of RStudio. So when doing data analytics, your default position should be that of skepticism. In the case of our data set, can we really build a near perfect classifier with 300 samples with data collected at very early stages of the pregnancy and with this limited amount of features? Well, the answer to that is probably no. Thirdly, well, just don't use oversampling. It introduces many assumptions that often do not hold up, and they make your training pipeline a lot more complex. Each of these oversampling techniques will have their own associated hyperparameters that you will need to tune, and they also increase the amount of training samples, so training procedures will take longer. And more importantly, in the context of this talk, it opens the door to fundamental mistakes. Fourthly, if you're using a publicly available data set, you should always provide your code along with the paper. If that is not the case, the journal should actually desk reject the manuscript. It is inexcusable when your data is publicly available to not provide the code along with it and let other researchers just reproduce your results. Of course, this is difficult when the data is sensitive, which is often the case in the medical domain. And then finally, which is going back to the introduction, well, explicit label leakage actually never occurs on Kaggle. An important remark, we have many other types of leakage that occur on Kaggle, but no explicit label leakage. So perhaps a similar mechanism could be set up by the dataset publishers and by journals. These are the 5 tips and tricks, but I'm seeing that that time is up. So here they are, you can quickly read them. And with that, I would like to thank you for your attention.
Thanks so much, Jill. That was great. In the interest of time, we'll go to the next speaker. Mike, are you ready to begin? Great, we can see your slides.
Right, can you hear me as well?
Yep.
Perfect. Okay, well, thanks for the invite to talk today. So yeah, I want to talk about whether the reproducibility crisis that I'll hope to elucidate on is actually a natural consequence of the way that we work at the moment and the way that we're incentivized and everything like that. So just to sort of show my journey into understanding about reproducibility issues, I started doing a lot of work with machine learning for COVID-19, and that's really exposed me to a lot of the issues of reproducibility of existing models. I'll talk about those later in detail, and then moved into using machine learning for incomplete data and found a huge number of reproducibility issues there as well. And then just to complete everything, we started to get to, right, we want to use machine learning at scale as part of a large project connecting up many hospitals, and found more reproducibility issues there. And finally, there's fundamental issues around machine learning and code, and the way that we code and the way that we build code bases. And each of these areas is kind of building on a paper we've either published or is in preprint or is in preparation at the moment. So this initial one is around machine learning for COVID-19. And so we wrote this paper last year that was looking at radiological imaging, so just chest x-rays and CTs that claim to diagnose or prognose for COVID. And with COVID-19, it was almost a perfect test case for whether machine learning could have great applications for image-based machine learning. So we've never before had access to such a large database of images for a single disease, which were all collected around the same time period. So we removed manufacturer and machine biases quite significantly, and also where the disease has a short infection time. So the outcome data is obvious within a couple of months from all of the patients. So this was a really good opportunity for machine learning to contribute to help the pandemic. But why did it fail to significantly contribute, in my opinion? Well, we looked through, we ran the systematic review and looked through all the literature to find papers that used machine learning along with CT and chest x-ray imaging to diagnose or prognose for COVID. And we have 320 papers eligible for the review, which would have been a Herculean task to analyze. So we put a basic quality check in for reproducibility that said, you have to explain where your data came from, you have to explain what model you used, and you have to explain how you trained it. Very kind of basic parameters that are outlined in the paper, which left 62 papers to analyze in detail. And we found that none were of safe clinical utility. And this is due to biases in the way that the data was collected or curated, the models themselves in the development or the evaluation of the models. And I'll kind of come up with the main pitfalls here that we found. So the first one is kind of obvious, is around you should know where your data comes from. We turned this idea of Frankenstein data sets, where these are a huge host of the COVID data sets that existed back when we did the review. And we find that a lot of them are dependent on other data sets. So for example, this CERM data set feeds into this IEEE and this COVID-19 database. Both of them the IEEE one then feeds into this radiography database and COVID-X, and COVID-X gets fed into by these other two. So we have 3 copies of images at least in this data set that are the same, and they'll appear in the train, test, and validation splits without you actually knowing. So understanding the provenance of your imaging is really important. There's also extreme biases in the data themselves, so either how they're acquired or how they're displayed on screen. So in particular for, it was mentioned earlier by Sayash about the children versus adults in the COVID cohort. So many people use this pediatric data set of pneumonia patients and set them off against adults with COVID, clearly a massive issue. The other biases were, for example, in chest X-ray, you have labels on the image which indicate whether you're lying down or whether you're standing up, for example. But clearly a patient that's lying down and can't stand up is more sick than one that's standing up. And your model shouldn't be able to use the fact that they're lying down as a marker of outcome. Another key bias we found was that ground truth was often assigned based on the images themselves. So people would look at images and say whether they were COVID positive or negative. And this process just hard codes in the bias of the radiologist rather than letting it do what we want it to do, which is the model to learn its own features of outcome. And the final one is around resolution of the network. So a lot of the models downsample images to a fixed resolution, which is purely based on, we want to use pre-trained networks, therefore we have to do the resampling down to this resolution, which is clearly not right. They should be driven by a clinical decision, not just the convenience for the machine learning practitioner. The features of COVID that differentiate it from a different pneumonia are very specific and visible at high resolution. So I'll now move on to machine learning for incomplete data. And this is very important. So normally the data that comes out in the real world or in hospitals is incomplete for many reasons, such as the data is collected at different sites who perform different tests or perform tests at different intervals. So you'll end up with these blank areas in your data set. And you must perform imputation on that data to replace those with a kind of good guess, typically because machine learning models prefer to have complete data sets to fit to the model. So why is imputation really important? Well, here's an example from a while ago that is the Q-risk model that was designed for predicting your risk of a cardiovascular event in the next 10 years. And initially, when the paper was published, they found that there was no link between cholesterol and outcome of these patients. However, other researchers found that when you actually only consider the complete data in the data set, this link to cholesterol does come back. And so actually, after improving this imputation method, the link to cholesterol was recovered. So typically, imputation is incredibly important because the model interpretability is completely sacrificed if you don't get that replacement correct. And we can just show a quick example here of, here's some true data on the left for which we now delete half the samples and then we perform imputation. And if we impute with conditional expectation, for example, we get the mean square error very low, 1.00, and then the Wasserstein distance, which measures the distribution of these values, well, that's been recreated 286 again. But we can see visually that this recreation is pretty terrible. However, if we now use two different methods, say Miss Forest and mice, we see that the mean square errors both are higher than this really bad imputation, and their Wasserstein distances get significantly smaller than that. So it's very important to really consider what is quality and how should we be measuring the quality of the imputation methods, because many of them use mean square error. And typically the new methods that use, say, deep neural networks and things like that are using mean square error to design their models, but they're sacrificing interpretability at the same time. So in the paper that's referenced back at the start of this, I'll go to it later, our preprint, we find that many of the new methods fail both to recreate the data distributions and to give stable imputations. So if you run one of these deep neural network methods several times, each time can give you different results. And sometimes you can get mode collapse and get complete nonsense. And this is really important because you're then fitting a machine learning model to this data that's had mode collapse and its interpretability is completely sacrificed. Also, always important is that the missingness pattern may be informative for these models. There may only be some tests that are performed if you're in intensive care, and you don't want the imputation to be so bad that then it can tell which values have been replaced in your data set, and therefore learn who is in ICU and use that as a feature of the model. The next part I want to talk about is machine learning at scale. So we've been running a project here called Blood Counts, which uses full blood count analyzers at huge scale, thousands and thousands of these machines feeding into our network, but it leads to significant issues of bias in the models. So I'm going to just explain what a full blood count is for anyone that doesn't know. You go to the doctor and have a small sample of blood taken from you. It then goes into an automated analyzer. And from there, a decision is made on whether you should go to hospital or whether you need a particular treatment. And it's the most common clinical test in the world, 3.6 billion per year. And it's absolutely essential in clinical practice. And so we're linking together these thousands of machines, and we can see here that this is one of the typical reports you get from a full blood count and how everything feeds in. But typically people collate this data at scale from, say, 50 hospitals, you throw it all into one data set and make your predictions. But this is really, really not a wise approach to follow. And I'll show you why here. So this is kind of our data model that we're working with. So if we say on the left, these are your observed full blood count values, and on the right were the true values. And in the middle, there's some functions that interfere with those true values and make them to the observed values. So in particular, one of these is an error introduced due to the machine itself. So every machine is calibrated slightly differently and gives different results for the same blood data. And also, there's an error introduced due to clinical practice itself, that if blood is taken from you and then sits around for a few hours versus goes straight to the machine, it tends to really change quite significantly. So these two errors we need to really understand, because if you're working on a massive scale at different sites, you don't just want the model to learn this came from a trauma center, therefore the patient's had a worse outcome than a patient in a GP surgery down the road. So here's just an example of a clinical bias that we found in our data. So this is from a blood donor study, and we see that this is on the x-axis is the delay between the time you were bled and the time that the result went into the machine, the blood sample went into the machine. And we can see in the blue line that these white cell counts fall away consistently over time, quite significantly. And you don't want your machine learning model to be biased by this. And so we've done some work on correcting out this bias. But some other clinical biases are, temperature of storage. There's always differing service at weekends in the blood processing labs, and also the seasonal variations in the blood. And you don't want the fact that a blood sample was taken in February to be in any way informative to the model, ultimately. There's also significant machine biases that we find. So these are, for example, two machines used in a blood donor study that we're working on. And you can see that for some of these variables, there's a 10% difference between the blood sample measured on one machine and another machine. Yet there's no fundamental difference between these blood samples. They were randomized to these machines. So we would expect everything to be consistent. So this blue line is showing the differences we see. And these machine biases are due to different calibration between machines, when they were serviced, how long they've been on that day. But we really need, if we've got thousands of machines in our network, to calibrate out this bias. And because we want to ensure maximum interpretability of these models at the end, ultimately, and that the machine and the clinical practice that led to those readings at the end are irrelevant to the predictions. So what are the real issues that we found here? Well, there are lots of publications that use full blood count data and lots of publications that use it on lots of machines, but there are none which strip out or focus on these biases in particular. And these are absolutely critical to understand how we should model blood data. And importantly, especially in Cambridge, many hospitals reserve a machine to permanently be open for urgent care blood samples that come in. And you don't want the machine to be able to use the model to be able to use the knowledge that it was run on a particular machine that's kept for urgent care and can make a prediction of outcome, saying, well, this person was run on machine 5, therefore they're likely to have a worse outcome, just because that machine is always kept aside for urgent cases. And finally, models can't generalize across sites where the clinical practice significantly differs. So if at one medical site, it takes an hour consistently to get the blood to the machine, and at another, it takes 3 hours, these models will be significantly biased by this clinical practice, this change in clinical practice, and will start to make spurious predictions. And then finally, we're going to talk about issues with machine learning and code. And this might be kind of quite a shock of like, why am I going to talk about how we can do the issues with code itself? But how are we going to do machine learning without code bases? Well, it's more about how we need to change our approach potentially. So 10 years ago, this was the idea of who was a software engineer, sat in front of a terminal, coding and coding all day. But however, nowadays, this is also everybody in this field. Most of the people in the audience will be data scientists, mathematicians, statisticians, machine learning engineers. Everybody that's involved in this field now has to code like a software engineer and maraud in this space that they aren't trained to be in. Designing extremely complex systems using complex data and trying to fit models to it. So what are the issues in this kind of new world we're in? Well, there's been a massive explosion in the amount of data that's available. We're drowning in data and also in the sources of that data. So data comes in from so many different streams nowadays, and we need to master this ourselves. So typically, as machine learning practitioners, we often are involved in structuring this data and pre-processing this data all by ourselves. And then without this deep knowledge of the domain that we're working in, say it's clinical for most of my work, we really lose control of the biases that are hiding in this data. So just as a summary, we kind of have this extremely complex data we now work with. And then we go into machine learning space as well, where this is an idealistic interpretation of what machine learning would be to the community. We've got this very organized map of what's going on, and we all know what we're doing, and we code it very carefully. But actually, it's more like this, that I feel there's a lot of moving parts, and all of them simultaneously move in a very complex way. And we've built these very complex systems for doing machine learning. So for example, here in a typical machine learning pipeline, you've got your data loading, your pre-processing, your training, and your evaluation of your models. And the typical workflow for a machine learning project at the moment is that the code is built as a monolith. We code and code and code and code everything at once. We tinker with it and we debug it until it stops giving any more errors. And then we also train these architectures using all the data we've got, because more data is better, and then analyze the results. But this is crazy as an approach, and we should stop doing this. I'll try and give some feedback on why. So my general recommendations for the field and insights that we've got from these 4 areas of work are at the moment, we need to really rethink the incentive structure for machine learning based research. Currently, if I'm an academic and I get a great result from a model, my temptation is to publish. I have no temptation to keep revisiting my model to try and find out what could be wrong with it that I don't know is yet wrong with it. And unless there's that incentive there to, rather than just, oh, my AUC is better than your AUC, I'm now going to bold it, put it in a paper and move on. Unless there's a temptation to share your code freely, make the code well documented, reproducible, reusable by everybody, we're never going to get anywhere. So really looking at the incentive structure. Why would I care? Also looking at other fields. Clinical trials are very slow and they're done in phases, and they're done this way for a very good reason. We don't develop machine learning methods like this. We typically take all the data that we're given and we fit the model to it. Whereas clinical trials work on, let's start on a small number of cases and try and extract a signal, and you build and build and build the scale of your work as you go like that, rather than just, we've got 5,000 images, let's use 4,000 of them for development and 1,000 for testing. That seems a bit crazy to me. Also in clinical practice, you typically create a study plan in advance where you would consider all the problems. So like Gilles was saying about imbalance, we really need to think about that in advance. Do we even have the power, if our model plan was brilliant, do we have the power worked out that, you know, we can make conclusions that we're claiming we can make? So, and you would know in advance the real flaws of your study. Then in addition, the literature really needs purifying. So for our projects in COVID in particular, we wanted to fit COVID models or use someone else's COVID models. We didn't care, but we just wanted to do something and apply something. But every single model we were coming to was not reproducible. It was really poorly documented. We couldn't do anything. And so all that literature just became a sort of a field of nonsense for us, that we wanted to pick out the really good stuff. And at the moment, we work on the balance of how do we exclude things from our consideration as quickly as possible. And so we really need to go through and purify the literature, or ensure at least the next papers coming out are pure. We need to use checklists. This is just a basic, lots of fields before us have found that they're useful. Airlines, clinical practice finds that it improves quality, it saves lives. We need to be doing this as well. And journals need to be involved in enforcing the use of them, and some of them are. Just to say that complex data sets plus complex systems is an absolute nightmare for reproducibility. We've paired these incredibly complex things together that create so many sources of bias for us that we need to really be conscious of. And it's just come to the end. So I think as practitioners of machine learning, we need to rethink our coding methodologies, maybe looking to software engineering with agile methodologies, unit testing, slowly developing code bases, developing code that has singular uses, things like that. And finally, if you're not enforcing your assumptions that you're making about your model in your code, someone is going to break it. If you require a variable to be a float rather than an integer, you must enforce that in your code. You just need a simple assert statement and you're done. And there's no excuses anymore for all of these issues. And thank you for your time.
Awesome. Thanks so much, Mike. Before we move on to our third speaker for this session, I'll just make a note that we've been putting bios for each of the speakers in the Zoom chat. And for our YouTube participants, we have a link in the description, which also shows who's speaking and speaker bios. Okay, with that, Odd Eric, are you ready to begin? Excellent, we see your slides.
Can you hear me as well?
We can.
That's perfect. So thank you very much for inviting me to this workshop. I'm really excited about it. And so I'm Odd Erik Gundersen. I'm the Chief AI Officer at Trønderenergi. We're a renewable energy company, soon changing name to ANEO. And then I'm an associate professor at the Norwegian University of Science and Technology. And I have, one of the reasons that I'm so excited to be here is that I have been thinking about reproducibility for 10 years. And it started with a keynote at a conference I was attending, and it was really about the reproducibility crisis. It was about something else, but this researcher, Yolanda Gill, she's past president of AAAI, and she was mentioning the reproducibility crisis. And I was, so why aren't everybody running around screaming? The house is burning, basically. So and I started to dig into this and read a bit about it and try to understand what it all was about. But I have to say my questions weren't really answered. And to be honest, I think the main problem of this reproducibility crisis is that we do not have a shared definition. So I would like to talk a bit about how I understand reproducibility. So let's start. So why do we need a shared definition? So we need to capture the concept, and then we can create a shared understanding of this concept. We can use it for teaching. We should use it when we practice our research, and we should use it for evaluating research done by others. And maybe we could use it for helping us understand sort of the limitations of the conclusions that we draw, or even what went wrong. So, so what would characterize a good definition here of reproducibility? It should be a mental model that you can easily look up when you need it. It should be simple to understand, but it needs to have the depth to be valuable. We should be able to operationalize our understanding and help let this definition help us define our experiments and design them and evaluate them. and it should be connected to the scientific method, because as everyone writes in their papers, reproducibility is a cornerstone of science. So then let me try to define reproducibility for you. This is reproducibility. Reproducibility is the ability of independent investigators to draw the same conclusions from an experiment by following the documentation shared by the original investigators. Okay, so if this is reproducibility, then what is a reproducibility experiment? Well, reproducibility experiment is an experiment that is conducted by independent researchers from those who did the study in the first place. And they do this from the documentation, but the documentation isn't the complete experience. So they have to bring something else to the table. And based on this documentation and what they bring to the table, they draw a conclusion. And if the conclusion is the same as the original researchers made, well, then we have reproduced the experiment. If not, well, we haven't reproduced it. Okay, so it's simple. Okay, but where is the depth? Is there depth? Yeah, I think it is. So we have independent investigators. So it's different from repeatability when you just repeat what you do. I made an experiment. I just press the button. I run the same thing. There's no difference. It's doing the same over and over again. In independent investigators, they should also read the documentation, understand it, and assess whether this experiment actually answers the research questions or properly tests the hypothesis. Okay, and so that is one thing. Another thing is that there's some documentation here. So what is the documentation, and what is the same conclusion? In order to understand this definition, we need to understand what the documentation is and what same conclusion means. Okay, so let me show that through going through the scientific method. And I've tried to capture the scientific method here in form of an empirical machine learning experiment. And instantiated it for a machine learning experiment. So first we have to observe the world, we create some beliefs, and we make a theory about the world, what we observe, and this, if it's scientific, it can be tested. So we generate a hypothesis that we want to test. We a statement about the world that we want to find out whether it's true or if it's false. Then we have to design the experiment and write down what is it exactly what we want to do. What is the hypothesis? What is our prediction and why? What is the plan, the study plan, and what is the analysis plan? And how should we get the data? And then after having planned all this, we need to in machine learning we need to implement this as code. We have code for the machine learning algorithms, maybe that we want to test, and we have the workflow of the experiment. We have setup of the experiment. We might have some pre-processing code of the data. We have the data. It's all digitized. We have some auxiliary software that is not the software we want to test, but for instance, the operating system and maybe some libraries that we're building our software on, such as TensorFlow maybe. And we're running this on some hardware. And when we have done all of this, we can now run our experiment, which is basically to press a button and let the code do everything, and we produce some outcome. And if we're classifying images of cats and dogs, well, the outcome is the label attached to each image of cats and dogs, cat, cat, dog, dog, dog for each of the image. That is the outcome. And then we have to analyze this outcome. And typically in machine learning, we do this with performance metrics, and we look at different methods and how well they perform. And then we have code for this as well, both for running the analysis itself for performance metrics, and also code for visualization. And based on the results of this analysis, we have to interpret this analysis, and then we have to draw a conclusion. And this conclusion, we use it to update our beliefs. Oh, our prediction were right. Very good. Then nothing to change. Our prediction was wrong. Well, our belief about the world was probably wrong then, so we have to update our belief. So, and this is sort of a general experiment. And here you have to make a lot of things that you do not have to make or think about if you're doing a reproducibility experiment. For instance, you have to identify the hypothesis, you identify how to test it, and you have to collect the data, for instance. Okay, so then we have an instantiation of this reproducibility experiment. So we can think about it. Many think about reproducibility in machine learning and in computer science as you have the study protocol, everything, the workflow, the setup of the experiment as code. You have digitized data. You have the machine learning algorithm as code. You have performance metrics and everything as code. What you bring yourself to the table here is some hardware and some ancillary software on top of that hardware. It might be a different OS than what they used in different experiments. It might be different computer all along. And then you run the experiment, and then you get the outcome and figures and all that, and you have to interpret it. So that is a reproducibility experiment. Not the only way of doing it, but that is one way. We're going to look at these different things. Okay, so as part of this definition here, we I want to talk about different dimensions of this of reproducibility, because when I talk about reproducibility, I only use one term. I say that, okay, we have repeatability, it's just doing the same, it's no scientific in that, it's just what we do, we run our code the same once again on everything the same. And I don't care about replicability. I just say that replicability and reproducibility, they are basically interchangeable. I know that people distinguish them, but I think we can come away with instead thinking about different dimensions. And the two different dimensions I'm talking about is one, we can talk about, okay, which documentation did we use to run to do the reproducibility experiment? So what did the researchers share with us? What did they open? That is one thing, they can share everything, but we don't have to use it. We can write our own code. Okay, but what we used in order to reproduce, that is the type of reproducibility experiment that we run. And then how we reach the conclusion, that is the degree of reproducibility. Okay, so now we have two dimensions that we can characterize our reproducibility experiment. It's the type based on documents, and it's the degree based on the results we got. Okay, so let's go through the documentation first. So there are three types of documentation here. We have sort of descriptions, or the written text. This could be if we're reproducing machine learning experiment on an AI experiment, then it would be the description of the algorithm and how the experiment is being conducted, how we analyze it, and as well as the hardware specification and whichever software you use to run it, TensorFlow and Windows, all that. But that is typically what we document in a paper. This is the description part of the documentation. And then luckily for us in computer science, we have code which allows us to share exactly what we did and the procedures that were run, and we can codify all of these as workflows, and every setting, everything, we can share that. That's a good thing. And we can also share the data, which is good for us because reproducibility should be simpler, but that's not always the case, as you've heard already. And based on these different types of documentation, we can talk about different types of reproducibility experiments. Okay, it's the description. You just read the paper, you implement everything yourself, you do everything by yourself, you see how they do it, but you do it your own implementation of that. And And then you have a R1 description type of experiment. And if you have the code as well, but you don't have access to the data, well, then you have an R2 code reproducibility type of experiment. If you have access to the data, but not the code, well, then you have an R3 data reproducible experiment. And if you have access to everything, then it's an R4 experiment reproducibility type of experiment. Okay, then we have sort of different dimension, different sort of values along the one dimension that describes the type of the experiment. But then we have the degree, and the degree is related to the results. And as I said, with machine learning experiments and computer science experiments, we can actually get the exact same result every time. So if I run my code and it's simple enough, and the algorithm is simple enough, I can get the same outcome every time. I can get the same label for a cat image or a dog image every time I run the code. The same image will always get the same label. Okay, and if I have exactly the same labels as you generated, then I can just copy your analysis and copy your interpretation, and that's all. I just say I get the exact same outcome as you got. I did reproduce it. It's outcome reproducible here. So exact same outcome. Okay, but this is not always the case. Some algorithms are not meant to produce the same outcome every time, and even though if it's produced for doing that, it might not even do that for many different reasons. Okay, so then we have analysis reproducible, and that's a different degree. So we can have the different outcome, but if you're doing the same analysis on it, and based on the same analysis of the different outcome, we interpret it in the same way, well, then we have basically reproduce it, different outcomes expected, but we do the same analysis, we draw the same conclusions from the interpretation, well, then we have an analysis reproducible experiment. Okay, very good. So then next degree here is interpretation reproducible, which means that I might have the different outcome, or I might have the same outcome, but I do a different analysis on it. So I use some different performance metrics, but or different tests or analysis all over, but still my interpretation of these outcomes I got and the analysis I got makes me draw the same conclusion as you did. Well, then I have an interpretation reproducible experiment. Okay, so now we have different degrees, but we can also analyze this scientific method here and look at all the parts here where you see I've explained what goes into the different parts here, the research protocol, the experiment, the analysis, and all this, and we can analyze them and look at which type of what are the sources of irreproducibility here. So we did a study here with some colleagues of mine at the San Diego Supercomputing Center, where we sort of have a taxonomy here of sources of irreproducibility, and we relate them to the study design, we relate them to the algorithms, to the implementation of the algorithms and the experiments, which hardware we're running on, and then the data, the observations that we do. We have some related to the way we do our evaluation, and we have some related to the documentation. And there are all in all, maybe not here, but total in the paper is like over 40 of these. So I'm not going into them, but for the study design, it's basically which choice of baselines do you do. These are sources of reproducibility for machine learning, specific for machine learning, this taxonomy. So that you need to keep that in mind. So you can do sort of when you design the experiment, which baseline you use for comparing your experiment might affect the conclusion that you draw and in the interpretation. Okay, and same for algorithms. It might be a stochastic algorithms. You might need to do hyperparameter search, and all of this can affect the conclusions do you draw. Same with implementation. Are you running it on different initialization seed for your random functions might affect the outcome of your results, which again might change the whole interpretation. And there are lots of studies explaining exactly that. Data bias is a huge thing. So do you sample from the world, but does your data reflect the actual world? So if it doesn't, well, then you might draw false conclusions about the world because the data that you have does not represent the world. You might have a data leakage, as Sayash and Arvind has written a lot about, very nice paper. And you can have many factors regarding to how you evaluate your experiment and how you document it. Do you share everything, code and data? Do you document the workflows exactly? It's a huge thing in general science. Do you explain exactly what you did? Because if you change the sequence of the tasks you're doing to conduct your experiments, you might get a different result. Okay, so these are the sources of irreproducibility. And I said this definition should be operational and you should be able to use it. And I'm going to show you how you can use it. For one experiment here, the same that I presented for her, you have the code, everything as code. You run it on your own hardware and ancillary software, and you produce some outcomes. So, and if you get the same outcome, you can classify your experiment as an OR4. So it's outcome reproducible after executing the exact same experiment, same outcome. Only difference here, sources of variability, is the hardware and software ancillary software you're using. And then if you only read from the paper and you write your own code, get your own data, run on your own hardware and ancillary software, and you still reproduce results, you have an interpretation reproducible after own implementation, which you can sort of categorize as IR1 reproducibility. So now we can talk about, oh, I ran this type of reproducibility experiment and I reproduced your results. That is a value, I think. So all in all, I think in conclusion, this definition is quite simple, but it has some depth. It is defined in relation to the scientific method, which reproducibility is so nicely tied to, and it's operationalizable. So we can actually use it when talking about experiments. So I list here some research, done some research on this, finally, this is the page from AI Magazine in 2019, where I had a paper called Standing on the Feet of Giants, and I have to say I love the art. Thanks a bunch.
Thanks so much, Odd-Erik. Okay, so that concludes the presentations for this part of the session. Before we move into a discussion with audience questions, we'll take a 5-minute break.
I just wanted to mention, folks, feel free to continue typing your questions into the chat. Even if Priyanka is not able to get to them during the Q&A, we're going to email all the questions to the speakers after the workshop. And if they have time to answer them, we're going to put up those responses on the workshop website. We'll be back at 11:20. Is that right? Thank you.
Hi, everyone. Welcome back. I think we're going to begin with the panel discussion and Q&A. So are our speakers back with us?
Yes, I'm here.
Okay, great. And I think we might be waiting on Mike. We can give him another 20 seconds or so. Okay, well, maybe just to keep things moving, if you both would be okay with it, maybe we can just get started. And then when Mike comes, we can ask him to answer some of the questions we covered. Okay, great. So just to begin, I'll ask a couple of questions and then we'll get right into audience questions. And so my first question for both of you is to describe a little bit more about your journey into researching reproducibility topics in ML-based science, and how did you first become interested in this area? I know, Jill, you touched on this a bit in your talk, but if you could tell us a little bit more about that story.
Yes,
Sure.
absolutely. Oh, sorry. Yeah.
All right. Yes. So indeed, it was rather by coincidence, I would say. It was never a predefined goal to look into reproducibility, but it was rather in the context of this project that we found that these scores were, yes, an entire ballpark away from what we were achieving. And so when then investigating deeper into it, we found these mistakes. And from that point onwards, reproducibility has always actually sparked my interest as a topic.
Thanks. Eric, would you like to take this question as well?
Yes, absolutely. Now, of course, I said I was attending this keynote at the International Conference on Case-Based Reasoning from Yolanda Gill, and it's very interesting. After the talk, two researchers went to her directly, and we talked about the reproducibility. It was David Aha and I, and we immediately thought that, oh, we have to try to help our community, the case-based reasoning community, to do better, and we looked into how to improve our processes and so on. And we presented it next conference. No one's really interested, because everyone understood that this would require more of them to publish at ICCBR, which takes enough time. We don't have enough time to do research really well. So I thought I had to push elsewhere.
Yeah, sounds good. Mike, the question that we're talking about right now is just to briefly describe your journey into researching reproducibility topics in ML-based science, and how did you first become interested in this area?
Yeah, so I started in like mathematical modeling of images, and then started to move into using machine learning. But once I started to get in there, I really started to hate what was existing in the field already. There was so many issues with reproducibility of codes that I was finding that just didn't work or didn't generalize or were just hopeless. And so I really got exposed to this when we started the COVID research. That was the prime time when I'd never had that much exposure to so many code bases all at the same time, and so many papers discussing the same type of models. And we had massive issues with reproducibility of just trying to get some of them to work on basic data. And then started to go down more and more of the rabbit hole into clinical data of where else is machine learning used or going to be used, and what are the issues. And it felt more like we had to kind of break the system to make it, to start to rebuild it again. So before we could do any COVID modeling, we had to figure out where the problems actually lay, and then we could start doing it and really start thinking about how should our code base be constructed. And the same for, say, the missing data work was exactly the same issue, that so much of it was flawed. Where do you start without actually just pivoting and starting again, but on a new set of rules?
I see. Okay, I'll ask one more question, then we'll switch to audience. And this is for all the panelists. what do you see as some of the primary challenges or barriers for avoiding common failure modes in reproducibility failure modes in ML-based science? And maybe the order we can go in is, we can go opposite of speaker order. So we can start with Eric, then go to Mike, and then Jill.
So first of all, what we do, machine learning is so complex. So the algorithms in complex, that often the design of the experiments is so complex, and also computers are complex, and we run our experiments on computers, and all this complexity means that it's really hard to find what is causing the results. That is sort of, and that is why it's good that we focus on ML-based science here, because we need to explain all of this complexity, and it's not that easy to just run an experiment and look at results and be happy, because software bugs could lead you to a different result, but you will never know that because you expect that the software that you got from someone else worked, but it might not work.
Could I just check what the question was around? Is it why the failure modes are caused, or what failure modes are most common? I was trying to...
Yeah, the question was just around like primary challenges or barriers for avoiding common failure modes, reproducibility failure modes in ML-based science.
I think significant training gaps and differences between groups. There's a complete wild west of techniques that you want to follow. Like, you pick your favorite way of designing a model and someone has followed that before. There's not one concrete way that every group follows or that every researcher thinks about following. And I think everyone kind of knows that that's wrong. There's an acceptance in the community that something is strange. The pressure to publish is huge, and that's causing this problem of, I feel like, you know, I'm spending 6 months on something and it went nowhere. Now I feel stupid. The pressure is, how do I kind of turn that on its head or try and get a positive result out of this? Or is it better to spend 2 years designing something that works perfectly? But you have to have like the belief of your research group and your PIs and everyone around you to let you have that freedom to work for so long on just one problem.
And then from my side, yeah, especially within the medical domain, it is often hard to reproduce studies because the data is mostly very sensitive, especially here in Europe with the GDPR, the recent GDPR and so on. It becomes very difficult to really reproduce stuff. And on the other hand, code is often not made available as well. And so then you need to go based on the description within a paper. And then if you obtain a result that is significantly different than the one in the paper, you're never sure that it's either you who made the mistake in your own implementation or whether the original authors actually made that mistake.
I see. Okay, so next I'll ask a couple of questions that came in for individual speakers during their presentations. And so Jill, there was one question in the chat for you, and I'll just read it. A couple of people were interested in this question as well. Isn't there a potential data leakage problem when extracting features before splitting into train and test sets too? How did you avoid that? And another person chimed in and said that it seems like the features were pre-selected and provided with the data set, so it depends on how they were selected or computed.
Yeah, okay. So indeed, there is potential data leakage when calculating features, but maybe first, before we go into that deeper, well, we should make a distinction between, well, it's probably not the most correct terms for it, but basically supervised and unsupervised features. So if you're not using any label information to calculate your feature, a very trivial example might be you take the second power of a certain number. Well, that doesn't use label information. So that is always safe to use. You can reapply these functions to both your training and your testing data. But there are many features out there actually that, for example, well, it's not really a feature, but the oversampling procedure uses label information. And to give another example, there's a technique called, for example, target encoding, in which they process categorical information by filling it in with the mean or the mode for a certain category. And of course, that's where label leakage can occur as well. So when you're calculating these types of features, well, it's very important to be wary of this data leakage and make sure that you never use label information from your test set. A good rule of thumb is to always try to think about how this model would work in production. So if a new signal and new data sample comes in, can you calculate all these features without knowing the label of that sample, and really make that exercise in your mind? And I think that often helps, for myself at least, to avoid this kind of leakage.
Okay, we also have a specific question for Eric. And the participant says there's some evidence that science is getting harder to read, and they cite a 2017 paper by Ball in Nature. They say, do you see this growing inaccessibility of the narrative to be an impediment to reproducibility? And if so, how would you go about fixing this?
Oh, I think you have to repeat that. It was, okay, once more.
Sure thing. So the participant says there's some evidence that science is getting harder to read. Do you see this growing inaccessibility of the narrative to be an impediment to reproducibility? And if so, how would you go about fixing this?
Yes, of course. It is, so science is becoming more and more complex. We build it on top of very complex machines, most of this, and both in collecting data and in running experiments. And of course, we as scientists, we try to explain what we did as simple as possible. But we cannot explain everything. It is not possible. And the more complex our research is, the harder, of course, it is to explain. So, and often, as I understand my research completely, or at least I think I do, I might miss something some things, keywords that are so important for you to understand it, but I don't see that this is the keyword. So yes, I totally agree that this is a problem, and as much as possible, this means that we need to be more open, more transparent. Articles might be looked at as a way of promoting your research, and that sort of the full research protocol is shared someplace else where all the details are. We do this in machine learning. It's the opening code and data happens more and more, and we have a larger focus on that. So I think this is the way to go, more transparency, because we're not able to capture everything in the document itself.
Yeah, that transitions really well into one of the audience questions. By the way, there's some really fantastic questions in the chat. And even if we don't get to all of them, like Arvind said, we will be emailing them to our speakers and hopefully get you some answers. So one participant is curious to hear the presenter's thoughts on setting up a dedicated, independent, like agency or office of transparency, reproducible research before funding beyond a specific threshold is granted. And so they like, as examples, they say like an independent agency like NSF or NIH, DARPA, UKRI, or NHS offices. So if the panelists want to speak a little bit on that, and maybe the order can be, Mike, we haven't heard from you in a while. So if you have thoughts on this, maybe we can begin with you.
I definitely think there should be some check and balance, some reward structure for people that do really good research but get negative results, because that doesn't exist at the moment. And a way of acknowledging that some research is done and published and gets great acclaim but is non-reproducible. I don't know how, it's way above my level at the moment to figure out, like, I don't know what that would be and whether setting up independent agencies would be a lot of bureaucracy. I can only work on it at a base level and say, well, my PhD students have to do stuff in this way, and we enforce that they develop models in a careful, reproducible way and test every small component as we go, and the share code bases and really enforce that. And that as we develop models, checklists are used in the development of that. So also journals enforcing checklists at the time when you publish is incredibly important, because it will start people seeping into their knowledge that you should use them whilst you develop these things, because you'll start to realize that if you write your paper and submit it and then they ask for a checklist and you've not done it, you then have to redo so much of your research. Whereas if you'd use the checklist as you go along, you'd have never got that point of, hooray, I'm finished. And then you realize, oh no, I've got to go back again. So I wonder whether it's more like that, that at a lot of levels, we need this to seep in, that everyone with PhD students should enforce this. Everyone that's supervising anyone at any level needs to enforce it, and journals as well. And then we stop it at, we kind of fix it at both ends of the pipeline.
Yeah, great. I don't know if Jill or Odd-Erik, if you'd like to also take this question.
Yeah, so indeed, I think responsibility for reproducibility can be put at many places. So first of all, the authors are quite responsible, but definitely the journal on its own is responsible as well. And I can understand that by letting this being performed by a third party, that could potentially be increasing trust. But on the other hand, the public themselves can kind of check how well a journal, for instance, puts effort into these reproducibility aspects. So yeah, to say that a third-party agency would really be needed, I mean, it would be ideal to have as many efforts as possible, but I think a first effort should be taken by the journals as well, and yeah, especially the authors.
Yeah, so I think first of all, it's important to understand that science progresses through failures and errors. So there needs, so I don't think we can or should strive towards removing all false results in publications or at all. So okay, but we can do better. Certainly, according to Ioannidis in his 2005 paper, why most research findings are false, 50 to 70% of all research findings are false, and that is too much, of course. So we have to do something, and I think that the problem here is that, so we as researchers, we have different incentives. We need to publish, and that we might need to skip. But then, of course, there are others, funders. They could say, yeah, in order to get our money, you need to do this. Open data or open code, for instance. You should do, we require you to do some things that will help improve transparency. And then, of course, journals could also say, yeah, we need you to do this. You need to go through this, you need to share, you need to do certain things. And of course, we could hire people based on how good research they do. So are they following good practices? Are they opening up? Are they doing good methodologies? Not only whether they are publishing at the top venues. So those are important things. Institutions who hire should think about this. But then science, and this is the problem with publication bias. Science have this problem that more positive results are accepted than negative results. Okay, so if you have negative results, it's really hard to publish. And even if you reproduce something and you get negative results and you say, but this is significant, then the journal will say, yeah, but you're not doing new research, and we're just interested in novel research. Okay, so we need this feedback loop. So we did this, it doesn't work. I don't understand why. So I think, and this is something we're working with on the Journal of AI Research, JAIR, is having this feedback loop. So we publish something in this journal, but feedback loop, someone else tried to do it. Were they able to? Okay, that is closing this feedback loop. And I think it can be done. We have the internet and everything. It should be easy to close this feedback loop when we're not working on paper. So yes.
Great. Okay, so I think we have time for just one last question, very brief answers, unfortunately. But because this panel is on diagnosing these issues, I think these questions are quite related. So one person asks, should the number of trial runs also be published as part of ML studies? And so maybe if you could discuss what you think would be important to include in studies so that reproducibility efforts can be made possible. And then another participant asked, when you analyze published papers regarding reproducibility or leakage, do you contact the authors first asking for code data? So basically, like, what information do you need? And yeah, please, sorry.
Okay, so in my case, indeed, to answer perhaps the second part of the question, I indeed contacted each of the authors, but never got any reply in quite an amount of weeks. So that's why I decided to implement it on my own. And then with regards to indeed the number of trial runs, it's definitely a fact that you can overfit on your cross-validation results as well. If you throw enough stuff to the wall, something will stick. So indeed, it would be ideal if there are just no test labels provided in the data as well. So that way it becomes a bit more difficult to kind of overfit on the specific cross-validation seed you are using. But indeed, I think it would already be a good step forward to report the number of trial runs of how many things you've tried in a paper as well. Yes.
Yes, for the last part of the question, yes, runs, all the top AI conferences now, machine learning AI conferences, they require you to say how many runs you did and provide the sort of the central tendency of the result and also the variation. So mean and standard deviation to your results to see how it varied. Because the algorithms are stochastic, and even there are stochasticity variability related to the random seeds and setup of the experiment and all these strange things. So you need to understand how much does the result vary. And some of the studies that are published show you could have huge changes in the performance based on random seed. For some, it could be like 100% change in the results. It varies quite a lot, and so we need to understand this, how where you're just lucky with the random seed data and the setting of the machine learning algorithm for this run. Absolutely.
Yeah, and I think that's all correct. Like the idea that you don't say how many experiments you ran or how many times you repeated the analysis just feels like you're hiding something from the audience in a way. Like, but again, there is absolutely no motivation for you doing it unless you're forced to do it. Like, humans are human. If I did 2 runs and one of them's great and one of them's rubbish, why would I report the rubbish one if I'm trying to get into the best journal? And that's the problem. Like, human nature will always come into this, that we need to, it's so hard to tackle that component, but insisting like you do 5, 10, 15 runs of a full training cycle, you know, to get some statistical significance out for the quality of your results is not is a completely reasonable thing that we don't see very often.
Yeah, I just wanted to add that one of the problems that you're talking about, the publication bias, could be solved by accepting registered reports. That is sort of, this is, you describe the study you want to run and you send it to the top journal that you want to send it to, and they say, yes, this is a really interesting experiment. Absolutely, method looks good, evaluation looks good. We are interested in understanding where this lands, whether it's a positive or a negative result. And then you get acceptance. So we remove the incentive here to getting positive results or very exciting results or surprising results. We say that this is good methodology research.
And yeah, and I just have to say for systematic reviews, you already have this Prospero system that we used for, you register the question you're asking in your review along with exactly how you're going to do it, so you can't bias yourself. And then when you publish the review, you say exactly what study number you had so that people can check that you didn't change your conclusions or change your methodology because you were tempted to go in a particular direction suddenly. And it really holds you to account along the way, that we were like checking, have we deviated from what we said we were going to do? And I love that idea with study plans, that they should be registered, because then you even if you get a negative result, you've assessed it in the best possible way from the start. Or you don't do the experiments at all because there's no power in them.
Thank you all so much. I think that's going to have to conclude this session, but thanks so much for your presentations, and thank you so much to the audience members for your questions. We will do our best to send them to the panelists. And with that, I will pass it back to Arvind.
All right, thank you, everyone. I learned a lot from that session. I hope you did too. We have a 25-minute break now. I should say that because we couldn't make this workshop as interactive as we had originally hoped, for the Zoom participants, we've actually added breakout rooms during this 25-minute break, where if you want, you can go and share your knowledge and experiences with each other. It's totally optional. The rooms are not going to be recorded or live streamed. I hope you can see the breakout rooms in the breakout tab in your Zoom screen. If you scroll to the bottom, you will see 5 rooms, and you're welcome to jump into any of them, hop between rooms, however you like, and the rooms will automatically close when it's time for the next session. That'll be at 12:10 Eastern Time, 10 minutes past the hour. We looked at the disciplinary topics in which we had the most interest, and we created rooms for those if you want to have those discussions within your communities, or you're welcome to join a random room if you want to meet a random group of other people and share your experiences. And on the slide here, you'll see, especially for the disciplinary rooms, a couple of questions that can perhaps guide your conversation just as an icebreaker. You don't have to stick to those. I think the Zoom rooms have a cap of participants so that it doesn't get too big. You can actually have a conversation. And if you want to create a new room for some other discipline or theme, just let us know in the chat. We're happy to do that. Okay, yeah, I hope that was clear. Feel free to either take a break or enjoy the breakout rooms, and I'll see you back here in 25 minutes.
All right. Hello, everyone, and welcome back to session 2 in our workshop on the reproducibility crisis in ML-based science. I think people are still trickling back in, so we'll give them until the end of the minute, and we can start the session at 12:10 p.m. All right. It is a pleasure to welcome all of you to this session. I think we have around 200 people consistently in the Zoom link and around 150 more on the YouTube live stream. So it's great that so many of you have showed up. First of all, thank you so much. Our next panel has 4 speakers. I'll briefly mention their names and titles, and we'll include their bios in the chat as they begin their talks. So our first speaker for today's for the second panel today is Professor Michael Loans, who is an associate professor in the School of Mathematical and Computer Sciences at Heriot-Watt University. Our second speaker would be Deb Raji, who's a PhD student at UC Berkeley. Our third speaker is Dr. Momin Malik, who's the senior data science analyst at Mayo Clinic. And our fourth and final speaker for the second session is Professor Marta Serra Garcia, who is the associate professor of economics and strategy at UC San Diego. So without further ado, over to our first speaker, Professor Michael Loans.
Okay, so hopefully you can see that now. Right, so yeah, so my name is Michael. I'm coming to you from Scotland today. If you hear weird noises, it's because it keeps chucking it down outside, which is kind of normal for Scotland. But there you go. So thank you to Sayesh and Arvin for inviting me to speak at this great workshop. And my talk is motivated by a paper that I wrote last year called "How to Avoid Machine Learning Pitfalls." And sorry, just something onto my screen. Okay, How to Avoid Machine Learning Pitfalls, a guide for academic researchers. If you want to look at the paper, there's a link on the workshop's reading list, or you can scan the QR code, which kind of appears around the place. And as you can probably guess from the title, this paper discusses the kind of things that can go wrong in machine learning, and it aims to provide some guidance on how to avoid these pitfalls. And it's very much targeted at people who are relatively new to machine learning. I'm not going to take you through all the stuff in the paper because there's not time, but instead I'm going to focus more on the reason why I wrote this paper in the first place, which is basically that a lot of the mistakes we see in machine learning are caused by inexperience. And part of the reason for this is that novice machine learning practitioners often struggle to understand the more established machine learning literature. So my aim was to write a more plain English guide for people who are new to the field. So I'm going to start with a very brief overview of the paper, and then I'm going to spend some time just illustrating some of the things that can go wrong, particularly when an inexperienced practitioner first starts out in machine learning, really just to show how easy it is to fall into these pitfalls. And after that, I'm going to talk a bit about some of the things we might go about changing in education and machine learning tools in order to address the underlying issues of why people are making these kind of mistakes. So this is the paper's archive page. I chose not to go to the traditional publication route for this because I want to be able to update it periodically, both as machine learning methods change, but also as my own understanding of these things changes. It's written in relatively plain English, which I hope makes it accessible to a broad spectrum of people, and it's concise. You can read it in probably less than half an hour if you really go for it. But it also gives lots of references to kind of in-depth sources. And I very much welcome feedback on this, and any suggestions you send me will hopefully make into future iterations of this guide. Here's the contents page. It basically goes through pitfalls that occur in each of the main stages of the ML pipeline. So that is before you build models, whilst building models, whilst evaluating models, whilst comparing models, and whilst reporting results. And I say it focuses particularly on the evaluation and comparison parts, because these things are particularly important for academic researchers, and they're the kind of mistakes I often see when I read academic papers. Though actually most of this stuff is pretty relevant to non-academics too. Okay, but so what does all this have to do with reproducibility? Well, I guess my view is that the failure to reproduce results is often due to a failure of understanding when people produce results in the first place. So that is, people get things wrong because they don't know it's wrong. And I'd argue that applied machine learning is essentially a new field. So it's been around quite a long time, of course, but it's only recently that it's become a mainstream activity and that lots of people have entered the field. And so the majority of people working in the machine learning field at the moment are relative novices. So they get things wrong because they don't know it's wrong, because they don't have much experience. And it's not just experience that's the issue, it's also education. So many people who work in applied machine learning don't have a formal background in machine learning in terms of having done a degree or something. And even those who have done a background, who have a degree in computer science, they may have only studied maybe 1 or 2 courses on applied machine learning during their degree, and that may not have involved actual application to real problems where they kind of come across all the things that go wrong. And in fact, many of the people who teach machine learning are themselves pretty new to the field, because there just aren't that many experienced practitioners around, so not enough people to teach it. So inexperience and a lack of knowledge are both important problems in machine learning, and I think they are, at least in part, driving this reproducibility crisis. And I guess my paper is intended to help with this, at least a bit, by making machine learning knowledge more accessible. Because although there's a lot of information out there on how to do applied machine learning properly, it is often in places where people new to the field won't be able to access or understand what's been said. So they kind of have to fall back on more informal sources of knowledge, such as blogs and tutorials and YouTube videos. And many of these resources don't really say much, if anything, about what can go wrong when you start applying these techniques in practice. And the underlying problem is that there is a lot that can go wrong when inexperienced machine learning practitioners start to work with data and they start building and evaluating machine learning models. And just to emphasize this, I want to take you through a few common examples of the kind of things that can go wrong. So often when doing machine learning, we start with a single data set and we load it into our preferred machine learning framework, as this slide kind of shows. And then once we've loaded in our data, our impulse is to play around with it. And frankly, there's nothing to stop us from just playing around with it. So we dig into it, we take a closer look at it, we do some exploratory analysis, we can visualize bits of it, we can work out ranges and distributions and summary statistics. And generally speaking, this is a good thing to do, since it helps us to understand what we're modeling and see whether there are any issues with the data, because the last thing we want to have is a kind of garbage in, garbage out kind of scenario. And certainly most guides to machine learning will encourage you to look at your data. But what's perhaps not obvious to novice machine learning practitioners is that we should never look at all our data at this stage, because we have to bear in mind that we're going to use some of this data to evaluate our model, and that this test data should have no role whatsoever within the training process. And if we let the test data affect training, even in seemingly innocuous ways, like, say, taking into account the range of a particular feature across the whole data set, then we're going to suffer from data leakage, which in this case is something that occurs when knowledge of the test set leaks into the training process. And this is inevitably going to be the case, even if we just look at all our data, since our understanding of what the data looks like can affect how we approach modeling it and how we set up our models. And this influence on our modeling can easily happen subconsciously, especially if we spend ages just sitting and playing around with our data. And this is important because, as people have already said today, data leakage is one of the main reasons why machine learning models fail to work as well as expected when they're deployed in practice. Because the test set was involved in training, it's no longer an independent measure of how well a model performs, because it's basically been used in both training and testing. And then when data leakage like this happens, the performance metrics you get from the machine learning study are likely to overestimate the model's real-world performance. And I guess the point I'm trying to make is that really simple things like not looking at all your data are not necessarily obvious to someone who's new to machine learning. Though having said that, looking at data is probably going to be a minor form of data leakage in most cases, but there are plenty of more serious examples out there, and these are also quite common. And one that I often see is when people apply dimensionality reduction or feature selection before they split the data into train and test sets. So in this slide, someone's using PCA, principal component analysis, to reduce the number of features. And then they're splitting this reduced data into train and test sets, and then using the train set to build a model and the test set to test it. But because the test data was still in the data set when PCI was applied, the weightings of the principal components will inevitably capture information about the data distribution in the test set, as well as the train set. So this will influence how the model is built, and it'll make it more likely it'll overfit statistical irregularities across the whole data set, including the test set. And it could allow some pretty deep knowledge of the test set to leak into training, and so could really affect the independence of the test set as a measure of performance. But it's certainly not just PCA this happens with. I see it a lot in feature engineering more generally, and it's also a problem in hyperparameter optimization. So that is people making modeling choices like the number of layers in a neural network or the number of trees in a random forest. And they do this based on the performance on the entire data set rather than just the train set. And in my experience, this is particularly common when people are doing cross-validation. So I often see people performing the feature selection or hyperparameter optimization step on the entire data set before they do cross-validation. And I can understand why this happens, because to a novice, it's probably not at all obvious how to combine something relatively complex like hyperparameter optimization with something else that's relatively complex like cross-validation. And they simply may not be aware of the idea of using something like nested cross-validation, which would be a much better way of doing it in this case. So you may think that I'm banging on quite a bit about data leakage, but data leakage is an important problem in the reproducibility of machine learning results. And I think it's interesting also because it's one of the easiest mistakes to make when you're new to machine learning. So I want to talk about one more occurrence of data leakage, and one that's probably very common and can have a big impact on reproducibility. But it's also quite hard to spot because it's something that's really documented in someone's machine learning scripts or workflow. So let's assume we've trained a model, we've tested it using the test set, and we have a reliable measure of its performance on the test set. So far, so good. But then we decide our test performance isn't looking great. So we tweak the model in some way. Perhaps we change a parameter. Perhaps we change from a neural network to a support vector machine. And then we evaluate it again on the test set to see whether it helped. And we basically keep doing this until we get the kind of performance we're hoping or expecting to get on the test set. And I'd say this is a very common thing to do. I'm pretty sure I did it when I first started working in machine learning many years ago. But it's also a classic case of information leaking from the test set into the training process, because it basically involves using the test set to guide the training process. So if you're using the test set to decide which models to keep and investigate further, then you're implicitly using the test set to train the model. And the more we do this, the more our model will overfit the test set, and the less reliable the test set performance will become as a measure of the model's generality. And even if we're not explicitly conveying any information between these iterations, the chance of getting lucky and the model just happening to do well on the test set also increases each time we evaluate a new model on the test set. So by doing this kind of thing, you can really overestimate model performance. And you can even do this on purpose. And there's nothing really stopping people from doing this within current machine learning frameworks. So there's nothing to stop us from loading data and then just messing around with it, training models, seeing what happens, and informally converging on a particular modeling approach, which you might then document formally. But then once this approach is being documented, all of these previous experiments don't get reflected in this. And so you can easily overfit the test set without anybody really realizing how you've achieved that. And interestingly, much the same process goes on each time someone uses a test set from a community benchmark. So each study that uses the same data set can learn from the test set performance in previous studies. Plus the chance of overfitting the test set by chance also increases the more times people use it. Which makes me and many other people wonder how much the progress on common benchmarks is due to overfitting rather than actual progress in model development. Especially when you consider that the performance being achieved on many of these benchmarks is starting to kind of reach maximum. So for instance, CIFAR 10 shown on this slide is currently at 99.5% accuracy, and it's known that at least 0.5% of the samples are mislabeled, so it really couldn't do any better than this. Is this performance due to the greatness of the model, or is it at least partially due to overfitting? It can be really hard to tell. So data leakage is a nice example of what can go wrong in machine learning and how easy it is for it to occur. But it's certainly not the only cause of failure to reproduce machine learning models. And there are potential pitfalls throughout the machine learning pipeline, many of which I talk about in the paper. But as one more illustration, I'm going to fast forward to pretty much the end of the machine learning pipeline, when there's often a need to rigorously compare different approaches to solving a particular problem. And one of the pitfalls that crops up here is the choice of statistical tests. So typically you'd have a bunch of results from a bunch of different models, and you want to work out which model works best for your particular problem. And in theory, you can use statistical tests to help you do this. And there are a whole host of tests that you could use for this. But actually picking the right test can be a pretty hard problem in itself, because most machine learning practitioners are not statisticians. We may be aware of a bunch of tests, but we probably only have a limited understanding of how these tests work, what their limitations are, and what assumptions need to be met in order for us to use them. And if we use the wrong test, then our conclusions may not be valid. And I suspect there are probably thousands of papers out there where people haven't used the right tests. And actually, even statisticians often disagree on what are the correct tests to use for a particular scenario. So frankly, it's no surprise that we get it wrong. So I included this example to illustrate that it's not just novices who can get trapped in machine learning pitfalls. There are things out there that can confuse and confound even really experienced practitioners. Okay, so finally, I want to say something about solutions. So how can we improve the practice of machine learning so that people make less mistakes and therefore don't contribute to the reproducibility crisis? So first of all, the guide I wrote is supposed to be a small contribution towards this kind of thing by making people who are new to machine learning research more aware of what can go wrong and how they can fix it. But that's really just a stopgap solution, and I don't pretend it's either comprehensive or appropriate for everyone. So certainly I think there's a need to improve machine learning education more generally, since I think a big part of the problem is that many people currently get a quite shallow education in machine learning and data science before they go on to start practicing it. But how might we improve this situation? Well, I think accreditation is one possible route. We could develop a curricula that makes sure people are aware of what can go wrong in machine learning. And we could require that people do an accredited course before they're able to practice in critical areas, for example. And actually, this will bring machine learning into line with other scientific and engineering disciplines where accreditation and chartership and things like that are really important elements of assuring quality of the artifacts that are produced by these disciplines. And perhaps we should also stop thinking of applied machine learning as just an adjunct to a computer science degree, and instead teach it as a separate program or perhaps even a separate discipline. I think there's an argument for this because existing CS programs do tend to focus on training software engineers, not machine learning practitioners or data scientists. And if you want to teach applied machine learning well, perhaps you do need an entire degree program that focuses on this, potentially including depth in areas like statistics to help us with our stats tests, for example. So improving education is one way of potentially solving or at least reducing the reproducibility crisis.
Michael, just a heads up that we're at 20 minutes.
Okay, I'll be very quick. But I think another route worth exploring is better tool support. And I mentioned earlier that once you load some data into an ML framework, you can do pretty much whatever you like with it. Perhaps this shouldn't be the case. Perhaps we should expect tools to track our data usage and actively prevent us from doing things that allow data leakage. And the scope for tools to provide context-sensitive warning messages to the user and do things like guide us with the stats tests we use and help us interpret our conclusions. So I think there's a lot that could be done with tools to help as a kind of safety cushion to stop us making mistakes all the time. But those are just some thoughts I had. So let me conclude. Mistakes are easy to make in machine learning, especially for beginners, but also sometimes for experts. We need better ways of preventing mistakes, and these might include better guidance, better education, and better tools. Thank you. That's all I have to say for now.
Thank you so much, Michael, for the really insightful presentation. In my excitement for this panel, I completely forgot to introduce the theme at the beginning of it. The theme for this panel is fix, and we'll be focusing on the ways to ensure the validity of ML-based science by avoiding common pitfalls. Note that fixes are still a work in progress, so otherwise we wouldn't need this workshop at all. But as we saw in our first talk, we do still have a slight idea about the various areas for improvement. All right, with that, we're on to our next speaker, Deb Raji. Over to you, Deb.
Hi, yeah, thanks so much, Shash, for organizing this workshop and inviting me. I'm really happy to have heard all the amazing talks. So I'm here to talk about the sort of consequences of reproducibility issues in ML research and practice. So, as has been discussed thoroughly today, machine learning as a field is sort of going through a reproducibility crisis. And I think it's interesting how the challenges that the field and machine learning has had is now influencing the sciences. Actually, a lot of my experience has been looking at the consequences or looking at this reproducibility crisis within the machine learning research community, and then also looking at it not necessarily as it affects research in the sciences, but as it affects our understanding of downstream deployments. So an example of what this looks like, and this is a slide that my co-author Thomas Liao, who sort of led this project on meta evaluation of a meta review of evaluation failures across machine learning, where we looked at sort of a bunch of papers that re-examine or revisit the progress made in machine learning and demonstrate how some mistakes that are commonly made in the evaluation process of the machine learning development cycle lead to a misunderstanding of what it means to progress as a field. So as an example, here are sort of, the reported results of machine learning models on the movie lens data set. And you can see it looks like a lot of benchmark reports that we're familiar with seeing maybe for ImageNet, where it's like, we constantly see over time, the models are doing better on this benchmark, and it looks like the field is making a lot of progress. However, in this paper, this is Rendell et al. In 2019, they actually found that a lot of the the baseline implementations were incorrectly deployed. So they were just like incorrectly adjusted for all the hyperparameter and implementation tunings, but also the way the baselines were actually executed were incorrect, was incorrect. So when you actually compare the proper baselines with the even newest crop of algorithms, there hasn't been a lot of progress in the field on this problem. So this sort of is a good highlight of this recurring issue that we have in machine learning, where we struggle to understand progress, and it's a direct result of the reproducibility and evaluation issues that the field faces. And then sort of in my other work, or putting on my other hat, my more policy-oriented hat, a lot of the consequences of that misrepresentation of performance in the machine learning space also manifests in the systems that get deployed and actually affect people in the real world, that actually make their way out there. And here's just a sample of the headlines recently of all the ways in which these machine learning models have just fallen short. So in research, we struggle to measure progress, and in practice, we struggle to actually deploy systems that work as a result of this reproducibility crisis. So in both cases, we desperately need accountability. So I'm going to just start with a high-level overview of the machine learning research problems, just for those that are less familiar. So in our paper, and this is based off of a paper called Are We Learning Yet?, which is the meta review that I mentioned of evaluation failures. And this is work that was led by Thomas Liao and was also in collaboration with Totten and Ludwig Schmidt as well. So in that paper, we discussed sort of the idea of the benchmarking paradigm that's very prevalent in the evaluation schemes in machine learning, where the way that evaluation works in machine learning is that there's sort of this task universe where people think about, what they want the model to do and the objectives of the model, and they try to instantiate it with a data set and with a metric to represent progress on that task. So you might want to think of natural image classification as a task or as a goal that you'll have for a model, and people might instantiate it with the ImageNet data set and, a metric of top 1 accuracy. So we talk about that instantiation as the learning problem, and sort of these high level, more abstract goals as tasks. And, typically you would think that it's a very straightforward thing. You evaluate on a learning problem that should translate to progress on that real world problem. But it's actually a much more complicated process. And in this paper, we break down how evaluation and a sort of appropriate, realistic presentation of performance of these systems involves multiple steps to go from, a new algorithmic idea to actually demonstrating that this is a better implementation of the model than previous iterations, and that it actually relates to the real world problem in a meaningful way. And the way that we sort of split these issues as internal validity issues and external validity issues. And along this entire chain, there's a bunch of different hazards. There's all these different ways that these systems can fall short of, the standard of what it would actually require to do well and to properly represent performance of these systems. So, when we talk about internal validity issues, we're talking about issues that arise within the context of a single learning problem. And a lot of these, if you take a learning problem and you add a leaderboard and you have people focusing on it, then it pretty much becomes a benchmark. So we can talk about it as a benchmark for the purpose of this discussion. But it's anything that has to do with sort of the quality of the benchmark itself, or the learning problem itself. So these are like label errors, which have been found to be prevalent in a lot of popular benchmark data sets, literally images of a cat labeled as a dog, and that confusing the model or leading to misleading results. A lot of the issues are around inadequate baselines. So not comparing, machine learning model performance to maybe something very simple. So we've now found out that, decision trees are really good on tabular data, and they're much better than deep learning. And even though models have been comparing themselves on their performance in the deep learning space, they hadn't actually compared it to these sort of simpler implementations that end up outperforming all the deep learning implementations. And this also happened with reinforcement learning as well, where random search works, just as well, if not competitively, with a lot of reinforcement learning implementation. So looking at the sort of simplest baseline and making that comparison is enough to reveal all the ways in which we misrepresent performance in this space. Another simple example was, revisiting human baselines. The human baseline for ImageNet, which is a very popular computer vision data set, for a long time was just, the results of a single grad student, Audrey Kapathi, who was, working on that project at the time. And his labels just ended up becoming the human baseline for this data set that's been used now by, thousands and thousands of people. So internal validity issues are just really questioning the quality of that learning problem and that instantiation of the benchmark. External validity issues are kind of a different story. So these are looking at how well the progress on a particular learning problem transfers to other learning problems for a similar or related task. So if you have the goal of being able to predict, lung cancer based off of medical images, it technically shouldn't matter which data set you're using in order to evaluate performance on that task. You should be performing similarly on these different data sets. And most importantly, if you demonstrate an improvement over a baseline on one data set, that improvement should be consistent on another data set. But that's not what we see. And there's a couple of reasons for that. So one reason for that is this issue of hidden stratification, which is really this idea of, sometimes the model is not actually using the key important features of the image in order to make its prediction. It's looking at, in this case, for this study, they found that it was looking at other artifacts in the image, maybe other labels that were sort of auxiliary to the image, indicating what kind of machine was being used for the X-ray. And that could misguide the model in ways that were not anticipated, but also makes it impossible for the model's progress on one data set to translate to progress on another data set. Another example of this is there was a team that took the ImageNet data set and they sort of recreated the data set. They followed the steps involved in developing the data set, and they said, let's just follow the exact same steps and come up with, another version of that exact same data set, and let's see if it translates across, two different versions of the same data set. And they found that the answer was no. So just the brittleness of these models to any minor shift in the distribution of the images results in sort of drastic drops in performance. And that's something to also keep in mind as we reflect on the sort of external validity of the results of these models and the kind of progress we're making as a field. And then the sort of final comment I'll make, and this is not from our paper, but this is another paper sort of on the benchmark lottery, where they talk about this idea that in machine learning, there are different data sets. There's actually quite a few benchmarks to choose from. And depending on which benchmark you choose, your model might win in one context and not the other, sort of giving the perception that your algorithm is better than another algorithm in one context, even though that might not be persistent as a result across, all the relevant contexts. And Henderson et al. Also does this really well in their paper, Deep Reinforcement Learning That Matters, where they talk about how, different reinforcement learning algorithms win in different deployment environments, where in some environments it looks like there's one algorithm that's the best algorithm that should be used by everybody, and then in other environments it's another algorithm. And in the papers for these different presenting these different algorithms, they sort of cherry pick which tasks that they demonstrate, and that ends up sort of distorting our understanding of which algorithms actually work best globally. So, aside from these problems in research and sort of the difficulties and consequences of these issues for, how we understand progress in the research space, there's also clear problems in machine learning practice to a lesser degree, but definitely sort of this increasing issue. And I think this meme sort of captures the nature of the challenge in practice, where what you end up is, following, what I had mentioned about how machine learning researchers often misrepresent their performance and their results. You end up with people misrepresenting or misunderstanding how well AI actually works in the real world. So you have people becoming really worried about AI and sort of having catastrophic scenarios in their mind about what these systems are going to do, when in reality, a lot of our images are mislabeled and the systems don't actually work very well. So this meme kind of captures a lot of that sentiment. And there's actually sort of an academic term for this this phenomenon, and it's called critihype, where pretty much even those, we expect that those promoting a certain technology will be optimistic about how well that system works. But critihype discusses how even those that are critical of that technology or that are meant to regulate that technology also at times, adopt a very optimistic perspective of how well these systems work. So they adopt these things called wishful worries, which are fears about, what the system will do, but they can only be realized if the system works or works too well. So it requires them sort of adopting the perspective that these systems operate as advertised. And in the machine learning space, where performance is often misrepresented, we are very, very sort of vulnerable to falling into discussions about these wishful worries. So an example of this functionality assumption, as we call it in the wild, is the New York City's bill to sort of require bias audits for AI type HR technology. And actually, I think Arvin actually mentions this in his speech about in his talk about snake oil, where although people are so focused on bias, the real issue with a lot of these AI hiring tools is that a lot of them, misrepresent what they're actually doing, or they have inputs that are completely invalid. So they use face data, or they use sort of these pseudoscientific personality tests to determine someone's hireability. And there's actually fundamental validity issues with these systems, independent of the bias question. So the bias question is almost, built off of the assumption that these systems work as expected or work in any meaningful capacity. So the functionality assumption sort of plays out with policymakers in this New York case. And in our paper, we kind of go through various different types of failures. And we also discuss how, different policies kind of reflect this functionality assumption, how people ignore these different types of failures and how that reflects on the policy outcomes in these different scenarios. So, this is supposed to be the section on fixes. I'm not sure how much time I actually have left, but I wanted to go over, what people are proposing as solutions in these spaces. So in the machine learning research space, a lot of the solutions has been very oriented around conferences and the operations of conferences. So thinking through, how can we actually set measures so that we can't publish research that has these reproducibility issues or these basic sort of evaluation failures. And, the ethics review process has been really critical for that. So technical reviewers can flag papers for academic integrity issues, and reproducibility is one of those concerns that they can flag. And then a bunch of ethical reviewers can come and review, if and make suggestions, and if the authors do not adequately address those concerns, then the paper isn't published. And over the years, there's sort of been this evolving conversation on that. Similarly, there's this move that was made since about 2019, 2018 to set up a bunch of reproducibility challenges and checklists for the machine learning community. And we actually have that as part of the paper submission process now at NERIP since 2021. This has been sort of the recent main sort of implementation strategy has been, okay, well, we want you to do certain things like share your data, share your code, make certain clear statements. So we're going to make that a requirement for submission. And we're going to have this checklist so you can check that you're doing all of these things before you publish, this work. And with the reproducibility challenge, it invited students to come in and try to reproduce some well-known machine learning results. And that was a very sort of enriching exercise for the community. Another sort of underestimated strategy, and it was actually recently highlighted in a Nature comment, is this idea of reanalysis studies, where I look at the same data set or I look at the same algorithm, but I'm just coming from a different perspective as a different team. And in the Nature sort of comment, I think they do a good job explaining all the different variations of how this can play out. But the simplest way is that I give everyone the same data set, and if you have 9 different teams analyze it, you end up with with sort of 9 slightly different variations on results. And that tells you something about just the quality of the results coming from each of these teams. And it's kind of an increasingly popular strategy for research accountability in the sciences. And in machine learning, what that looks like is that you have parts of the machine learning community going back to popular results and revisiting them and questioning them. So Dodge et al. Did a great job revisiting some results in the machine learning space and saying, well, what would it mean for us to evaluate the performance of these systems and make these comparisons with a fixed budget constraint? So I can't use a certain compute beyond this size. And what they found is that there's certain budget regimes where, it looks like, in this case, logistic regression works better than, convolutional neural nets. And then, at larger budget regimes, convolutional neural nets beats logistic regression. So maybe we should be reporting performance anchored to like a discussion about resources. So this was sort of an interesting trend that happened. I think it started around like 2018, 2019 with the reproducibility challenge of people just revisiting past results. There's a great paper called Implementation Matters in Deep Policy Gradients, and they find a kind of similar issue, but they actually identified that there's 2 reinforcement learning algorithms, one called PPO and the other one called TRPO, and they found that the progress demonstrated by TRPO could be completely attributed to code implementations in that code base for TRPO. So if you adjusted the code base for PPO to include all the tricks that they used for TRPO in the TRPO code base, then PPO ends up beating TRPO in many cases, and the progress was sort of an illusion. Similarly, Henderson et al., which I've mentioned multiple times now, they did a really thorough study where they found that different code implementations of the same algorithm will give you different results. And similarly, just using a different random seed for the same algorithm will give you different results. So different initializations of the same algorithm will give you different results. And so, they really pushed for sort of more standardized practices in the field and allowing for the community to release information so that people could actually examine and question these systems. And so similarly, we have sort of a set of quote unquote solutions in the machine learning space as well. I don't have a lot of time, so I won't really go as deeply into this, but one thing that has been arising as a strategy to sort of counteract the illusion of the fact that these systems work and the sort of confidence that policymakers have in these tools, in these systems and these AI tools is the use of audits. So audits are really evaluations with an expectation for accountability. So they're evaluations that are sort of integrated into accountability processes to re-examine these systems with the purpose of holding various stakeholders to account for the decisions that they made about that system. And you have internal and external auditors, those with a contractual relationship with the audit target versus those who are on the outside. And there's sort of privileges and advantages and disadvantages of both positions. One very focused on internal sort of accountability. So, an independent team that can kind of, interact with various other teams within the organization and interface with senior management to set up to compare the performance of the system to the expectations internally and perhaps externally as well. And the main strategy in the machine learning space for this has been documentation and documentation approaches. And there's also been sort of the implementation of integrating these documents into these bigger frameworks to come up with like an end-to-end approach for internal auditing. However, you can also kind of audit from the outside, and a very popular kind of version of this external audit is the gender shade study, where they found with commercial facial recognition products that these systems perform significantly worse for the darker female subgroup than for the lighter male subgroup. And this disparity was found by Joy Blamwini and Timnit Gebru, Joy Blamwini being an academic researcher that just investigated these systems from the outside. Similarly, there's been sort of this push for bug bounties. Twitter recently did one to analyze the bias of their crop algorithm, but pretty much this idea of incentivizing external actors to come and re-examine a system.
Deb, just a heads up that we're at time.
Okay, I will go super fast. I'm so sorry. Another thing that we can do is regulate these systems. So, have policymakers sort of think about functionality and performance and reproducibility in these questions as part of their regulatory regime. So we have other industries that have gone through sort of a similar reckoning. And we, as a result, especially in the US, have sort of a lot of legal infrastructure, tort law, consumer protection law, warranties, fraud law, that can actually serve as the basis for a lot of the potential ways that we can vet these systems before they enter the market or even after they're on the market. And with facial recognition, we saw that happen as well. A lot of the response to the gender shades audit and a lot of the citations and policy has been sort of these ordinances to restrict the use of the technology, before it can be examined for performance and for bias. So the regulatory approach is pretty popular. And then sort of finally, the last sort of approach that we could take on the practical side to minimize these deployments of systems that appear to work but don't quite actually work is just taking them out of circulation. So, Stanford attempted to use an algorithm to, predict sort of who deserved a vaccine and missed out on a lot of the younger but very much on the ground residents. And as a result of the sort of backlash that they got from that whole decision, they just ended up removing the algorithm and switching to a first come, first serve kind of policy. And there's a great quote about how nice it is to just remove the algorithm and approach things more straightforwardly when that algorithm, we're unsure about how well that algorithm is actually serving those that are impacted. And a similar thing happened with students that protested, the use of algorithms in determining their A-level results. And then, the same thing happened with facial recognition as well. After a lot of public pressure, a lot of companies pulled those products off of the market because of concerns of functionality, especially in the high stakes use of law enforcement. So, in conclusion, when a lot of these systems fail, real people get hurt. So these questions of reproducibility and performance and functionality are quite connected to a lot of the cases of those that are affected by how these questions translate in terms of policy design, in terms of actual products that end up being released. Thank you very much.
Thank you so much for that excellent presentation, Deb. I'm sure everyone would love to hear more from you in the panel as well. So participants, feel free to put any questions in the chat for Q&A, and I'll pick them up when we begin the panel. All right, next up, we have Dr. Momin Malik. Over to you, Momin.
Hi, everybody, welcome. I have way too many slides, and so I'm going to go fast from the beginning, but please, my slides are already uploaded, so you can go here and download them. And I'm going to try to cover a lot. Deb inspired me to also include a meme of my own background. That was my dissertation in one meme. I'm coming from a kind of diverse background, history of science, science studies, but then also machine learning statistics. So as an overview, I'll be covering methodological problems in which I think it'll tie to some of the earlier speakers, but also contextual points, which I think will tie to some of what Deb said, particularly towards the end. Currently, I am an AI ethicist, and ethics is a whole other concern that I'm not going to touch into, but I'm happy to discuss that later. So a lot of this is based around my preprint, A Hierarchy of Limitations in Machine Learning, where I try to position machine learning among all other possible methodological approaches. The point of that is that nothing is the best method. There's different cases where different things are appropriate. And we should consider that, including pointing to where qualitative research is appropriate. Going through a couple of these problems. So again, each branch has trade-offs and problems propagate downwards. Looking at the very first branch, we often assume that we can have a division of labor where we just work with the measurements that exist. But there's a whole process to that. And that's one way in which all models are wrong, all abstractions are not the thing themselves, and so we'll always flatten out some variability. Very old debate in social science, but pretty much unknown in machine learning. We can represent kind of constructs, the primitives of social science, hidden graphical models. They're often unobserved. And so even though we might make a model that kind of is this, there's really something going on behind the scenes. As an example of that, we take catness and we take human labels and patterns and pixels. Is this a cat or not? it's a false saber-toothed tiger. It looks kind of like a cat, but it's genetically, phylogenetically, cladistically not a cat. This, we wouldn't call it a picture of a cat unless we notice the hidden cat in it. So catness could be defined in different ways, and that's usually not something that people think about. The failure to replicate of the epic sepsis model is probably a matter of that. Of course, it wouldn't generalize if you define sepsis differently. If you refit the model on the different definition, on the audit definition, maybe it would generalize. So this is an example. Stats and ML versus maybe some other approaches which have their own limitations, summarize things with central tendencies. We can't do anything with an N of 1. Qualitative research can. Qualitative research can draw out more variability, more understanding, but statistics and machine learning require this kind of flattening of the world into comparable things. And this is, going on that other branch. I'll talk about that more later. Sampling frame is incredibly important, not something that people are trained in, but you can't ignore it. Xiaoli Meng has some nice work about this, historical precedents, survey sampling, and Cohen and Roots have a paper where they basically talk about how they were sampling on the dependent variable and using Twitter to classify political orientation. They only modeled those users who had a signal. When they went back and tried harder to extract a signal, performance dropped precipitously. So study design, we should have training in that, looking at sampling frame and using measurement models. Abby Jacobs and Hannah Wallach are trying to bring this a little bit into machine learning. Or maybe we should just give this to psychometricians, qualitative researchers, people who understand the kind of connection between constructs and measures. We avoid that at our own peril. Second problem, as a caveat, causality is hard, maybe too hard. There's nothing you can do that really ever guarantees causality. This book has a nice sort of summary of that. Causal inference can break down in really unexpected, spectacular ways, and this paper is a great example. ML, a good way to understand that compared to traditional statistics is splitting between explanatory and predictive. So when we define predictions as minimizing loss, the answer is that the correlation. Non-causal correlations will sometimes predict well, but they're fragile. And that's a theme we've seen again and again today, that machine learning can be fragile. If we defined kind of success in the presence of change, not that I advocate Milton Friedman's politics, but as one perspective, in Essays on Positive Economics, he writes that the purpose of positive economics should be prediction in the presence of change. That's not prediction in the machine learning sense, right? That's conditioned on changes. In that case, correlations wouldn't work, but how do you formalize change? What are all the possible distributions that could happen? That's kind of hard to do. And that's why we end up defaulting to correlations and loss functions. Gallat-Schmele has a nice paper about this. But of course, Leo Breiman talked about this in 2001. I use his diagrams as kind of a way to define machine learning as what it is, rather than what it aspires to be. I don't use the Mitchell 1997 definition. I base my definition on this. An instrumental use of correlations to try to mimic the outputs of a target system, rather than trying to understand causal relationships between inputs and outputs. This is what I communicate. I think it doesn't capture everything, but for people outside machine learning, this is the right framing for them. This is the right way to immediately connect to things that they're already know and are familiar with. Machine learning can go wrong in all the ways that correlations alone can go wrong. Machine learning can be unjust in all the ways that correlations alone can be unjust. Historical oppression causes certain empirical patterns. You can make money by optimizing to them. And insurance and credit have a long history of that, and a lot of activism pushed back against that. That's the right prehistory of kind of machine learning ethics, and Rodrigo Ochagame is the person I credit for kind of making that connection for me. Breiman argues, others argue that statistics ignored this at its own detriment. So absolutely, there's a place for it, but there's a cost to abandoning a lot of those guardrails. This is Bob Cass's traditional picture of statistics. This is a version of different types of validity. And I like how Deb kind of separated out internal and external validity for machine learning, but in general, machine learning ignores everything except for these parts. On this diagram, it ignores everything but kind of out of sample success or attempts to estimate that. Ignores all of these. Sometimes you can do that. Indeed, there are what are called prediction policy problems, although I think we need to think carefully about what's actually that. But there's a cost to ignoring these, even if sometimes it is appropriate. And I'll talk more about that. These two goals turn out to be separate. Non-causal, I tend to stay away from the word spurious because that can either mean non-causal or it can mean overfitting. Correlations can fit robustly, such as if they have a latent common cause. And these are some works, calling them different things and theorizing them. I like Senthil Mullainathan and Jan Spisa's version best out of all of these. And then on the other hand, econometrics will kind of portion out everything but a small place where we can actually tease out causality, which means we get a poor kind of view of the entire system. I would recommend this philosophy book for machine learning and statistics. It's the only philosophy work I've found that really delves into the meaning of prediction. We don't think about that enough. He has this very helpful table. All of machine learning is really what he calls rudimentary or elementary forms of prediction. When people hear the word prediction, especially in the press, they are probably thinking it's scientific sophisticated, that there's causal correlations, that there are laws being discovered. Maybe that's what machine learning should be. Drew Diapro certainly thinks so. Others on the causal learning literature argue for this. But in terms of what the majority of machine learning is, it's a rudimentary form of prediction. It's not going to have the same solidity as something that is phenomenological modeling, law derivation, or indicator coordination. And that's important to keep in mind. Bruce Hoadley, one of the commenters on Leo Breiman's 2001 paper, notes that, yeah, correlations are great. Sometimes things do change. Google Flu Trends did their cross-validation correctly. They didn't have temporal leakage, but it still failed. This is the diagram I used from a public health paper that actually shows how Google Flu Trends failed. The dashed line is Google Flu Trends. The bold line took a delay to find those numbers, but the actual CDC flu numbers. They fixed it, but it still failed again later on. Sometimes the world just changes. Something else I'll come back to later on. And of course, correlations are not causation. Correlations can't predict in the presence of change or interventions. And again, Mullainathan and Spies has a nice diagram about this. Leo Breiman thinks it's a good thing, which I think we have to contend with, but that's a more subtle point. We should always do out-of-sample testing if possible. I really like an example I came across of a 2002 paper, custom-built decision tree for correlates, genetic correlates of breast cancer. It took 14 years, but finally this was tested truly out of sample. They had a really nice study design where if both tests agree, absolutely treat with chemo. Both tests disagree, don't treat with chemo. The question is, what do you do if the two disagree? And that's what those are the patients who are randomized into chemo. This is what they found. So from this, you understand how the machine learning generalizes. It was able to pick up false positives in clinical diagnosis, but if you used it as your first port of call, it would make things worse. You would subject people to chemotherapy who wouldn't actually benefit from it. There's subtleties in that, including the fact that we model the correlation, but the actual target is if people with a certain genetic profile will benefit from chemotherapy. Subtle difference in the objective. The latter objective is what we care about, but we can't actually measure it until we've done this study. The Lucas critique in econometrics is similar, that we can only model interventions in the world that we have now, not interventions in the world that will exist with the intervention. Very subtle point, but it can be important for machine learning interventions. One of my pet peeves is language. If we can avoid saying prediction, avoid saying prediction. If it's really correlation, just say X correlates with Y, not X predicts Y. Prediction is overused as it is. You will see predict the probability of risk. That's akin to saying a probability of a probability of a probability. That's kind of nonsensical, if not redundant. And so use estimation, use calculation, and be careful. If we can use detection or classification, use that. The paper about predicting race from medical images didn't use the word predict, but media coverage of it did. You don't predict race. And detecting and predicting cancer imply two very different tasks. And I always try to say models, not algorithms, unless I really mean iteratively reweighted least squares or CART, because all models are wrong. I don't want to have to spend time kind of revisiting and showing that all algorithms are wrong if we're just talking about models fundamentally. Fixes, expectations, language, claim making. We should be precise about what we're actually demonstrating, avoid the use of prediction because it has this powerful kind of resonance of the human psyche dealing with prophecy. And it's not sophisticated. It's not low down on that kind of hierarchy that Rescher provides. And just because we found a correlation doesn't mean we've advanced scientific understanding. That's another drawback. And this is why machine learning is sometimes only appropriate for exploratory purposes or engineering purposes. And this is some ongoing work that I have with some collaborators that I want to give a shout out to. 3, this is a lot of math. It's on the website. I'll go through it quickly. Those of you who are familiar with the math don't need a long time to look at it. Those of you who are unfamiliar, even if you looked at it for 10 minutes, it probably wouldn't sink in. But you can go to my preprint where I try to explain things in intuitive ways as well as formal ways. Model metrics are estimators. What we care about is not how well a given model performs, but how well it would perform on out-of-sample data. In statistical terms, it's an estimator of an underlying unknown quantity. We can study that statistically. I have a demonstration that dependencies cause test error to be biased, and we should look at their distributions and study them. We can even apply instrumental variables because accuracy test error is an estimator that can have bias that an instrumental variable might overcome. Matrix bias variance decomposition, if you do it in multiple dimensions, you get this extra term of which Bradley Efron in 2004 called optimism. And I think Sayash and Arvind, when they're using that term, optimism, pessimism, they're likely referring to that. The classic argument for doing cross-validation is if you were to just train and test on the same set, you would have this kind of extra covariance penalty. By splitting out the test set, the estimator is independent, so this covariance goes to 0. Otherwise, you have this kind of extra thing that makes you think the error is lower than it actually is. But let's apply this to non-independent and identically distributed data. Kind of 2 copies of X, randomly drawn Y for each of those copies, and a ton of covariance between them. We get optimism in the training set, but also in the test set. An example of what this looks like, this is kind of a model polynomial specification. Training and test can be close to each other, but far from an independent draw. And this is kind of the logic of this. So you think that your test error is worse than your training error, but the actual out-of-sample error is enormous potentially. Okay, this is only one example, but it's a framework for understanding. And certainly we see places where we can use this framework to understand things. If you use future values and train on them and then test on past values, that's time traveling. Unfortunately, I think this blog that kind of critiques that paper is no longer online, but it had some great kind of points. If a colleague of mine naively kind of trained a model to recognize birds on a windowsill from a webcam and split frames randomly, of course, you're memorizing 2 adjacent frames. And I like this example from Greg Park. Kaggle has a public leaderboard and a private leaderboard. You can resubmit to the public leaderboard and see your results, but the private leaderboard is kept secret until the end. That catches and I think quantifies overfitting to the test set in a really nice way. Wagstaff, Machine Learning That Matters, argues that probably we shouldn't use the test sets only once. Pure, lack of burning the test set would require only using it once. But probably, I think the better outcome or the better approach is just hedging our claims and being much more limited in what we claim. Split by dependencies. I also like Rescher, who talks about every prediction necessarily entails a meta prediction, whether you predict the prediction holds, and so on ad infinitum, but at least 3 levels out is useful. So cross-validation is meta prediction, and optimism helps us look at meta prediction. And I think we should try to do that. And of course, we need to make assumptions. Machine learning has ignored the IID assumption, even statistical relational learning when it comes to testing, but it can't. You don't care about standard errors being biased. You don't care about estimates being biased, but the test error is also an estimate that gets biased by dependent data. The next thing, and this is some preliminary work, how are metrics distributed? I could find very, very little about how these things actually are distributed. Which is kind of a precursor to designing statistical tests. So I simulated this. This is, just a normal standard normal variable, and then just a kind of bivariate specification of a binomial. large sample size, small sample size has some funky stuff, but I'll just stick to large sample size. Okay, counts look pretty nicely, binomially distributed, normal approximation. Precision and recall start to look weird. Of course, we know they're dependent. I've never seen anybody modeling a joint distribution. Maybe we should do that for precision recall. This is just randomness over Y. This is just randomness over the irreducible error and nothing else. And we already see that this is kind of a two-dimensional Gaussian. But this is really weird. This is a mixture. Not in AUC, fortunately, but it persists in F1. Okay, AUC, this is not a lot of variance from irreducible error, but we probably should look at power and do power calculations. And I would love to think that I did this wrong. My code is in the appendix, that this is not actually a mixture, but somebody should look into this. There's only scattered preliminary work, but this should be kind of, intro graduate statistical machine learning, these distributions. And so we should really start taking a look at these. In the meantime, bootstrapping, Wager has a really nice comment where he looks at the performance of CV for model selection versus evaluation. And against the Rashka paper that the first speaker mentioned, we should use a totally held out test set for model evaluation and only use k-fold CV for model selection. And then we should bootstrap to the test set to get standard errors until we have better kind of statistical results. Study asymptotic, study distributions. Cultural issues, now this is a lot more subtle, and I'll cover it in the last minute and a half. Really nice essay from Phil Agri towards a critical technical practice, where he talks about kind of the limits of his education in AI. Good old-fashioned AI, not machine learning, a lot carries over. Most people in machine learning or even statistics have never seen some version of this chart of paradigms of inquiry, but it's basic in social science. And it's important that we think about how we even assume the world works such that we should expect generalizability. We should keep in mind that the quant view of the world is not inevitable or natural. It's quite the opposite. Qualitative research approaches the world in ways that are much more kind of natural to how we think of things as human beings. We expect that models are picking up signal, not noise. But maybe we should rethink that and rethink where we should even expect regularity. What are we even doing? So when I bring this critique to people, that can be very troubling. If science isn't true, what are we even doing? But I think intellectual supremacy is probably a bad reason for doing science. I think that there's ways of understanding and doing science that don't use generalizability, reproducibility as the standard, but use it as a lens of understanding and interacting with the world. But on the other hand, that's not a very developed idea I have, so that's still a work in progress, but it's something I want to offer to the crowd here. Lessons from other fields. I have some work with Nicole Nelson, who's a historian of science, on the rhetoric and the kind of this debate in biomedicine and psychology. This is just to say that machine learning is probably not unique. And it's really dramatic failures that precipitate crises. And that hasn't happened from dramatic failures yet in machine learning. Despite those headlines, I don't think that we'll actually see any reform. There won't be an external incentive for it, at least not yet. And so we probably won't get reform, but of course we should still try to reform methods just as a matter of course. Summary and conclusion, contextual issues. I would encourage scientists to rethink their fundamental assumptions about how science works and what it is and how the world works. We shouldn't expect reform anytime soon, but of course we can still take these methodological steps. I have a little chart here. There are problems that exist that we can definitely solve, that we should do regardless of whether or not there's a crisis, regardless of what we might think about the nature of science. And that's just to get our methods more in alignment with what we think we're doing and what we should be doing. Thank you. References and simulation code in case somebody can figure out why I had a mixture.
Amazing. Thank you so much, Momin. This was an excellent talk. All right, next up, we have our last talk of this session, which is by Professor Marta Serra Garcia. Marta, over to you.
Hi, everyone. Thank you for having me. I hope you can hear me. I'm gonna be talking about the replication crisis in social science, and this is gonna relate to my recent work on replication or replicability and citation. So what happens after we figure out that some results are not reproducible or not replicable, does science self-correct? I'm not going to be talking about machine learning reproducibility. This is going to be about social science and mostly lab experiments, but I think it's relevant to the crowd and everyone interested in machine learning methods because of two reasons. First, the replication crisis in psychology and economics has led to some changes in how we do research, how we conduct lab experiments that resonate with many of the things that we've been discussing. So I'll mention them at the end. And second, because it's important to know what happens to science after we discover these failures of reproducibility. And I think I don't have very good news here, but I think it's important to know, which is that non-replicable research may be cited and cited and cited, and people may not learn about their failures to replicate unless we are very aware that people are attempting to replicate and it didn't work out. So with that said, I'm just going to briefly talk about or differentiate reproducibility and replicability. I think this was mentioned before, but reproducible research is using the same data as the previous researcher, conducting the same analysis, finding the same results. In social science research, we often use lab experiments. That means that when we want to replicate something, we don't necessarily have the same data, but we go to different human subjects, for example. We run the same experiment and we see if we run the same analysis, whether we find the same results. I'm going to be talking mainly about replicability, but those are very closely related insights, as was mentioned earlier. And obviously, there's discussions about how we define them, but that's how I'm going to refer to replicability. Okay, so I want to take you a little bit through the story of the replication crisis in psychology and economics and our findings about its consequences long term. So in 2015, Science published an article about replication in psychology experiments. And that made the news and the headlines and really shook the field of psychology and many of us who use lab experiments. For example, Nature had a headline talking about it, stating that over half of psychology studies failed reproducibility tests. It was featured in the New York Times that many psychology findings are not as strong as claimed. In the Washington Post, the same, that many scientific studies cannot be replicated, and that's a problem. So what is this replication crisis? What happened? There were three big replication projects that I'm going to briefly describe. So in 2015, the first replication project done by the Open Science Collaboration took 100 research papers that were published in 2008 in leading journals in psychology. These were based on lab experiments. And what you see here is the distribution of the effect sizes of the original studies. And obviously, most of the results were significant with relatively large effect sizes. Now, what happens when a new team of researchers gets the same experimental instructions, implements the same procedures, has a well-powered large sample and tries to replicate those findings? Well, much, much smaller effect sizes and only 61% of replications failing. That means that the original study had a p-value below 0.05. The replication, a well-powered replication that tried to do exactly the same as the original study, had a p-value larger than 0.05. So is this only psychology? Well, one could ask, does this happen in economics? I'm a behavioral economist by training. There are many studies in leading journals that are published based on the lab experiments. So a new team of researchers led by Colin Kemmerer and Anna Dreber attempted to replicate 18 papers published in economics in two leading journals. If we would be able to replicate those original findings, we would expect most of the replications to have effect sizes that lie around here, around 1, because these are relatively standardized effect sizes. What we find is that a majority of them are to the left, so smaller effect sizes in the replication, and 39% of the replications failed. That meaning that the p-value of the replication was larger than 0.05, while the original result was below 0.05. What happens when we look at a different set of journals, Nature and Science? These are leading journals, have very large impact and get a lot of citations. These authors looked at 21 studies that were published in Nature and Science of social science experiments. So these are mostly psychology and economics, but also related fields. And again, you can ask yourself, well, if we run a replication, do we find the same effect size. Then we would find most results around 1. What they found is much smaller effect sizes and 38% of replications failing. So overall, we found psychology, economics, and nature and science, when we attempt to replicate important results published in leading journals, there is a substantial fraction that didn't replicate. And these were findings in 2015, 2016, and 2018. Now, one may ask, well, is this a surprise to the field? Is this something that others that we don't know, that we were completely surprised about? Or can experts predict which studies will replicate? And so what some of the researchers in these teams did was run betting markets before the replication results were known. So basically they invited experts to play or gamble or predict or trade in a betting market about the replicability of these studies that they were going to replicate or that were currently in the replication process. Can experts predict? This headline by The Atlantic kind of summarizes the results. They can sniff out weak psychology studies. So an expert can look and often they were able to correctly predict which studies were going to replicate, around 71% accuracy. So correct predictions ended up arising. So this leads to us, this is where my joint work with Ulrich Nisi and that was published recently comes in, is while we've seen many papers that fail to replicate in social science based on lab experiments, but that experts could predict which ones would. So maybe this is not a problem. Maybe replicable research is then going to be cited, and non-replicable research is maybe going to be cited with a hint of caution or not cited as much. So we asked ourselves this question: are papers that fail to replicate cited more or less than those that did replicate? What happens to citations? Is there any awareness in future work about the replicability of these initial findings? So in our work, what we've done was take Google Scholar citation counts of papers that were published, that were studied within this 3 replication projects. So I mentioned the psychology, the economics, and the nature science papers. So we took 80 of these papers from these studies. Why do we focus on these replication projects? Obviously, when you look at replicability, there's an issue of selection. What is important about these replication projects is that they took all papers published in leading journals in a given period. So if you were concerned about selection here, there's no selection on what to replicate. These are all of the studies that were published within a certain time period. Now, do citations differ for replicable and non-replicable studies? They do, but actually what gets cited more is non-replicable publications or the non-replicable papers. And that happens, or in our data indicates that it happened even after the replication study was published. So I'm going to show you a few of our results. So if you look at the distribution of total citation counts, you can see that for nature and science, the non-replicated ones that's the blue line, they have many more citations than the replicable ones, which are the black line. We find a relatively similar result for economics, a smaller gap, and even smaller for psychology. So there is a gap in the total citation count of these papers between the time they were published and the end of 2019, which is when we stopped collecting the citation data. Now, on average, replicable papers were cited 153 times less than the non-replicable ones. The papers with larger relative effect sizes, so where the replication was closer to the original study, were also cited less. And the studies that were predicted to replicate by experts were also cited less. Now, one may ask, well, maybe this is something that is happening at the beginning when we don't know yet about the replication results. So let's see what happens after replication. So here's a chart where I'm showing you the years. In gray are the years in which the original papers were published, and in red you see the year in which the replication project was published. For nature science, we only have 1 year, so that is obviously very little data. When we look at economics, we have a few more years. The citation gap doesn't change much. We look at psychology, we also don't find much of a change. So after the replication project is published, we still see a citation gap, and that doesn't seem to change by much. Hopefully more and more years will come and we'll uncover new trends in the data, but from what we saw initially, we haven't seen that the citation gap is closing. So they are cited more, non-replicable papers are cited more, but does it matter? Perhaps these citing papers of non-replicable work are of worse, quote unquote, quality. So how can we assess that? What we looked at is at this impact of these citations, and we asked 3 questions. First, how often are citing papers themselves cited? So maybe they are not cited and not looked at by other researchers. How often are citing papers published? And if they are published, what's the impact factor of the journals in which the citing papers are published? And so we took the data from over 20,000 citing papers and considered journals in the Journal Citations Report database. So very briefly, the answer to the 3 questions is, how often are citing papers cited? Well, similarly, both if they cite a non-replicable finding or if they cite a replicable one. Are the citing papers published? We find slightly higher a likelihood of a paper being published if it cites a replicable result. It could mean that during the review process, there are some corrections made and references changed towards favoring more the replicable over the non-replicable results, which is encouraging. But conditional on being published, the impact factor of papers that cite a non-replicable publication is very similar to papers that cite a replicable. Okay, now I showed you a gap in citations, and also another natural question could be, well, maybe these are negative citations, right? Not all citations are the same. It could be that these non-replicable results are cited, and it's good because we're learning about the science. We're learning that there may be a failed replication, an initial result that worked. We're having a discussion and learning about the ground truth. It's not all about one study or one replication. So what we did was look at the type of citation. How is this replicable or non-replicable result, according to the replication project, cited? So we take data from these failed replications and look at many, many citing papers and dig deep into each paper. So we found, out of all of these papers, we found 83% were in English, and there was a citation in the text to the relevant paper. And together with a team of research assistants, we went through the papers and asked, well, does this citing paper indicate an awareness that the findings in the original paper failed to replicate? Right? It could be because they cite the failed replication. It could be just because they cite other studies that find mixed evidence. It could be because they just state that they, that's an original result, but there's mixed evidence. We found that only 12% of citing papers mention the failure to replicate or mixed evidence. So it seems as if these original results are published without much discussion of evidence that's been produced later on about showing lack of replicability, at least in one instance. Now, this brings up the question about why are papers that fail to replicate cited more? We don't have a definitive answer, but I think what I will say resonates with what was said in the first panel and some of the things that have been mentioned earlier. This is our conjecture. Of course, it's not proven, but one thing we think is that when you're reviewing a paper, when a review team, an editor, and reviewers are reviewing a paper, they could face a trade-off. One between what we could call an interesting result, exciting, new, surprising idea, and the robustness of the evidence. If that's the case, then maybe there's an unconscious weighing of these two things such that the experts may favor the result interesting and unconsciously put less weight on whether the evidence is robust. There's very interesting work on this area. Many papers have been cited and work in previous presentations. I would recommend also the book by Stuart Ritchie on science fiction. So discusses fraud, bias, negligence, but also hype and the replication crisis across a lot of different fields. So to conclude, we find that non-replicable research or papers in psychology, economics, and nature science focusing on psychology and economics are cited more than replicable ones. A possible explanation is that results that are considered interesting could be subject to lower standards regarding replicability. And that raises questions about how we do the review and also how we state the results. Based on what we have seen within social sciences, I have a few suggestions on, at least fixes that have been adopted in other social science research using lab experiments. One is pre-registration. There's been some of the fixes that I have heard being mentioned before have some resonance with the idea of pre-specifying or ex ante stating what is the sample, what are the runs or the simulations or the experiments that are going to be run, what are the key hypotheses, and what's the data prior, or the data that's going to be collected prior to actually having that data. That kind of reduces researcher degrees of freedom, a term that has been used before to talk up to us about this issue that, we have many options when we are conducting research, be it machine learning based or also experiments, and tying our hands ex ante before we see the results, before we see the data, could be a good first step in reducing issues with replicability or lack of robustness in our results. And in social sciences, we have many platforms that allow us to pre-register a study, and we then publish our papers with the pre-registration. I think this is akin to the checklist that was mentioned, and that other initiatives that are being also put in place within machine learning. Open data is something that I've seen many of the presentations mention. This has become the standard as well. So, and the open science framework could be a place to openly post the data and share both data and code and make it available. Many journals, at least in economics, are now requiring this to accept the paper. So your paper will not be published. It's always conditionally accepted, only will be published subject to a second data editor or a data editor going over your code and your results to ensure that they are reproducible. The last thing, and this has been mentioned as well before, so I think there are many issues to talk about in the panel and throughout the workshop, incentives. So the fact that we have new and interesting ideas and have first evidence for them is great. It should, to some extent, be rewarded. It's sometimes that science is progressive. We learn through trial and error. It doesn't mean that, we cannot propose new ideas and have first results, and that review teams cannot say, this is really interesting, could change the field, let's publish it. But maybe we should write about it as such, as this is first evidence, or this is the first results. I haven't, these are the potential problems, but these are very nice or very important and groundbreaking changes to the field. Because sometimes the pressure to publish may lead researchers to think that whatever they state has to be a really strong and final statement of what their findings are, without mentioning the pitfalls or the limitations. That's bad for future researchers that take that initial study with first data and may take it as being more robust than it may actually be. And with that, I'll conclude. Thank you.
Amazing. Thank you so much for the talk. So now we have concluded all the talks for session 2. We'll take a quick 5-minute break, and we'll be roughly back around 1:42 p.m. Eastern time to begin our panel discussion. In the meantime, please feel free to keep putting your questions in the chat. Your questions have been great so far, and they really help make our task as moderators much easier. All right, see you all in 5 minutes. All right, welcome back, everyone. We'll just begin our panel discussion in a minute, and we hope that all the speakers can join us for the panel. Yeah, we'll spotlight all of them in just a minute. All right, we're all set. So first of all, I want to thank you all so much for such a wide range of topics that we discussed. And we also got to go quite a bit into the depth of these topics. So thanks a lot for all of your presentations. I'll start with my first question, and this is directed towards Martha and Michael, which is, what is the hardest part of changing scientific practices according to you? Both of you have been, looking at how hype can sort of lead to irreproducibility and what we can do about it. So in your experience so far, what have you found to be the hardest part of changing these practices?
That's a good question. I think it's making people aware that they're not doing things the right way. Because, well, I guess you can tell from my presentation that I think a big part of the issue is that people don't necessarily have much education in machine learning before they start practicing machine learning. And things that often seem like good ways of approaching a problem have pitfalls that they're just not aware of. And there's this question of how you can make them aware of these things, and I don't really know what the answer is. I just put this guide together and make it available and hope people will read it, but whether that happens or not, who knows?
Yeah, I agree with that. I also think that there's incentives, and so we get new and interesting ideas, and then the question is, we want to put it forward. We have some evidence, and it seems like the incentive, at least to get the paper published, is to say this is this is my result, right, and make it sometimes sound more than it actually is, and sometimes during the review process, right, as reviewers, I think it may help us to say, well, this is a great research idea. We don't have to have final results. You don't have to have 100 versions of the test and show that in every version of the test, it works, right? Because if that's the pressure you're putting on the researcher, then that may lead to, let's say, hype. And sometimes it's unconscious, and sometimes we forget that this is a learning process, right? That we do publish an idea, we do want to learn, and others will come after and add to it and maybe correct us or maybe find out where it has its limitations.
Amazing, thank you. Oh, I'm sorry, Michael.
I was just going to say that I think another problem is that in many applied areas, people don't get good feedback from reviewers and editors because the reviewers and editors don't understand machine learning. And I see in the fields I work in that often in very good journals, there's very bad machine learning papers, and no one's going to pick this up.
Got it. Deb and Momin, anything you want to add to this answer?
I think at least talking to people with some training in econometrics or social statistics, just explaining machine learning as kind of an instrumental use of correlations goes a long way. Why do we even need data splitting? Why don't we do data splitting in econometrics or social statistics generally? Maybe we should, but it's because if you're building a theory-based model, the ways in which things can go wrong are very different. Overfitting is seldom a concern. If you're doing stepwise regression, which probably nobody should do now that we have the lasso, then it's a concern. But yeah, the concerns are very different. And so just explaining this is how correlations can go wrong, this is why we do what we do, explains why you should avoid overfitting to the test set. You should think about that. You should, think about data leakage. That's my running hypothesis. It's been somewhat effective, but that's just my anecdotal experience.
Yeah, I'll add that I think education is really important, and that's definitely an important intervention. I also think you can kind of twist people's arm a little bit more, set some restrictions or some boundaries in terms of the expectations of what we sort of allow and don't allow with respect to publication. So whether that's in the machine learning field through sort of policies of different conferences and guidance provided to reviewers, where we're just a little bit strict about certain reproducibility requirements and some executing on some of these suggestions and in Michael's paper and other work that kind of points to particular practices that are sort of best practices and enforcing that as the standard required for publication, either in machine learning venues or other venues like other journals where people are beginning to use machine learning as a method. So I do think that we can definitely leverage some mechanisms we have for enforcement of other ways, other research integrity issues to also apply to reproducibility issues. Another sort of option that's been presented as well has been funders sort of setting requirements around like publishing your data or publishing your code and having that be another opportunity to sort of guide or push people a little bit more forcefully to comply to some of these best practices. So yeah, there's lots of, I think, opportunities for these kind of things.
Cool. Actually, that leads us very well into our next question, which was targeted to Deb. And then I think, Mike, Momin, you can also take a moment to answer it because you also went into this. So the question is, Deb, you mentioned that we don't know what the best model across all settings is, but if the data distribution and collection practices differ across contexts, do you think we should strive for generalizability? Or do you think we should just be more precise about the contexts in which a model is appropriate?
So I think for deployment of like the current state of the art machine learning models, definitely a more specific articulation of when the model is appropriate to deploy is my preference. So just being clear in communication around here is the data set that here's sort of the scenarios in which we have a validated performance for, and then every scenario outside of this scenario is effectively an unknown. And being very honest about that, I think is a very critical step forward. That's why a lot of my interest has been in documentation strategies of just communicating to different stakeholders the limits of where you can actually apply this system. I understand the desire of the machine learning community to extrapolate. I'm also very curious what Momin's response will be to this question. But yeah, I totally agree with you that there is like a very strong interest with generalization in the machine learning community. And that's because you want sort of this all-encompassing, all-in-one machine learning model to rule them all that you can deploy everywhere. The challenge, of course, being that that's not the practical case. So for me, it's just, honest reporting on evaluation and sort of where you have validated results and where the results are unknown, or which populations you validated results on, and communicating that through a model card or other sort of transparency mechanism, for me is sort of the approach that makes the most sense. Even if you're aiming for generalizability. So in our relearning at paper, we talk about how if you want to be able to claim broader sort of general applicability, then you need to evaluate it in a wider range of scenarios and report those results and still state that there's limitations beyond that. But if you want to apply it to like more than one case, then you have to evaluate it on more than one case to demonstrate that that generalizability is there. So we don't even do that. So even starting there would be like one way. But yeah, I think as a goal, that's definitely a question goal. I also wanted to add a final thing, which is, there is this trend in machine learning, and we have another paper called the AI and Everything in the Whole Wide World benchmark, where we talk about how people will develop, data benchmarks have a history of being anchored to very specific tasks and applications. But in the machine learning community, there's sort of these like higher level intellectual objectives that people have. They want the model to have visual understanding or natural language processing. So they develop these sort of generalized sort of cognitive ability benchmarks. So things like, Glue or ImageNet are examples of this, but they're not actually tied to any practical task. So what does performance on Glue mean with respect to some downstream tasks? We don't actually know. What does performance on ImageNet mean with respect to some downstream tasks? We don't actually know. But the prevalence and the sort of elevation of these, we call them like general benchmarks or everything in the whole wide world benchmarks, where they try to fit the whole world into a benchmark unreasonably, has also distorted our understanding of what it means to do well on these like downstream tasks. So I do think definitely like ignoring the way that data is localized and the way that these benchmarks represent very specific contexts has already led to sort of this delusion of generalizability that we see in the machine learning space. So I'm against sort of the use of data benchmarks as the approach for that.
Amazing, thank you. Anything to add, Momin?
I also would say I'm much more in favor of limiting our claims, limiting the scope. My dissertation, which was very much in computational social science, I concluded based on what I looked at, Twitter doesn't generalize. If we study Twitter, what our interest should be, and the only interest that's valid to use Twitter to study is what do people do on Twitter? We can try to link that externally, but that's so fraught and so noisy that I'm not sure it's ever worth doing. There still are valuable and interesting things on Twitter, but that should be our only kind of goal. Almost use it anthropologically, right? That this is a one-off. This tells us maybe about the variability of human behavior and experience, not the mean, not the signal, not the central tendency. So yeah, I'm much more in favor of that. I think we should also think about if a particular estimation procedure, rather than the specific estimates or the specific trained fitted model, might generalize. And that's much more realistic to think that we should allow retraining. It's not very satisfying, different genes in two populations in different states might be selected into a model, but we should be okay with that, right? We should okay with what's selected not being stable necessarily, as long as it works effectively in robust out of sample testing for the relevant population. And that's why I like that Cardozo et al. Example. We can discover things about how the model does generalize. And we can do kind of audit testing on subgroups, more on that, but yeah, definitely limiting our claims, giving up on generalizability and giving up on universality. And that's a much larger theme that I try to argue about around science.
Amazing, thank you. Actually, someone from the audience just posted what was going to be my next question to the entire panel. So the audience question is, how difficult is it to point out such issues? For instance, failures in well-published papers. In my experience, researchers or people generally do not like being told when they're wrong. Do you think that such well-needed investigative papers are difficult to publish? Or even worse, that such papers can tarnish one's reputation? Maybe we can go Martha, Deb, Michael, and Moomin.
It seems to me that it really differs by field. So I think psychology after the replication crisis became really open, and there's lots of interest and very well published work criticizing prior work, reanalyzing. Someone was mentioning reanalysis, right? My experience in economics is that that's more rare, and people take it perhaps a little bit more personally, but maybe the culture will change. Maybe in other fields it's a bit more open, and I hope it will be. I think that would be helpful for all of us.
I think people take it personally in every field. Yeah, I think reanalysis is definitely an objective. I think maybe it's more common. It seemed like it was more common in the biological sciences, especially when they can share data sets, and they went through this open data movement in the last couple of decades. So I think that has allowed for people to begin to reanalyze things. And so quantitative political science spaces also will share data and try to reanalyze things. But yeah, people always take it personally. There's RCTs that have been since debunked. I don't know if anyone is familiar with the warm wars, where the deworming RCT, where they were sort of analyzing the effectiveness of these deworming pills. The RCT said that giving kids these deworming pills had led to all kinds of benefits. And then they actually published their data, and other researchers were able to re-examine it, and they found that the results fell far short of what was initially reported. But then I read a book that was published 2 years ago, and the first example of a successful RCT that they gave was this deworming RCT that's since been debunked by multiple studies. It's been years of other researchers pointing it out. So exactly what you had been sort of discussing. So I feel there's a lot of challenges with everything you said about getting people to actually take in the critique, but also even more challenges with making sure that people understand that it's not personal and it's really just in service of the science. In a lot of my audit work as well, I find that when you confront a company with a deployment result where you're saying the system doesn't work, they also very defensive. I think that we have strategies to mitigate this with corporations when we do our audit work that might be helpful in terms of the science communication part of things. So with audits of deployed systems, what we do is we actually have in information security where they're like inspecting a system to see if there's like a computer virus or something in it. They actually have a very strict protocol around how they communicate around that vulnerability. So they have sort of like a vulnerability communication protocol where they tell the company, but then they also have an obligation to the public. So they tell the company like, you know, we found this vulnerability in your software. You have 30 days to respond or 90 days or whatever it is. And then at that point, we're going to release it to the public. And if you have a response within that period, we're going to publish our results, but also publish your response with our results. So the public understands that you're aware and you're addressing the issue. And I think something like that might also be nice because that minimizes corporate hostility towards the results. And we did that for the gender shades audit and it worked well. And we've done that with other audits as well. And that might be a nice strategy for reanalysis in the sort of computer science space of just, communicating with the authors beforehand before you make it public, so that they're not caught off guard or they don't feel attacked. Another thing as well is I mentioned bug bounties and the idea of just incentivizing people to re-examine some major studies and major findings through just actually paying them. There's in that Nature article, they talk about classes like students participating in, reanalysis studies as part of their education. The reproducibility challenge at NeurIPS was very student heavy in terms of participation, whereas part of their learning process, they re-implement an algorithm or they re-implement a model. And it's like part of their learning to reanalyze the system and revisit it. So that's another strategy that I think has worked well. So there's all of these little things that we can set up. Someone has also mentioned the idea of a reproducibility journal or having like academic publishing incentives around reproducibility studies and reanalysis studies, and a little bit of a harder problem, but at least a workshop where people can demonstrate these results would be nice.
That's actually super interesting because in our next session, Dr. Jake Hoffman, he's written, I'm not sure if he'll talk about this, but he's written a paper on doing what he calls data analysis replications. And there too, they did something very similar where they worked with undergrads to sort of uncover these problems. So yeah, that's a super interesting set of points. Michael, do you want to go next?
Yeah, it can definitely be a problem getting critical work published, particularly if you're working in a fairly niche area. I certainly had one paper where I'm pretty sure it was sent to the person I was criticizing to review and it got rejected because of that. I guess preprints helps. You can get the information out there still, even if it's not formally published. And I think it's worth trying because it's important to get this stuff across to people.
Great. And Momin, any thoughts?
There's another quote, I think, from that same Phil Agri paper, that when you come from a technical field, structural analysis can seem like a personal insult. So I think if we, and he means kind of like sociological analysis of power structures, not methodological critique. But I think a similar principle applies, that we should do a better job of building that in. One of my academic heroes and mentors is Cosmo Shalizi. For those of you who know, he's famous for kind of calling bullshit. He has a paper debunking the claims of, the Christakis and Fowler kind of Framingham heart study, contagion study, kind of rejecting the idea of power law distributions being found everywhere because they're using kind of 100-year-old outdated stats methods. I asked him about this, why don't you write more of these? And there's some things that he critiques but doesn't write about. And he said, there's only so far you can go in your career just writing negative things. And so even though I love that work, and he has more papers like that, he wrote about Ergam's exponential family random graph models, which also prompted a whole big thing. But yeah, there's only so far one can go professionally. That's the advice I've gotten, even though I love kind of iconoclasts, bomb throwers, bullshit callers, and gravitate towards that work. But yeah, that's the advice I've gotten.
Wow, this is fascinating advice and sort of reflections from everyone all across. It's also interesting that everyone has had these experiences. It just shows you how difficult doing some of the critical work is. So it's great that, all of us are here together today. All right, the next question is for Deb again, but I think we can have like a lot of perspectives from all of the speakers as well. And I think this is this was framed when you were talking about reproducibility as an integrity issue. So the question is, framing reproducibility as an integrity issue is a fascinating intervention. It could be very effective, but how do we make sure that we don't incorrectly accuse researchers of malfeasance in cases where reproducibility failures are due to oversight? And could you speak to how it's played out so far?
Yeah, so I kind of mentioned it in the context of the NeurIPS ethics review process as an intervention where some of the reproducibility challenges people were facing, we decided to integrate as just something for the technical reviewers to flag if they thought that there were, like it kind of compromised the integrity of the result or the presentation of results. And then that could be sent to an ethical reviewer or the PC, depending on the nature of the problem. And what we found was that a lot of the cases that were flagged ended up not being like insurmountable by the author. So it was really just, it ended up being sort of a feedback session for the authors around that aspect of their paper. So the ethical reviewer would point out, you know, you need to release your data, or you need to release a data dictionary, like this is illegible data, or some kind of problem around the way that the results were presented and the resources that came with the results. And that was actually within the review timeframe, a lot of the authors were able to fix it. And I don't think we didn't end up rejecting any paper because of reproducibility issues. It was just another way to sort of flag for the authors that this was actually like a serious ethical consideration on par with, some of the data ethics considerations or some of the other sort of bigger questions around broader impacts. Like this was actually a really kind of critical piece to what it meant to do good research. And I think, a lot of it was due to oversight, but they were able to fix it within the review period. I think if they weren't able to fix it between with like the 2 or 3 weeks that we had for the review period, that would have actually been a really interesting question for the organizing committee of, do we allow papers that fall really far, like really short of whatever reproducibility kind of best practice standards we have? Do we allow that work to show up in our proceedings? And I think that's definitely a conversation the community is having right now on if that is like a valuable enough aspect of the work that not meeting that standard is enough to kick it out. But in my experience so far, like it actually is not that much work to meet those standards, especially when they're pointed out to you. So it's able to be addressed within the time frame, and it actually didn't practically interfere with them publishing.
Thank you. That's so fascinating, Deb. Any other thoughts from the panelists? If not, we can move to our next question. And I think we only have time for a couple more questions. So the first one is, what do speakers think of MINIMAR and other reporting guidelines of AI research? So for context, MINIMAR is the minimum reporting for medical imaging in AI. And the questioner also asks, are any particular ones preferred? Do you prefer any one over the other? So I think I can also give some context on this. I think a lot of checklists have been published in the last few years across domains, but specifically coming from medical sciences. And so if you have experiences in your research dealing with any of them, and of course we have model cards, which Deb was also a co-author on. So what do you think about what constitutes a good checklist, and which one do you prefer over the other? Or any thoughts on the current status quo?
I think checklists are a good idea, but I do worry about whether they're understandable to everyone who's going to use them. Because a lot of fields, as I keep saying, people don't have much experience. And these checklists tend to be written in quite a technical way. And I think there's certainly scope for helping people more to understand them. We're perhaps producing documents, kind of going into more detail about what these things mean. So they kind of guide them through the process of following these checklists.
Yeah, I think I would agree. Like the NeurIPS checklist and the reproducibility checklist that was developed for the challenge and then ended up being sort of a requirement for NeurIPS papers. I think like collaborators in other domains, and even people sort of submitting to like the NeurIPS application track from other domains struggle to fully understand what is actually being discussed in these checklists. Like they're actually quite, they include a lot of vocabulary, and they don't necessarily always the most clear, especially when attempting to discuss across domains. So I think having domain-specific checklists is always really helpful, just to make sure that everyone using the checklist understands the vocabulary and is doing the same thing in response to what they're seeing as the requirements. I will say, like, even something like model cards is really hard to get people to implement. I know that it was a challenge even initiating that effort at Google. Sometimes you have engineers that are just not used to doing certain things when it comes to evaluation. Even if it's like a very simple set of questions, it actually is your, to point back to like Moment's talk around the need for cultural change. I think there's definitely a cultural shift that needs to happen, and the checklists kind of push you towards behaviors that you might not be used to doing. It's not something you can do like 2 hours before submission. A lot of it actually requires effort and like redesigning how you evaluate these systems and all these things. So I think that that's something that people don't anticipate about checklists, is that they're not just ideally, they're not just things to check off and reflect on arbitrarily, but they actually like shift practice in the field in meaningful ways. And that can actually be really hard to get people to do the right actions in response to the guidance provided by the checklist. So I feel like that's the hardest thing, is getting people to react to the checklist appropriately.
Agree with that completely. I'm working on some sort of ethics type, checklist type thing internally with Mayo right now as well. Part of my frustration is that the things that I care about, I often don't see reflected in some of the proposed existing documentation. As the most direct example, fundamentally, what is being correlated with what? Word frequency co-occurrence, or frequency of co-occurrences is being correlated with ICD-10 codes, like something like that, right? And that would help me enormously to kind of see where I might worry about this model or what I might worry about. The larger point is, so there's this nice sociological work, Arthur Stinchcombe, When Formality Works, that kind of tries to theorize when computer scientists are familiar with APIs. So let me just call them APIs. When API type things work. The idea of an API, application programming interface, is that the user doesn't have to understand how something connects to the underlying thing itself, how the abstraction works, so they can just learn the abstraction and use it. That's what checklists do. I think they're useful and powerful in that. But I always, and this also, Amy Weinkoff has a comment in the chat right now as well. There's a certain elitism to that. And Stinchcombe talks about how you need people who can kind of go behind the abstraction to repair the inevitable ways in which it will go wrong. He talks about architectural diagrams, lots of examples. I don't know how to democratize that. I don't know how to give people more of an understanding of the underlying complexity that we're trying to abstract, because I think that's the much more reliable way by which people can deal with that, can deal with all the ways in which things can go wrong. Until then, checklists are a way to proceed. Sayash, certainly I'm reading some of the things that you put together about how checklists improve performance, and that's convincing. I think fundamentally, I'd love to see this more democratized, but I don't think there's a kind of civilizational human solution to the need for abstraction, at least on the scale of our civilization, and all the flaws that any abstraction will inevitably bring, whether it's an API, whether it's a statistical model, whether it's legal framework, whatever it is.
I love how poetic your answer was, Momin. Mada, any thoughts?
I want to add that, every checklist, I guess, will have its drawbacks and its weaknesses. We have the same with pre-registrations, and there's different approaches. And I think, having different approaches, making it easy, making it accessible is key, right? So it doesn't have to be complicated and extremely standardized, just to initiate this process that was talking about of us, even when we get started in the project, how are we doing what we're doing? If it just sparks that, I think that's already a big step forward. Yeah.
Amazing. I think this is a great point to close off our panel. Once again, thank you so much to all of you for your excellent answers. I'll certainly be thinking about a lot of your points like far from now. So thank you so much. There was a lot of food for thought. To everyone else, I think we'll take a quick break of around 20 minutes now before we begin our third panel. So feel free to sort of jump off the call, take a quick meal or something, and we'll see you all at 2:30 p.m. Eastern Time.
Welcome back, everyone. Our final session is a forward-looking one. We have three great speakers who are going to present ideas for improving the validity of machine learning, broadly speaking. Before I introduce the speakers, I wanted to quickly mention that after the workshop, we're going to have a variety of materials online. We're going to have the talk videos, the talk slides, perhaps transcripts, and also written Q&A from some of the speakers on some of the questions that we didn't have time to get to in the live panels. So all of that will be on our website. So our speakers for the third panel are going to be Jake Huffman, who is a senior principal researcher at Microsoft Research, Jessica Huldman, who is a professor of computer science at Northwestern, and Brandon Stewart, who is a professor of sociology at Princeton. I won't do the full bios as usual. You're going to see the bios in the chat. I want to give as much time as possible for their exciting talks. So we'll start off with Jake.
Great, Arvin. Can you hear me okay? See me okay? Fantastic. Okay, slides coming through?
Yes.
Great. Okay, so thank you so much. I have really enjoyed the workshop so far, and I'm very glad to be kicking off this final session on future paths. I think actually a lot of what I'll talk about has been sort of foreshadowed in other sessions in the workshop, which is just great. And what I'm going to do is I'm going to talk about a recent paper joint with many great co-authors, the title of which is Integrating Explanation and Prediction in Computational Social Science. But I think as you'll see, hopefully the sort of ideas behind the work really apply to ML-based science more broadly. So hopefully that will come through. And so in earlier today, we heard a lot about reproducible work, identifying and fixing problems with reproducibility in ML-based science. And I think it's super important. I'm very passionate about it. I was really glad to hear all the talks on the topic and learned a lot from them. Reproducibility is really this cornerstone. If we don't have that, if we don't have individual results that are credible, it's really hard to go anywhere. And that will require a lot of work and a lot of changes, and be a hard thing to achieve. But I think if we look in sort of a bigger view, it's also kind of a low bar in some sense, right? We want individual results that hold up, but we also want those results to be cumulative and to build up on each other. We want empirical and theoretical results that work together, empirical results that build on each other. And we want those to be able to be turned into useful tools that generalize in practice, as many people have pointed to. So I think this, really sets the stage for what we hope to discuss in this future paths, session, sort of shifting from thinking about the good things that we should be doing more of and away from the bad things that we should avoid. And so to do that, I'm going to lean on a few lessons that, come from thinking about the last decade or so of computational social science, which I think shares many features with ML-based science all up. One of them being that it is an endeavor that has brought together people from different fields that take different approaches to the same problems. And so in the case of computational social science, combined with large-scale data and computation, this has led to a lot of insights about how people behave and how people interact. But I think equally as important, it has surfaced differences in how we do and think about doing science. And I think we should reflect on that a bit in thinking about where we can hope for ML-based science to go. And so in doing that, I'm going to lean on this two cultures analogy that Momin also mentioned, that points out a very particular tension that I think is quite important. So Leo Breiman over 20 years ago called it the two cultures and had slightly different names. And more recently, John Kleinberg and colleagues have sort of restated it as the beta hat or Y hat distinction. And what this refers to is really this idea of explain versus predict. These two different approaches to science. And so I actually, Momin mentioned these in his talk, and I want to dig into them a little bit further and sort of look at this tension, this idea that people view it as one versus the other, either you're explaining or predicting. And I want to try to dispel that and think about them as complements, not substitutes. So both, I think, are important, and neither alone is sufficient. And it's also very, very easy to get them confused. So what I'm going to do very quickly is lean on some caricatures, some examples and critiques, one on each side, to talk about how focusing on just explain or just predict can go wrong, and then present a way of clarifying these distinctions and also integrating the work into, hopefully, something we can pursue going forward. So first, on the explain culture, is this paper about civil war by Fearon and Leighton, probably one of the most highly cited political science papers on civil war, in which they take historical data from many countries over many years, and they fit a regression model to look at the outcome being whether a civil war breaks out in a certain year. And so the key result that you can see here is that they kind of say, look, you might think that the drivers of civil war are ethnic and religious strife. And in fact, we find that it's more the conditions that favor a war, the economic conditions, for instance. And how do they arrive at this? They do this, as I said, through a regression. So they're very much in this beta hat culture. Here is like the main table from the paper. There's a lot to stare at here, but they're showing you coefficient estimates and statistical significance with stars. What does it break down into? That there are a bunch of variables that have to do with religious and ethnic strife, and they show up as not statistically significant. And then there are things like per capita income and other economic variables that show up as statistically significant. And that's the main driver in the paper behind that statement that, that these are the factors that explain civil wars. And one thing that I think is interesting here, and that the folks from the more ML side of things will notice, accuracy is nowhere in the table. There's not any measure of AUC, accuracy, precision, recall. It's not present in the paper. It's not part of the culture, if you will, in the explain tradition. And so this paper went on to get a lot of attention, not just in academia, but really, to literally make headlines in things like the New York Times and get attention from the World Health Organization, in which, people actually followed this in policy guidelines that, you would look for countries with these economic conditions if you were trying to intervene and prevent bad things from happening. And so a few years, or maybe close to 10 years, I think, after this paper was published and was so well known, some other political scientists went back and they wrote this wonderful paper called The Perils of Policy by P-Value, which I highly recommend. And what they did is they said, the authors really, they focused on statistically significant relationships and didn't really look at prediction very much. And so all they did here, and this I think will be interesting for a workshop that focuses on machine learning, and everyone's so used to a train test split. All they did was go back to the training data. They didn't even look at the testing data. They looked at how well they fit on the training data. And so if you take this logistic regression that was built in the paper, and you just do the traditional thing of thresholding a prediction, if it's more than 50% likely prediction that a country is going to go to civil war, they correctly predict 0 out of 107 civil wars in the training data. The good news is that leads to no false positives. The bad news is you don't catch any real examples either. So they lower the threshold. They show if you have a 10% probability threshold, then you can correctly predict 15 out of these 107 civil wars, but you end up with a whole boatload of false positives. And so the conclusion from this Perils of Policy by P-Value paper is, despite all this influence in academic and policy circles, Fearon and Leighton's model is not actually very good at predicting civil war. And so you have to wonder what it really means to say that these factors explain civil war if they really can't predict any of them, right? And so I think that's a caricature on one side of how things can go wrong, focusing on, sort of myopically estimating beta hats and coefficients, and sort of turning a blind eye to prediction. But, we have to equally pick on the predict culture, some of which I think has been done a little bit today, but I'm going to pull up an example that was mentioned earlier and just dig into it a little bit more. So on the predict side, people probably remember the Google flu trends, there was a use of search data to predict, or at least count faster than anyone else could count, how many people would have flu in a given week. And so it uses tons of large scale data. And, in the tradition of machine learning, there's cross-validation and there's out of sample testing. And so, the main result they highlight here is that there's, a 96% correlation over, dozens of validation points that this model performs really quite well. And this was celebrated at the time in the sort of mid to late 2000s as really being this crystal ball to be able to do things that people couldn't do otherwise, using the internet to track flu spread. And so I think by now many people have seen that explicit failure. If you haven't seen it, I highly recommend this paper by David Laser and colleagues, where they talk about how this model kind of totally went off the rails a few years later due to changes in how search works and how searches are logged. And so you had more than a 2x inflation in predicted flu caseloads compared to reality. And in fact, it would have been better to simply use an autoregressive model that didn't use search at all, that just said this week's flu will look something like a combination of last week's and the previous week's flu caseload. And so here you have a case where machine learning is highly celebrated based on all these high dimensional complex data, and in the end actually lose out to a baseline model, for a real world problem. And so hopefully I think this contrast will, make clear that if you live sort of just in the beta hat or just in the Y hat culture, you can really miss things that are important to address if you really want this more cumulative and more useful science. But at the same time, it's sort of surprisingly easy to get these confused. And so, that's part of the contributions we make here in this paper and that I want to highlight in this talk. Really two high-level things. The first is a conceptual framework for categorizing empirical research, and I want to emphasize that this is about empirical research in terms of prediction and explanation. And then in doing so, sort of highlight an opportunity for what we call integrative modeling that combines the predictive and explanatory approaches to give us one of these future paths for how to move forward. And so to do that, I'm going to break this down into sort of a 2x2 that kind of spells out these different dimensions and hopefully clarifies some things that sort of came up in some of the previous sessions and gives us a way of thinking about it, talking about them. So in the rows, what you'll see is I'm breaking down whether we're talking about a specific input or effect versus predicting an outcome. And in the columns, that clarifies whether we're thinking about sort of a passive world or a static world, where we might be, for instance, observing or forecasting, versus one that's changing under interventions or changing for some other reason. So maybe you're acting in the world to do an experiment, or maybe something else has changed in the world that wasn't under your control. And so then I want to think about the four sort of quadrants in this 2x2. The upper left is descriptive modeling, which of course is sort of this cornerstone of doing science. If you can't measure and describe things, it's hard to imagine doing anything else. And so even though it is sort of the starting point, I don't want to underscore how important it is to be able to simply describe what you've seen in the past or present, right? But I do want to clarify that doing so really has nothing to do with causal or predictive modeling directly. And then moving to the right, the second quadrant is what we can think of as the explanatory modeling world. So people often look at particular effects, an individual input. What happens if I do an experiment and I change one input? What happens to the output? And so there's some sort of intervention or distributional change, but it's sort of focused usually on one or two factors. And the problem here is that there are often many factors that matter for a phenomenon under study, and it's hard to be able to compare them if you're only looking one at a time. Contrast that down here with the third quadrant, where the Y hat or predictive modeling world would live. And so I think we've seen, traditionally work assumes that you're sort of passively forecasting outcomes for similar situations to what you've seen already. And so this is sort of thinking about the Google Flu Trends example. it's easy for things to break under changes here. So just because, as Momin sort of spoke to, just because you can exploit correlations to forecast something doesn't mean you know what will happen under unseen circumstances. And so that's where I'd like to highlight this fourth quadrant, which we call integrative modeling, to try to pick that out as something unique and different, and indeed very challenging. But really, it's about predicting outcomes in new situations in the future. And so that is sort of really, I think, the opportunity. There's not a lot of work there. It's hard to do things here, but there are a lot of research opportunities here. And so, if we can think about bringing bits from predictive modeling and explanatory modeling to really do this, I think we'll really make giant steps in ML-based science. Just by way of example, I can relate this a bit to work on information diffusion, some of which I've been involved in. The study of how information spreads has been of interest to people for a long time, and we just haven't had data for it. So even descriptive modeling wasn't really possible until a couple of decades ago. But then you get things like online social networks, and you're able to look at how information spreads, how far it spreads, who shares it, how it's shared, and things like that. There's a ton of interesting work there just to be done in description and measurement. There's also great work that was done in terms of identifying specific inputs or effects. And so this is work by Jonah Berger and Katie Milkman, where they look at things like how does the emotional content of an article affect the popularity of that article? But they focus very specifically, sort of in the Fearon and Layton style, on these coefficient estimates, and much less so on prediction. There's also a ton of work in the predictive modeling world on things like this, where people try to forecast popularity, often finding that it's hard to do, but in a passive sense, right? There's no sort of intervention or change that's happening. They're simply trying to say, if I were to passively watch, what would happen? And so I think the challenge here for this example, just to make it concrete, would be to say, what if you actually use these models to try to design new content and predict its popularity? That would really represent this big leap in integrative modeling. And I think it's kind of daunting, but we should at least aspire to it and identify it as something uniquely different than in these other quadrants. And so that's really the first suggestion, which is look to sparsely populated quadrants for research opportunities, specifically this integrative modeling quadrant. Test how existing methods generalize to previously unseen circumstances, both cross-domain and out of distribution, as several people have pointed out earlier today. And also develop new methods that iterate between prediction and explanation, predictive models to critique explanatory ones and vice versa. And so there's some very nice references I would encourage people to check out in the paper from folks like Tom Griffiths and Susan Athey and other colleagues who have really worked on these sorts of methods. In terms of best practices, one very simple thing is to label contributions according to which quadrant they fall into and to the granularity of claims, because it's very easy to be sort of confused, I think, both for the people doing the work and in communicating the work as to whether we think we're achieving a predictive, an explanatory, or an integrative kind of result, but also to specify the level at which this happens. Are we talking about a directional hypothesis? Are we talking about predicting individual or aggregate outcomes? Is this a lab study or a field study? What's the time scale? These sorts of things. I think having these more explicitly labeled would lead to a more coherent conversation around many things. And then also, as several other people have pointed to, standardizing open science practices and best practices across disciplines. So we can look to things like explanatory modeling and see that pre-registration has really helped there in terms of clamping down degrees of freedom, and ask what that would mean in terms of predicting modeling. And so that's something I've been thinking about with colleagues. Jessica will talk a bit about that, I think, in the next talk. But also things like a common task framework for explanatory modeling. That's something that's been really helpful, having all these competitions and leaderboards in the machine learning world, and think about how that could be ported over to causal inference, which there's been some really interesting work on. And so with that, I just want to acknowledge my many great co-authors without whom this paper would not have happened, spanning from fields like computer science and machine learning, to psychology, political science, and communications. And I will leave you with a reference to the paper, a short link here, and just highlight again this message that explanation and prediction are both important. We should evaluate our claims in terms of both, and hopefully this will lead us to more replicable, more cumulative, and more useful science. Thanks.
Thank you, Jake, for that wonderful talk. Let's go to Jessica next. I'm Professor Jessica Hallman from Northwestern, and you'll see her bio in the chat.
Cool. Thank you. Let me just get set up here. Okay, you're seeing my slides, correct?
Yes.
Great. Okay. So yeah, thank you very much for inviting me. In many ways, my talk will be sort of a continuation of Jake's slightly different angle. So despite this explanation prediction divide, we've seen some broad strokes analogies between this ML reproducibility replicability crisis, as it's called, and the bigger replication crisis that's affected social science fields like psych. The question I want to pose today is, how well grounded are these comparisons? What's really new and unique about the problems we're seeing in ML versus a recapitulation of known issues when people are trying to learn from data? I think especially as we move toward integrative modeling, which I'm a big fan of, it becomes more important to understand the broad range of ways that we can be fooled when doing inference with data and how they relate across this so-called explanation prediction divide. And so the title of this talk comes from a recent paper where co-authors and I drew on hundreds of papers, literally, on these two so-called crises with the aim of systematically comparing, what's thought to be the causes of the crises or failures in learning, as we could call them, and to see, are there any common causes and perhaps consequently common solutions. So before I jump into some of our observations, I want to first walk through what's different between sort of the very typical learning pipeline. So this will be kind of a reduction in a field like social psych versus a field like ML. So in social psych, the goals for doing inference from data are typically to test some theorized association between variables that the researcher has in mind. Perhaps there's a certain direction they expect the effect to be in. For instance, speculating that listening to cheerful music will improve people's ability to do math. An experimental probe is designed to collect data, typically a human subjects experiment. This will capture a slice of some subset of the larger ground truth set of relationships that affect the outcome of interest. And researchers typically measure or attempt to control for only a very small subset of this very large, potential number of variables that influence the phenomena. They'll then often turn to low-dimensional linear regressions to analyze the importance of different predictors of covariates. They might judge, goodness of fit using something like R². And in order to actually, fit the models, I should also mention that, this is often done through analytical solutions. So they're not using any sort of, stochastic algorithms. They're using maximum likelihood estimation, often analytically, and then, looking at things like goodness of fit. So the results of this process are then typically communicated in the form of what some have called stylized facts about human nature in general. Things like, well, listening to music improves math ability based on some effect we found in our experiment. So in machine learning, a researcher might start with instead a hunch about how to improve the state-of-the-art performance on some task or benchmark, perhaps about the predictability of some particular outcome. Maybe they have a new training technique or optimization trick that is sort of, that their hunch is based on. And they might curate data or just find an existing data set associated with a task and learning metric, which we would call a benchmark. This data set typically includes a much larger range of ground truth and more recorded variables than a field like psych would, but it still might be biased in certain ways. For example, if it's not representative of the population where the model will be deployed. The researcher chooses a model representation. This could be, a neural net, a decision tree, et cetera. Choose your favorite. And then they also choose an objective and optimization approach, which unlike in psych, where we use, these plug and play analytical solutions, in ML, we're typically dealing with dynamic algorithms like gradient descent. Solutions are often evaluated in terms of their predictive accuracy, and this can be captured in various metrics. Results are communicated often using point estimates of performance, along with claims often about what has been achieved in terms of, beating state of the art on some task, which is often a kind of a human-like task, like reading comprehension, visual question answering. So this is what success kind of means. So what it means to evaluate our research hypothesis or hunch that we start with in order to output some interpretation at the end in the context of some specific learning pipeline really, I think, requires understanding what it means to choose model representations and to fit models. And so I want to talk about for just a moment about how threats at these stages of the pipeline differ across the two fields I'm using, social psych for explanatory and ML for predictive modeling. And then I'll get to some similarities despite some of these obvious differences. So to select a model representation in a field where we care about explanation, a primary requirement for good inference is that the function we learn captures the true structure of the data generating process. So if this true data generating process lies within the space of models we search, which we call an M-closed situation, then we can fall back on this, the guarantees associated with the conventional inference technique we're using, for example, maximum likelihood estimation to find the best fit given a regression equation. But it's well accepted in psychology that when we're trying to explain human behavior, the actual ground truth process that produces, someone's math performance or someone's political attitudes is going to be way more complex than we can model and describe through our relatively simple experiments. So instead, we need to think carefully about what variables go into our low-dimensional approximation of the true data generating process in the form of our regression equation here. And this process of selecting variables and selecting a functional form in typical social psych is generally driven by human hunches as well. So we see, few rigorous attempts to carefully analyze how good the choice of variables that we decided to measure and include in our regression are. This is problematic because authors then don't hedge at all in their interpretations to account for potential model misspecification. So, the standard interpretation of a regression coefficient is something like, for a 1 unit increase in X, I see a whatever unit increase in Y. And this interpretation is accurate if your model is well specified. If it's not, and you haven't even bothered to sort of test for that, then what you're saying may or may not probably actually is nonsense. So this is a problem. In ML, though, the conventional belief is that now we only care about prediction. We can throw away any cares about whether what we've learned captures the true process. However, we see an increasing amount of pushback in recent years on the inappropriateness of this IID assumption in general. So distribution shift is ubiquitous. We've talked about this already in the workshop. And it's not clear, how much longer we can avoid taking steps toward modeling the data distribution, or at least thinking about this true data generating process. I'll say more on this in a moment. Another common theme that runs through ML issues we see at various points in the pipeline involves a lack of theory around some of the latest high-performant model architectures. So we see some critics concerned about, how practice in areas with high visibility sort of problems like language modeling and vision has converged around these large conglomerations of models that are hard to theoretically analyze. For example, high dimensional representations are trained without supervision on huge data sets, and then fine-tuned with smaller amounts of domain-specific data for certain tasks. And they work quite well. This is sometimes called foundation models or fine-tuning, but they become much more popular, but we can't quite explain their performance or theorize about it. And so the problem is in social psych, we tend to ignore theory and model choice, whereas in ML, there are many cases where we actually don't even have the theory yet. If we turn to model-based inference or model selection and evaluation of that process, in social psych, the convention is to sort of treat model-based inference as a black box that takes in your data and spits out answers. However, many of the issues that we see being called out in ML reproducibility stem instead from this big difference where there, fitting your model involves optimization, which is typically dynamic, probabilistic, rather than deterministic, meaning that the solution you get after fitting your model can differ if you rerun the optimization process, and the performance can be highly sensitive to configuration choices like hyperparameter settings, things like the learning rate, computational budget, et cetera. So to some extent, researchers are also still figuring out the properties of these optimization algorithms, including, for instance, the way that gradient descent can be biased towards simpler solutions. And more broadly, the ways over-parameterized models, those that have more predictors than data instances that they trained on, can seem to defy this classic bias variance trade-off. So in ML, there's a lot of theorizing happening around what's going on in phenomena like double descent, where a model kind of perfectly memorizes the training data, but then if you keep training it, the test set error continues to go down, which is very hard to explain in our traditional analytical frameworks. So we have to tread cautiously when interpreting then what aspects of a learning pipeline contribute to what properties of a solution, because there's a lot we still don't understand. So you can see our papers for a detailed breakdown of cited issues at each stage and detailed citation information for some of these things that I'm talking about. But now I want to turn to a few themes that we see in common. So, first of all, I just spoke on optimization in the standard sense. We could also say there's implicit optimization going on to perhaps a great extent in both fields. So the garden of forking paths refers to making decisions after seeing one's results. And this has been a key concept in the replication crisis in social science, where authors figure out which analysis decisions give them the best story or the most significant results. But this means that assumptions of the model fitting process or statistical testing processes that they run do not hold, and hence their interpretations of the results are inaccurate. In ML, research progress is frequently defined by beating the state of the art on some tasks. And so researchers might rerun parts of a pipeline repeatedly, do some cherry picking of what to report. This can also impact, what performance measures they decide on, which runs of the model they decide to report, which baseline approaches they decide to compare to in order to make their results more impressive sounding. So what do we do about modeling decisions that are conditioned on seeing the results? Like several other speakers have already mentioned, I think we can cautiously proceed here in taking some inspiration from psych reform. In particular, the idea that problems related to conditioning on the data or on the results can be addressed when analysts specify a priori certain aspects of their goals, the data collection process, the fitting process, et cetera. So pre-registration has been a hallmark of reform in psych, where we're pre-specifying hypotheses, when we're going to stop collecting data, et cetera, what model-based comparisons will do. In ML, I really think this needs to look different. As Jake mentioned, we're currently doing some work trying to figure out exactly what do you ask people to pre-specify and when do you ask them to do it? Is it all, right at the start of the process, like in psych? Probably not. And so, I think it's hopeful that something like pre-registration could help with some of these problems in ML. There's also registered reports, which attempt to guard researchers from the situation where, they've posed some interesting research question, but then they get negative results and they feel like I can't publish, I didn't, beat the state of the art, et cetera. So there's already been some discussion. There was a workshop, I think, at one of the big ML conferences on registered report. And, I think it's a good idea to pursue if, your research questions are really about things like how do different learning techniques compare or do on some domain specific problem. And you don't want to have to worry about, being in a situation where you're incentivized to cheat. But one important point that I haven't heard yet today that I think often gets overlooked in these discussions of reforms and of problems themselves and why they're caused is that we really need to be careful and rigorous when we're trying to theorize about what is causing certain problems and how we're going to fix those problems. And this is sort of a meta lesson we can take from the psych reform crisis. So to take pre-registration as an example, for instance, this is something that has been proposed and, many people have adopted. And of course, it has led to, more reproducible science or more replicable science in various ways. But some critics have argued that sort of philosophically, if we take a close look at what we expect under pre-registration, we're saying, things that don't always make sense about the need or the importance of the time at which someone does something. Many of these debates often come down to, what do we expect the analyst to already be capable of? And then, the reforms are just about prompting them to document versus where might the reforms be actually doing the work in a way that doesn't require the analyst to already have the solution somewhere available in their mind. And so I think it's really important, and there's a great paper by Berna Debezer et al. About how to be rigorous in identifying problems and theorizing about how to fix them. We also see as a second high-level theme what we could call implicit optimism manifesting in these fields in the form of sort of a tolerance for irrefutable claims by convention. So in social psych, there's this tolerance for what have been called weak theories, as Paul Meehl, a psychologist writing about replication issues in the 60s, called them. We typically think of hypotheses as these associations we expect to see. We don't see in typical social psych mechanistic accounts that would actually have testable implications. So we could know when do we actually reject this theory. And so combined with this sort of inverted use of null hypothesis significance testing in psych, where basically, researchers take the rejection of a straw man null hypothesis as confirmation of their preferred theory, we have this situation where it's actually much harder to refute a hypothesis than it would be to just support one. So that's a problem. In ML, on the other hand, irrefutable claims manifest as a confusion between what's an engineering artifact versus what is a scientific claim. So I think we should see the presentation of achieved performance metrics of some pipeline in an ML-based paper as more possibilistic than probabilistic. We can think of it as, well, this tells me that there is a situation in which this accuracy can be attained, but this is not necessarily expected accuracy of this method overall. The problem is that in writing papers on results, authors often claim to have made scientific progress on some human-like task, and they often attribute the better than state-of-the-art results to parts of the pipeline that were their novel contribution. Though, as we discussed, these attributions can be wrong when major sources of uncertainty or noise are unacknowledged. So here, I think better acknowledgement of the difference between engineering and scientific goals is a start. So when we're evaluating a specific pipeline with some application in mind, what good performance means for that real world application is what matters. If we're trying to advance the state of the art in some field, we need to have a stance on how the setup we used, including what benchmarks, how we define the tasks, et cetera, maps to progress. And we need to be careful in leaping to assumptions of human-like learning just because we see, performance that seems human-like on some task. I also think better uncertainty communication can really help. In consuming and writing research papers, there is a natural human tendency to want to suppress uncertainty in favor of binary information. Things like, yes, we saw a difference, or no, we didn't, or yes, the technique did do better than the baselines. And we have to be skeptical for this reason in consuming papers, as well as in writing them. Because when uncertainty isn't expressed, it just isn't science. So it's not even good engineering. So instead of point estimates of performance, we should be reporting expected accuracy and its uncertainty, which is a function of factors like how big our test set is. But here I think it's safe to say that statistical significance testing as a way to quantify this uncertainty, as some authors have already suggested for ML, is not the answer. It promotes dichotomous thinking. Instead, we should be discussing the size and uncertainty of a difference in performance between prior state-of-the-art or baseline. We should be considering sources of uncertainty along the way, and whenever we can, trying to propagate those into our final results estimates. So, some sources of uncertainty or noise we can see clearly, but we often tend to ignore things like disagreement in labels among annotators, or sometimes we have stochastic processes built into the learning method, as in reinforcement learning. So we really need to try to propagate these down the pipeline. And this is not necessarily easy. So I am heartened, though, to see there has been a lot of activity recently around uncertainty representation for ML to try to build sort of a foundation for doing this better. At the highest level, I think we need to shift our perspective of what we're doing when we do ML-based science. It isn't about yes or no questions. It's about understanding, under what conditions certain approaches excel versus fail. That might mean different data sets, different instantiations of a learning pipeline, but we want to explain the differences. So if you find that your results differ than something that's been reported elsewhere on a similar benchmark or problem, make trying to understand why that is part of your paper rather than just ignoring it. Finally, another common source of disconnect is latent expectations about reality that conflict with statistical facts. So we see this in both fields. So causal attribution or explanation using constrained model spaces is fundamentally challenged by what Paul Meehl called the crud factor. This is the fact that basically everything is correlated with everything else. Human behavior is a result of these many complex relationships. And so when researchers set out to isolate effects using these simple regression models, they're ignoring this reality. Similarly, we see things in the literature, such as, this implication that, well, there must be many small interventions, that somehow have large effects on the same class of outcomes, things like political behavior, et cetera. But if we think about this, in a statistical framework, what we expect of correlated effects simply would not allow for these kind of many, small nudges having big effects. Like it's just not possible. In ML, we use this crud factor to our advantage, but IID data is a fundamental assumption that we know breaks down and is often unrealistic. So one way that I like to interpret this breakdown is as a failure to consider important human expectations or inductive biases when we approach learning. The models often have learned and they're even generalizing well. It's just not in the direction that the human is expecting. So ideas of underspecification and model multiplicity get at how an ML pipeline can produce many solutions that are identical in terms of performance on the test set, but which break down at various different rates when we probe their performance along dimensions that humans consider important, things like fairness or bias. And so failures like these suggest to me that the future of ML will most likely involve more steps towards explanatory modeling, like Jake was suggesting, or embracing integrative modeling. Specifically, if models are failing because they aren't generalizing how we want them to generalize, then we should be devoting more attention to eliciting human domain knowledge about what it means to fail versus to generalize well. For instance, in the form of what dimensions do people think this degradation of performance will be meaningful on? And then we should be, importantly, integrating validation tests, constraints on our learning processes based on this knowledge. There's going to need to be a lot of exploratory work to do this well, to understand where human judgment and expertise can really be useful. But it's a place where I think there's a lot of promise, in particular, because one of the most successful aspects of ML methodology is that when something's lacking in our solution, we can often integrate that as a requirement into the learning problem. So there's hope, but we do have to put more attention to explaining what it means to learn successfully. I'm going to wrap up there. You can see our paper for more kind of points as part of this discussion and many more specific factors. So thank you.
Thank you, Jessica, for that exciting talk. Our closer today is Brandon Seward from Princeton University. I'll turn it over to Brandon, and you'll see his bio in the chat.
Great. Thank you so much, everybody. So I'm going to be presenting a little bit today, drawing on this paper, What is Your Estimand, that I did with my graduate students, Ian Lumberg and Rebecca Johnson. Ian is now an assistant professor in information science at Cornell, and Rebecca is an assistant professor at Georgetown in public policy. And the core claim I'm going to make in this talk, extending a little beyond the paper, is threefold. So the first I'm going to say is that prediction as a term is really overloaded, which is an idea that we've sort of heard multiple times today, said in different ways. And I'm going to argue particularly that we need to say very specifically what quantity is being predicted and for whom. And that this is going to have huge implications for what counts as leakage, right? Because for certain kinds of tasks, the exact same thing may or may not be leakage. The second thing I'm going to argue is that both reproducibility and replicability require falsifiability. We need some way of saying that a thing's right or wrong, and that itself requires an unambiguous, cleanly stated goal, which we, in fact, don't have the vast majority of the time. And I'm going to argue that the framework that we give in the paper of theoretical and empirical estimands can be a useful way to communicate about what our evidence is and how it relates to the claim we're making. So let me just jump in, though, with by saying a little bit about like what we mean when we say, what is your estimand? So the estimand is like the purpose of the statistical analysis. It's like the parameter we're trying to estimate. And I'll give you a sense of like how this tends to play out in the social sciences. So someone will say, well, we took a data source and we estimated a beta 1 in a regression, right? As just as sort of Jake and Jessica both suggested, right? These like linear regressions are very, very common. And under this sort of notion, we could interpret beta 1 as our estimand, but that sort of assumes that this model is a true model of the data generating process in the sense that Jessica was just talking about. And so we might then ask this person, well, what if this model is wrong? And they say, well, the model, it's just an approximation. And so we say, okay, so like, what is that coefficient going to be an approximation to? And they say, well, it's something, I just haven't said what yet. And then you say, okay, well, is it, at least a good approximation? Like, does it have known properties? And at that point, you're in like an epistemological crisis because we haven't pinned down what the goal is outside the context of the approach we're using to get to that goal, right? We've just said the thing we're doing is running a regression and not what we're actually trying to estimate. So I'm going to give you an example of how this cashes out in like a particular example in the social sciences. So this is a paper by Roland Fryer, an economist at Harvard, about racial differences in the police use of force. And what he finds in this paper is that amongst white and Black civilians who've been stopped by police, they are shot by officers at equal rates. Okay? And he called this finding the most surprising result of his career. And it got breathless coverage in the news saying that, new evidence shows bias in police use of force, but not in shootings. Heather McDonald used it to support her view that systemic police racism is a myth. And The Guardian talked about how this shows that there's no racial bias in police shootings. So the claim here, the evidence that we have here is that police use lethal force at the same rate against Black and white civilians who are stopped. And the claim that's being explicitly made by the media, implicitly made by Fryer in the paper, and I think explicitly made by Fryer in the media, is that police are unbiased in their use of force. But then evidence and claim don't really line up. And we find out when we sort of look at the causal structure of what's happening. So the core idea here is that being perceived as Black leads to the application or not of use lethal force by police. But the issue is that there's this bit in the middle that we only have data on the people that are stopped by police. And we know from a large previous literature that being perceived as Black can increase your chances of being stopped by the police. Of course, it's not the only thing that can get you stopped by the police. Also, the most sort of obvious thing is like criminal activity, which is also connected to the likelihood that lethal force is used. So let me just explain, though, why looking only amongst the people who are stopped causes this huge problem. So imagine that we just simplify the world to 6 people who are white and 6 people who are perceived as Black. And we're going to say that the rate of like those committing crimes within these 2 populations is the same. Okay. And so police stop all of the people who are white who are committing crimes. And so we just like emphasize that by putting these like kind of black bars around there. Okay. But because of racial profiling and who is stopped, that we are both stopping all of the people who are perceived as Black who are committing crimes, but also people who are not committing crimes. Now, when we look at just the people who were highlighted here, and we say that police are applying lethal force with equal rates to just these highlighted groups, that equal application of the use of lethal force no longer looks like it's the police being unbiased. It actually looks like it's the police being extremely biased. And so this is the nature of the problem. So this is a case of what's called causal sample selection. And the idea is that, like, amongst those who are actually stopped, the white civilians may be more dangerous because of the sort of nature of how people were stopped. And so Fryer, of course, responded to these critiques that had been made by Knox, Lowe, and Mumolo, and another one by Gerloff and Hockman. And basically in the response says, well, that's never what I was claiming at all. And in fact, the sort of long form of the response, he says, we use the term racial differences 114 times in lieu of the more prescriptive wording, racial discrimination. We use the phrase conditional on an interaction 20 times. I'm not sure how many more ways we would have needed to caveat our results to satisfy the critics. But actually, from our perspective, the caveats are actually the problem. There's no clarity about like what the estimand is, just the procedure that's being used. And so because Fryer is basically saying, no, I just described the mechanical procedure I went through, there is this gap between what's methodologically being done and what our sort of interpretation of the results is. So we think that you should be specifying your estimand outside the context of the specific model, and in basically using 2 things. So first, there should be a unit-specific quantity, and that could just be some observed information or something unobserved, like a causal effect at the unit level, and that this has to be aggregated over a concrete, like well-defined target population. So what was Fryer's estimand in this kind of setup? Well, the problem is that it could have actually been a lot of things, and this has been the basis of some disagreement in the literature, trying to pick out actually what's the right way to talk about policing. But we need a sort of more explicit argument in order for that discussion to be productive. So I gave you some claims and an example. I'm now just going to walk you through our framework for estimands and sort of point you to the paper for more details. And then I'll go beyond the paper to talk a little bit about some questions that I think this raises for prediction. So we see the research framework as sort of starting with a theory or a general goal. And the thing that almost always does actually get reported in social science articles is like the estimation strategy, like mechanically what people did. But there are these parts we think need to go in the middle. So first, we think people need to specify their theoretical estimand, that is their sort of goal, potentially in terms of unobservables. And then the empirical estimand, which is the actual quantity they're estimating that is in principle observable. And then what they need to do is sort of set this theoretical estimand and link it to their general goal. And then they need to link this theoretical estimand, their sort of their goal that's possibly like counterfactual, possibly unobservable, to something we can actually observe in the data, that is the empirical estimand. And then what that will let us do is go in and learn from the actual data itself, go in and estimate using regression or machine learning or any of these other tools. And in fact, when we were writing this primarily to social scientists, part of the point was to explain how you could integrate machine learning into your workflow. That once we have set the theoretical estimand and we have linked it to the empirical estimand, it's now actually just a prediction problem. And so that's where machine learning starts to shine and we can use it effectively. Then, of course, this kind of links back and, evidence should point to new questions. This should all be cumulative. So I'm going to walk through each of these steps with just a little bit more detail to kind of make it a bit concrete. So setting the theoretical estimand is a thing we do primarily by argument. And as I mentioned, it has two components, this unit-specific quantity and the aggregation over target population. And this can be as simple as something like the employment rate, so like the average overall US adults, where we're just measuring whether or not an individual person is employed, or something more complicated where the unit-specific quantity is like a causal effect, like the difference for that same individual if they were given job training versus not given job training. So once we've set this, we have to link that theoretical thing that might involve unobservable stuff, either because of like missing data or because it's a causal effect, to something that we can actually observe, right? So this is that same statement about job training written again. And the core problem, the fundamental problem of causal inference is that we don't get to observe both this piece and this piece. That is, any given person is only employed if we only get to see them if they're enrolled in job training or not. We can't see both scenarios. But what we do is we link that to something based on observable data. So for example, if we had run a randomized experiment, we can write down a clean set of assumptions that links that unobservable quantity to just the average among people assigned to job training and minus the average of people assigned to no job training. And this process is called identification, and it applies not just to causal inference, but to how we use missing data, how we think about like domain adaptation to different populations. Now, in practice, these empirical estimands are often going to look something like this. They're going to be like relatively complicated because we think there's only going to be some correspondence within particular strata of covariance. And so it may be written as this is here as a difference of two conditional expectations. So that's the part where estimation comes into play. We may want to estimate these conditional expectations by just using a regression or using a machine learning model or something like that. Then we just plug in those estimates and we can get our estimate of the result. And because of each of these steps in the chain, we're going to be able to connect this back to our original theory. Now, we do this for a bunch of different examples in the paper. This is just our table summarizing all of them. And we also establish that, at least in the top journal in sociology, but I suspect more broadly in social science, no one's really being clear about what their estimands actually are. And so the fact that we can't back out what someone's goal is makes it actually impossible to meaningfully think about like replicating those results because we don't know what they were intending to capture. And so they can always do the two-step that Fryer did of saying, well, no, I was actually just intending to run this particular regression. So I'm going to raise two questions that I think this sort of framework raises for prediction that's kind of beyond what we talk about in the paper. And the first is I'm going to think about the distinction between prediction in the same population, a new population, or a counterfactual population. And then I'm going to suggest that we should be asking whether or not our prediction problems are more like predicting cats or more like predicting people. And I'll walk you through what I mean by that. So by the different populations, I'm going to give an example of verbal autopsies, which is a way that the World Health Organization gets mortality, a cause of death, basically, for people that die outside the context of hospitals. And the way this works is that, if someone dies outside the context of a hospital, a survey taker goes to their home and they ask them a list of questions like, was your loved one experiencing fever? Did they clutch their stomach? Did they have a headache? And then we take those symptoms and we use them to predict the cause of death. So it's a kind of classic machine learning kind of problem, right? We've got a list of features, we predict some outcome. But the issue is the places that we have labeled data, the places where we have the cause of death are very different than the places where we need to do the prediction. We have cause of death in hospitals where doctors are able to certify cause of death, like in this urban hospital in Uganda. But we need to predict, for example, in rural hospitals or possibly even rural areas that have no hospitals, where the causes of death, the presentation of those diseases, all of these things can be very different, which is essentially just like a domain adaptation problem, but it's something that we need to be really, really cognizant of. So this leads to sort of three stylized ideas. Cases where you're doing prediction in what is effectively the same population. So this is like predicting a cause of death in major hospitals in this case. Prediction in a different but real population. So that's like predicting causes of death in rural hospitals or rural areas without hospitals. And then finally, we can imagine prediction in a counterfactual population. That is the case in which it's actually never really observable because it's predicting the cause of death, for example, if we were to intervene, but we can never both intervene and not intervene. The second thing that I'm going to say we should think about is stylizing, like what type of prediction task are we doing? Are we predicting cats or are we predicting people? So by predicting cats, I really just mean the kind of canonical computer vision task of object recognition, where we take in the pixels of an image, we try to say, is there a cat there? And broadly speaking, of course, you can pick at the details of this, but like broadly speaking, the key feature of this is that by construction, we know that the features available to us, the pixels in the image, tell us that there is a cat there. If these cats were hidden behind this dog such that they were not at all visible in the picture, even though the cats were there when the picture was taken, we would not describe it as there are cats in the picture, right? That part of what it means for there to be a cat in this picture is to say that we have the capacity to predict it and that there's only one right answer. Now, an extreme opposite kind of situation comes from, for example, the Fragile Families Challenge, a mass collaboration run by Matt Salganik, Ian Lumberg, Alex Kindle, and about 100 plus other participants, in which they tried to predict the outcomes for kids at age 15 based on data up until age 9. And so they're predicting outcomes like whether or not kids experience material hardship, what their GPA would be, whether or not their parent would be evicted. And what they find is that applying tons of different machine learning methods, broadly speaking, just doesn't do that much better than a very simple, like 4-variable baseline. And part of why that is because at age 9, there's no guarantee that any set of features is going to pin down what these kids are going to experience. And in fact, all we really can meaningfully do in a context like that is estimate the distribution, that is the share of people that will experience material hardship. But as soon as you're thinking about it in those terms, you're estimating a distribution, it starts becoming super, super important what the population is that we're trying to generalize to, which brings us back to sort of the previous slide on this idea of what population are we targeting? Where is this machine learning algorithm going to get deployed? What kinds of people are going to run through it? So I think that these are very different tasks. And because machine learning often starts with this kind of example, we have the problem that, people sort of assume everything's like that. So that's kind of what I'm covering. Prediction is really overloaded. We need to be more specific about it. We need to be super clear about what our goals are, or replicability and reproducibility can't really mean much. And I think that the theoretical and empirical estimands language we develop in the paper may be a useful way of talking about some of these things. So thanks so much, and I'm looking forward to the discussion.
Wonderful. Thank you, Brandon, and thank you to all the speakers in this session. I should say that even though I've heard each of you speak about these topics before, I still ended up learning a lot from your talks. So I really appreciate that, and I hope our audience learns a lot too. We're going to take a 5-minute break. We're exactly on time. We're going to come back at 3:35 for the panel discussion. And again, please put your questions in the chat. I'll start off with 1 or 2 questions of my own, and then we'll go to the audience questions. See you in a few minutes, everyone. Welcome back, folks. Thank you for the questions in the chat. Please keep them coming. Are all of our speakers here? As soon as we confirm that, I'll jump in with some questions.
Yep, I'm here.
Yep, also here.
Okay, awesome. So this question is for everyone. I'm wondering, we've talked about a lot of problems throughout this workshop, and that's important, of course, but considering that this is the final session, perhaps we can strike a more optimistic note, thinking about the future. So I was wondering if each of you could give a vision. It's not necessarily a prediction, but your wish for the future of machine learning, where things are a lot more rigorous than they are today. What would that look like? And while you're doing that, feel free to reflect on and build upon each other's talks as well. So perhaps we can go in the same order as the talks, Jake, and then Jessica, and then Brandon.
Cool. Yeah, I love that question. I think that actually, just thinking about Jessica and Brandon's talks, I think they both offer like a really great vision for what this could look like. So I think Brandon's talk kind of points to this idea that we're all trying to learn from data, and that we need to be explicit about the goals that we have in doing that, separate from the methods that we go about in achieving those goals. And those methods do look really different, especially when you start to think about all of the sciences. And so the way we sort of formulate hypotheses and search over them and do experiments might be very different, as sort of Jessica pointed out, between certain disciplines like social sciences and then computational fields like machine learning. But we really need both. And I think if we can be as rigorous with our evaluation of reform for doing these sciences as we are with the science itself, and as Jessica pointed out, not just sort of deciding that something worked over here, so it's going to work over there, or it achieves everything under the sun. I think if we can get down to actually really evaluating these things to figure out what makes for doing good science, that'd just be fantastic.
Yeah, Jake's answer was great. I think something I could, touch on a little more, besides the sort of need for rigor in defining what's happening here and then trying to incorporate that back into the pipeline. I think this idea of we need more explicit integration of human domain knowledge, which I think is not just new methods, but is like sort of a whole enterprise in itself. Like a lot of these problems we perceive, in my mind, are like a mismatch between what we thought we were doing and what is actually happening, or what we thought was being learned, or how it was being learned and what's actually happening. And so I think, on like a first step is sort of understanding human expectations about prediction and learning, and where things go wrong, and then working on understanding where human expectations and domain knowledge can be useful here, like some of these like contextual dimensions that humans have knowledge of. I think we need to understand where those where that like sort of expertise or where those hunches are useful versus not, because I think we should expect that just always putting in a human in the loop is not always like gonna lead to performance benefits. I think in general, sort of bringing in the human. I thought some of Brandon's points were great in sort of that respect of like, we need to really understand what our goal is, what we're claiming, in order to, later figure out whether it went wrong or not. Like we're still in this area where we can't even tell because we haven't actually made a lot of things explicit.
Yeah, this is great. Thank you. I really love the other presentations. And I think one of the themes that you get both from the ones on this panel, but I think some of the other ones as well, is that this is just really hard, right? I mean, like, and I do think that there's a sense of like, we need to like recenter the expectation that it is hard to learn things about the world. It's hard to be explicit about what we're trying to do. It's hard to do it well. And I think Jessica raised a really good point in the presentation that like making policy around this is really hard. I think it's very easy to, part of what makes the question that Arvin's asking here so like deceptively difficult is that we can say, well, we would hope these things would be better, but saying like what you would do to get there is just profoundly difficult. And I do think, as has been raised by many people, it ultimately is going to need some change in the incentive structure, because ultimately it's just too costly to do some of these these things if like not everyone's playing by the same rules. And that's something where, I think psychology has done a really good job of actually really rapidly in the scheme of things restructuring the incentive set. But I think there's still a sense in which like what I would love to see both in the social sciences and on the ML side is an environment where people are replicating the findings that are most important, and that having your work be replicated is like a gold star in your CV that you're excited about, right? Because it meant that someone thought it was important enough of a finding to spend the time to go acquire extra evidence. And so you're incentivized, if that's all that matters, is like, are other people replicating your findings and finding that they hold up and useful in other contexts, then that incentivizes you to do the kind of work that's going to hold up in other contexts. And unfortunately, I think the issue is now that incentive structure isn't quite there, but possibly going forward.
I love that. All great thoughts. Thank you so much. I'll throw in a couple of my own questions, and then we'll go to the audience questions. Jessica, when you were talking about getting away from dichotomous thinking where a claim is either true or false, that really resonates, and I've seen Andrew Gelman also advocate for that. I was wondering if you can talk about what some of the downstream effects are going to have to be, because when I read papers, I assume this is true of many of us, we're still looking for claims to be either true or false. So how should we change our behavior as consumers of research and as teachers? In the classroom, again, we have this bad habit of presenting most things in this binary way. So I was wondering if you, and anyone, but especially Jessica, could talk about what are all the other things that need to change in order to make this change possible.
Yeah, that's a great question. I think we have to one simple thing is, never try to interpret the results of a single paper without looking at like the broader context, like what's the work in this area, like how are they defining things? I think often, we end up in these situations where there's a lot of unquantified uncertainty that we just kind of ignore. Like when we write papers, when we read papers, like this conflicts slightly with what someone else found. And we're just not going to worry about that. And we're just going to cite this paper and like forget about that one. So I think just really stopping ourselves when we're reading into a certain paper. I've thought a little bit, and I didn't present anything on it because I think there's so much complexity already in ML that I'm not sure how this would be implemented. But the idea of like multiverse analysis or just like much more sensitivity analysis, I think it allows authors, to still write a paper that has some clear point, but to like, if you're actually doing a lot of sensitivity analysis, or multiverse is this idea of like, I'm not just going to do, I'm not just going to set this hyperparameter in just this way. I'm going to like try doing it multiple ways here. Anywhere I have an important decision point in my analysis process, I'm going to like multiplex a little and report on all of these different, paths. Like, it makes it harder to write a paper. You can still write a paper that, but it suddenly, in order to write a paper that has a clear claim, you really have to understand what you're dealing with. And so I think in general, like sensitivity analysis would be wonderful. And then just this skepticism. I think this is one of, to me, the hardest parts of science reform is just that we cannot encode so much, information necessarily to memory when we read a paper. And so we really need to get better at sort of like crafting, accurate and uncertainty sort of sensitive claims in our papers so that uncertainty is baked into the message. And so some of what I said as well about, let's make trying to understand the differences part of the research goal rather than sweeping them away. So, but yeah, that's a super hard thing. It's a good question.
Thank you. Anyone else?
Yeah, I'll just add to that I think part of what goes with the dichotomous thinking is like a universalistic kind of thinking. This goes to like pushing into Jake's like the second row on his 2x2 table of like, we should be saying when we would expect our theories to break. And in some sense, like that would ideally be normalized, right? Like if you present a theory, it doesn't really mean anything until you say, this is the context in which I think it won't work anymore. And similarly, Jessica talked about with methods, I think it's the same way, right? Like we present a new method and we say it's great, but we should be showing like, what's the point when it breaks? Because that helps us understand it better. But I think also drives home the message to the reader that this isn't a universal thing. This is a, contextual thing, maybe in a context that is super important to understand or use the method in though.
Yeah, I think there's
Yeah,
there's an interesting paradox where in order to make sort of methodological improvements, sometimes we have to act as though there's a universal method, like we just need to fix it, but we cannot ever really believe that, like, so I think that's another hard sort of paradox. Sorry, Jake.
Oh, no worries. No, I was just going to follow up on that by like, I think that it is a strange part of Jessica, you had at the end of your flow for social sciences, and to some extent also for machine learning, like these stylized facts that pop out. Like we seem to want these stylized facts. We don't want an answer of, well, it depends. Right. And in the way Brandon's saying, like, it depends, it will work here, or this will happen. We expect this to generalize here, or this effect to be present under these conditions, but not these conditions. And I think that's like it's a very hard habit to break ourselves of, but seems very important because it seems less and less likely that we're going to achieve universal, stylized claims like this, whether it's about models or about theories.
Great. Thank you all. I have a lot of other questions, but let's jump to the audience questions now. One for Brandon is, in the prediction based on vocally described autopsies, would it make sense to select features that are commonly identified at home? Would that be adding information, or would that be adding information from the testing data into the final model?
Yeah, this is great. So one of the things I like about the verbal autopsy example, which I'll just be completely clear, I am not an expert in, is that it intersects a lot of things that are changing. So one of the results that's like incredibly robust from this literature is that the thing that degrades, that like is the best predictor of accuracy, isn't the algorithm you use to do the prediction, but the sites that you train on. So like if you train on data from Mexico, that matters a whole lot more than like anything else. And that's coupling a lot of information together, including like what features people are particularly good at answering the questions to, right? Like, as well as the kinds of diseases that are presented in that particular circumstance. And so we need both an understanding of like the psychology of like what people are going to answer well, which is kind of what I take the questioner to be asking about, as well as like, what diseases are common in that particular area. But I think the challenge, of course, is that they're trying to standardize the features they're asking about across the whole world, which is, a very difficult thing to do and sort of precludes the possibility of doing more like contextually specific information features.
Thank you, Brandon. The next question is for Jake and Jessica from Moment, who says, while I didn't mention it in my talk, I'm a fan of predictability and I've used that in my work. And I'm glad that I gave some details that set up the talks. I'm curious about this. I'm curious about if this is purely an issue of theory and study design, or if specific models, specifically post-selection inference, maybe causal forests, could pursue integrated modeling.
Jake, you want to go first, or?
Sure. So I guess I'm going to interpret the question to be, could you get at the question of predictability using some of these methods about post-selection inference and causal forests? I think it sort of relates back to Brandon's point about cats versus people. So I think if you are in a cat's situation and the data are present and the features are present, then sure, I think you can start to do these things. But I think there are often situations where we're in more of the fragile families type of scenario where we're not sure that we even have measured the things that might be relevant, in which case, it's hard to imagine any method that can discover these things. I think there's really nice work on sort of limits to prediction. Annie Liang and John Kleinberg have this nice work on sort of gaps between theoretical gaps where we know we have more to learn, because even with the features we have, we can achieve higher performance with a machine learned model than with theoretical models. And so that's one case where you think, okay, maybe you have the features you need, but there's still some functional form or relationship you need to learn. But in a situation where you don't have those features and you don't even necessarily know what they are, I think that's a really interesting and puzzling situation. And I wouldn't expect those specific tools to be able to help there necessarily.
Yeah, I mean, I was also going to mention this study by Fudenberg and Liang and Kleinberg to make the point that like sometimes I think it's useful to think about predictability just as part of the environment that you're trying to predict in. And so what they're doing there is like they're trying to think about like how humans predict random sequences or produce random sequences. And so they do basically sort of exhaustive data collection so that they can understand like, like how predictable is, like what the average person is going to put next as a sequence of ones and zeros or whatever. Like there's some underlying randomness just in often the data that we're dealing with. And I think machine learning can help us understand like how much sort of inherent variability there is or how much we can actually predict. And so I think of that it's kind of it's less about the theory, I guess, on some level and more just about understanding the environment. But I tend to think, yeah, we do need theory and study design. And if we have a good method, it's only because like we've either encapsulated aspects of that or we're using it in a way that, according to our theory, actually makes it work. So I don't, but I don't know enough about, some of these latest causal ML methods. Maybe I would take it back if I did, but.
The next question is for Jake. The question is, Dr. Loans mentioned earlier about the difficulty of grokking machine learning for newcomers. One reason is likely the use of complex math. What body of math knowledge do you expect undergrads to have to be able to run data replication studies by themselves? And I think that's a great question, Jake, because you've led an effort with undergrads to do data replication.
Yeah, so I really appreciate the question, and I didn't really talk about this data analysis replications work very much, but it was precisely a project to say, can we, to Brandon's point, there's not the incentive structure for people to do replications, at least people who are tenure track faculty, for instance. But as there are students, many students who are looking to learn methods in statistics and machine learning, and we train them in classes. And so we sort of ask the question of whether they could actually do replications that are meaningful. And the incentive structure is there in the sense of if it's a class project, students are assigned to do it and they'll do it. But they'll also learn things along the way. And so it can be beneficial for the research community and for the students. And so we've done this a few times, and with pretty fundamental training in probability and statistics and a bit of regression modeling, linear regression, logistic regression, students have been able to run these replications. And actually, Brandon and I were chatting, and one of the replications that the students did was on the Fryer paper, and just with basic, sort of a couple of introductory classes, they were able to find some interesting details that were sort of glossed over methodologically in the paper. So I think certainly you can pick out examples where maybe you need to know very advanced, software packages or mathematics or things like that. But I think there is a huge swath of papers with simpler methods where students can run these analyses. And they're much more available as well than compared to sort of psychology replications where you have to go out and collect new data. We're talking about just, taking existing data and rerunning analysis.
That's very encouraging. Thank you, Jake. Brandon and I saw that there was a back and forth in the chat about the measurement paper by Jacobs and Wallach. Actually, it would be nice if you're able to elaborate on that, the relationship between your work and theirs. A lot of people might not have seen that paper, so perhaps start with what that paper is about.
Yeah, this is great. So this is some work by Abby Jacobs and Hannah Wallach that was published at FACT, I think, 2021. But everyone should read this paper. It's great. And it's thinking about the connections between the measurement literature and the fairness literature. And it's kind of very self-consciously sort of importing some of the ideas from the social science literature. I think they're sort of heavily drawing off this early work in text analysis and political science by Kevin Quinn, Burt Monroe, and colleagues, who are in turn importing the sort of validity framework that comes out of the psychological, like the psychometrics literature in like the 60s and 70s. And but the sort of the connections between the two is it's all about, like, in some sense, being very precise about what you are hoping to get from the data. And so all of these notions of validity and measurement rely on the idea that there's something that we're trying to capture. And so that's kind of where I think the similarity lies, is this this kind of like explicitness about the goal of what we wanted. And as I sort of said in the chat a little bit, like our work clearly rhymes with them in the sense that it sort of comes from the same methodological tradition. The thing I'll say that's distinct is I think they're thinking primarily about measurement and then like what it can say about fairness, and we're sort of thinking we're actually even just taking the measurement for granted, not because Ian and Rebecca and I are just like super enthralled by the present state of measurement, but because there's just enough problems. Even if you say, yeah, all the measures are good, what are we actually trying to characterize about the world? But there's a whole other layer here that is about like how we choose to measure the things that go into our models, and then how does that interact with what we're trying to estimate.
Great. Thank you, Brandon. Do you mind if I take the privilege of asking the last question? It's a question for everyone, but it's inspired by Jake's 4 quadrants. What I was wondering about was, well, while it's clearly true that there's not nearly enough work in integrative modeling, that's something we want to aspire to in the future. It also seems to me, not as someone admittedly who's an expert in computational social science, but there also doesn't seem to be enough description work. I feel like I've heard other people say that, including Brandon. I know that there is a recent journal called the Journal of Quantitative Description to encourage more of that work. So if that is true, I was wondering if folks could speak about why there isn't enough of that work, and how to encourage that kind of work, why it's important, and so on.
So just, can you give an example of description so I'm somehow specific to like really large data sets, or just in general, you mean descriptive, like big observational data sets?
Yeah, I can try, but I'm sure the social scientists could do a much better job. So collecting data sets and describing them and describing what is going on in the world, right? So the analogy that is inspirational for me is, let's say, a biologist describing a new species. They're not making some inferential claim about some population. There's not really the question of replicability of the kind of the sort we've been talking about here. Hey, I saw this new kind of bird. Here's what it looks like. Here's how it relates to other species. That is so obviously considered extremely valuable in that world. But I don't know, in a lot of the areas that I work in, that doesn't seem to be the case. I really enjoyed working together with Brandon on a project where we collected a whole bunch of emails from politicians, and we're like, hey, what are they saying in this data set? And let's write a paper about that.
Got it. I mean, I guess my first instinct is that people want to be clever, and I think it's less obvious how clever you are when you're doing something descriptive. We want to test hypotheses or have come up with something new. And I mean, that's the biggest difference to me. I would say, I guess, like, this is not quantitative description, but I think it's interesting how much work at like the HCI AI boundary or HCI ML boundary is getting more descriptive. And even some of the work on like limitations of machine learning, we see more and more of these qualitative studies where people are just going in and looking at like how engineers are working, which is very different than quantitative description. But it's, I guess it's sort of encouraging in that, some pockets of the community that cares about some of these issues are actually trying to remove their sort of need to, make some clever solution and just to describe what's going on. So.
Yeah, and Jessica, just to follow up on that, I think that idea that, the feeling clever, and maybe to your point about stylized facts as well. So Arvind, even in what you said, maybe some biologist, goes out and looks at birds and says, I discovered a new species of bird. That's even a clever statement there, as opposed to just, I went out and I measured the distribution of wing sizes for birds, and I have a new instrument for doing so, which is admittedly less clever sounding and less interesting sounding, but very important, right? So this idea that like we are driven to these statements that seem like they explain things in a very broad way, I think works against these sort of more, minor sounding things that are still foundational and very important for what we need to do.
Yeah, I completely agree that like the problem is if you describe something interesting, people are going to hunger for an explanation of what is happening in that thing. And I know so this journal that Arvind mentioned was started by Kevin Munger, Andy Gass, and Esther Hargitay. And Andy's at at Princeton in politics and the public policy school, and he and I have talked a bunch about the journal, and they in their sort of their sort of throw down message to the field of like, this is what we're doing and why we're doing it. They sort of said like, we don't want these like causal stories in the journal. And talking to him now, a year or so out from it being published, I think it's actually really, really hard to tell when a thing is purely descriptive, because you're still baking in some like theoretical understanding of the world, why you're choosing to describe the things you're trying to describe, how you're choosing to operationalize those properties, and even like giving an account of what's happening. So, you think of something like a study that Jake mentioned really briefly about diffusion dynamics. And, it like, there was this like, how do these things spread through social media? And that's a very, it was very descriptive in terms of like, here are some patterns, but it also had an account of the way the process unfolded, which is in some sense, a causal account about the idea that there are these like, it basically things makes its way to a broadcaster who then pushes it out to lots of people, as opposed to being viral in the sense that we tend to think about virality. And so, so you can't, as actually was just said in the chat, right? No observation is theory free, and that's the fundamental challenge.
All right. I think the importance of theory is a great note to end on. There's one more question in the chat I couldn't get to, but I will surely email it to Brandon, and we'll put up responses from speakers on the website. I just want to take a few minutes for some closing thoughts. My brain is fried in a very good way after 6 hours. I hope all of yours is as well. I know I'll be going back and watching the videos, just so many good references and ideas for research. We do have some very concrete next steps for those of you who are interested, so please stick around just for a couple more minutes. One observation that came to mind as I was listening to all these talks is that I think there are two main motivations here why we need to pay attention to these issues and do a better job. One is at an individual level, we don't want our research, to be flawed. We want to improve its quality and validity, and we've heard so many ideas for how to do that. The other motivation, the less obvious one, but perhaps even more important one, is collective, because what's at stake here is trust in science. And when these reproducibility crises spread, we've seen in the past that it undermines the credibility of an entire discipline, and it could undermine the credibility of all of science. So that's something all of us have a stake in, especially at a historical time when the institution of science it has a little bit of a credibility crisis among the general population. So I think that's another reason for all of us to take this seriously and to have structural interventions. Again, we heard so many ideas about that. What can journals do? What can funding bodies do? And so on. So I hope you'll keep those ideas in mind as well. So I think one kind of structural intervention, perhaps, if I may be so bold as to say it, is events like this when they bring so many disciplines together, and this kind of exchange of ideas, I think, is very important. So on that note, we have a number of ways for you to stay in touch with the other folks you've met, including our Slack. So I'll turn it over to Sayash to say just a few words about what some of those next steps are.
Amazing. Thank you so much, Arvind. And thank you to all of you for attending the workshop. I think we were really overwhelmed by all of the support that we had from all of the participants, the speakers. So thank you so much. I wanted to quickly go over some of the ways in which we can keep in touch post-workshop. So for those of you in the Zoom chat, we can quickly paste this link in the chat. For those of you on YouTube, hopefully you'll be able to go to this website. So we have a few next steps in mind. The first one is tomorrow afternoon at 3 p.m. Eastern time, we're organizing an interactive session on model info sheets. As I mentioned at the beginning of the session, we created these with the aim of solving leakage specifically in ML-based science. Perhaps more interesting is that our Slack channel now has over 150 researchers already. All of us are interested in reproducibility and ML-based science. So if at all you're interested, please join the Slack channel. The third one is Kenny, one of our co-organizers, came up with a couple of questions about your own experiences with reproducibility, like what are the challenges, what are the fixes you've seen that work well. So if you have a minute or two, we would love to hear your responses. We also plan to put these up online on our website along with the other post-workshop materials. And last but not the least, please provide feedback. So what went well, what could be better? I think we have feedback forms for both of the last two questions on the link in the slide. So everything on this slide is present on the bit.ly link on this, the bit.ly link here. I hope you'll take some minutes out of, I'm sure you have extremely busy schedules, but please do take some minutes out and fill out these forms, give us feedback, join the Slack channel if you're interested. And if at all solving leakage seems like something that might be of interest to you, we'll see you tomorrow at 3 p.m. For the rest of you, thank you so much for attending. I think this was great, well beyond our expectations. And I'm just overwhelmed by all of the support that we had. So thanks a lot.
Yeah, I just wanted to say thank you again to the participants as well as to the organizers and staff. This was just such an amazing event. Thank you. And we'll end the meeting here and we'll end the live stream as well. Have a good one, everyone.